Hello, hi, namaskar. I Deependra welcome you all in the one-shot video of Vector Algebra. This chapter, Vector Algebra, is such a crucial chapter that in 2023, JEE Mains has asked 48 questions from it. Can you believe that? So Vector Algebra, when clubbed with 3D geometry, becomes the second most important unit after matrices and determinants. So when these 4 chapters are done properly, I hope you are imagining how important or how vital they become. So in this one shot, we'll cover everything related to vector algebra, whether it is theory, formulae, short techniques, along with a lot of previous year's questions. Of course, with this one shot, we'll provide you the handwritten notes and the DPPs for your practice at absolutely free of cost. The notes and the DPPs are available on our PW app, link to which is already given in the description box. PW app is an amazing application or a platform from where millions of students are already preparing for different competitive examinations and they are getting the desired results. So without further ado, let's get started with vector algebra. So before we get started, let us first of all understand what all we'll be discussing in this particular chapter. Vector algebra, first of all, discuss algebra of vectors. The two most important topics from which the maximum number of questions are asked from this particular chapter are algebra of vectors and product of two vectors. STP and vector triple product, scalar triple product and vector triple product are important, but these two hold the more importance from this particular chapter. I hope you have clarity that this two, algebra of vectors, which includes a lot of things, along with product of two vectors. This part here has the most importance. Along with this, of course, we'll discuss STP and VTP, but this particular part you need to pay more attention to. This is also what you should study, understand and learn, but this is the part from where most of the questions are framed. But what you need to understand is there are certain questions based on these topics which can be handled or done or easily with more efficiency if you are aware of these two. So they have their own importance, which may not be visible. So yes, all of these are to be studied with utmost integrity and sincerity. And how? Let's explore one after another in these coming slides. So let's begin with the first part here. What do we have here? First of all, let us understand that what do you mean by position vector of a point in a space? So a lot of things will start happening in 3D now, because we'll discuss vector as a concept being imagined in 3D. So we need to have a more better visualization skills, because that is what is expected in this particular chapter. I'll personally try my best in making you understand that. I'll personally try my best in helping you in visualizing all these things. But yes, of course, you should also be more open and flexible in learning these concepts. First of all, try and imagine that let's say we are given a particular this room kind of a structure. In whichever room you are studying and watching this video, it must be a room, we believe so, and it's a cuboid, let's say. So this is a 3D shape which you all need to understand. So let's say I have a 3D shape somewhat like this. So let's try and create a cuboid here. So if I were to create a cuboid like this, I think this is how things will be formed. So I'm connecting this with this one here. I'm connecting this with this one here. And I'm connecting this with this one here. I'm just trying to demonstrate how do you imagine a point in 3D. So this is what I have connected here. I hope there is no confusion on it. Now, let's say this we are treating for a while. Let's say we are treating this as our y-axis. This one I am treating as our x-axis, let's say. And this particular part I'm treating, let's say, as our z-axis. I hope there is no confusion on this particular part. So these three lines I'm having as our y-axis, x-axis and z-axis. So I hope I am labeling them. This particular axis we are labeling as y-axis. This one we are, let's say, labeling as z-axis, and this one, or rather if I create a right triangular system. So let me begin with this part, that let us treat this one as x-axis, this one as y only, but this one as z-axis. I hope you are comfortably understanding this particular part. So this is what we are imagining in 3D. Now, we all understand that the point where all these points are intersecting must be the origin. So this point here is called origin, which is having the coordinates 0, 0, 0. So gradually we are entering into 3D. But before understanding 3D, three-dimensional geometry, I'm wanting you to understand the concept of vectors. So let us imagine that there is a point. There is a point P here. So let us imagine that there is a point P here. So this is a point P here. Now, what you all need to understand is that let's say from origin to this point, I have created this straight line. So this origin is connected to this point P in this manner. I hope you all must be able to visualize what I'm trying to demonstrate or show you here. I hope you're able to think of it in a sense where I'm asking you to imagine it in 3D. Now, if let's say I say that this point P has coordinates x comma y comma z. Now, how do you define the position of this point P in 3D space? So let's say this is my frame where x-axis, y-axis and z-axis are helping us in fixing a point, in imagining a point, in positioning a point in 3D. So how do I do that? So with the help of this frame x, y axis, x and y and z axis, I'm able to create this frame, and with this reference, I'm looking at this point P. So how am I able to define this point P uniquely? That's what I'm trying to make you understand here. So let's say this point P has the coordinates x comma y comma z. Now, what is the meaning of x comma y comma z? That's exactly what we'll discuss. And through this, we'll understand the position vector of a point P in space. So let's say this is a point P, and point P has the coordinates x comma y comma z. I'll try to avoid most overlapping here so that you don't get confused here. So let's say here, I hope you all must have noticed that if P is a point, and from point P on the xz plane, I hope you can see there is this plane xz plane, there is this plane yz plane, and there is this plane xy plane. I hope you can see it all very clearly. So let's say from this point P, I am dropping a perpendicular on the yz plane. Can you see the yz plane? I am drawing it more clearly so that you can see it more clearly. Let me try a line here. So this is a line here, right? And parallel to this line, sorry, parallel to the OZ line, let me draw another line here, somewhat like this, right? Even if I draw it like this, then also it should be understood, but let me draw it like this only. So I am drawing a line like this, just trying to help you in visualizing this more properly. So can you see this YZ plane over here? So what I am doing is, from this point P, I am dropping a perpendicular on this YZ plane. So let's say I am calling this point A for a while. So if this entire structure, which happens to be a cuboid, can you not say that this length PA will be equal to this length over here, which I'm highlighting by this particular part here, this portion here? Not just that, this particular length will be equal to this length also, which will be equal to this length also, but I am interested in this length here. I hope you are noticing this part very clearly here. So if I have dropped a perpendicular from P to the YZ plane, I got a length PA, which length, I hope you all are able to understand, is the length of this point P from the plane YZ. So the distance of this point P from the plane YZ is helping me in denoting the x coordinate of this point P. I hope you are able to understand. With these three axes, x-axis, y-axis and z-axis, we are able to divide our space into 8 octants. In 2D geometry, we have x-axis and y-axis. And that's how in 2D geometry, we are able to divide our space into 4 quadrants. But with 3D, I hope you are able to imagine, if I am able to create 3 perpendicular lines, which are called x-axis, y-axis and z-axis. These are mutually perpendicular lines. With these 3 axes, I am able to divide my space. It is not 2D space, it is 3D space. So this 3D space into 8 octants. And here, if I'm dropping a perpendicular from P on the YZ plane, I'm able to create a length, I'm able to measure a length, and that length is helping me in deciding the x coordinate of this point P. Although as per the octant, the sign also matters. But here what you need to understand is that in a sense, when I'm talking about the length, if I'm talking about the x coordinate of P, that gets decided with the help of the length of point P, the length of perpendicular, dropped perpendicular from point P to the YZ plane. In the same fashion, will you not say that if from point P, I am dropping a perpendicular on the XZ plane, let's say for a while. So this length, this length, this length, and this length, would it not be equal? And if I talk about this length, is this length not assisting you in deciding the y coordinate of this point P? Similarly, what now I'm left with is, let's say from this point P, I drop a perpendicular on XY plane. So can you not help me with this understanding here that this length will be that perpendicular's length, which I have dropped from this point P on the XY plane. And this length luckily will be equal to this length and this length here, which is this length. And this length over here is going to be the z coordinate of this point P. Although sign will also matter or come into picture depending on the octant. But what I'm trying to make you understand is, how are these points x, y, z, how are these coordinates getting decided with respect to this point P when you're discussing this particular thing with this coordinate system in mind. So I hope there is no confusion on this particular part. I'm just removing this portion also so that it remains more clear to you. I hope this part is very well understood by you all, that what do I mean by x, what do I mean by y, and what do I mean by z. So if I were to write it here, I will say that this portion here, this length here, from O to this length here will be representing x, although in terms of distance I'm mentioning here. It depends, if I'm taking it on the positive side of x, then it should be plus x, otherwise it should be minus x. Similarly, this length over here, this particular length, I hope you are getting more clarity over here. This length over here will be denoting y. And similarly, I hope you are noticing this length here, this particular length. In 3D, you are able to imagine this particular part. So if this length I were to talk about this length, then this length is here, is giving you the idea on the z coordinate. And it all depends if it goes on the other side of z-axis, if it goes on the other side of x-axis, if it goes on the other side of y-axis, then the coordinates are taken negatively because those are the negative sides of those axes. I hope it makes complete sense. So that's how you get 8 octants. So a point can be placed into any octant depending on its coordinates. But here what you need to understand is that if I take this 3D imagination into vectors, this point P can be imagined, or this point's P position vector can be taken as, which is written as OP as x I cap plus y j cap plus z k cap, where I, j, k are your unit vectors taken along the x-axis, y-axis and z-axis respectively. I hope you are getting it. From 3D, I am relating it with vectors. So that's exactly what will keep on happening. Vectors in 3D look like two different chapters, but they go along. They move simultaneously. They move together. So whenever there is a concept which is studied in vectors, can be studied through the lens of 3D as well. Or if something you are observing or solving or noticing through the lens of 3D, can be learnt or observed or understood through the lens of vectors as well. So that's the relation I'm trying to establish here. So if there is a point P in 3D, and if it is denoted by x comma y comma z in 3D, then its position vector. I hope you are able to understand the meaning of position vector from origin to P. If I'm creating a vector, so P is defined as, position vector of P is defined as xi cap plus yj cap plus zk cap. And what is position vector P? OP vector. So I hope you are understanding this OP vector is given as xi cap plus yj cap plus zk cap. Give me a complete clarity. Did you understand this particular part? That's exactly what we are told in this particular part. I hope there is no confusion on this part. Whatever I have said so far is written over here. So I hope you have gotten a great, a complete, a very good clarity on vectors, positioning of a point, how do you define the position vector of a point, and how do you see things in 3D. That is also not confusing at all, and it is very well understood. I believe so. With that, let us proceed ahead. Let us move to the next part, where I'll try and tell you, let's say if there are 2 points in 3D, how do you define the distance between these 2 points? So if there are 2 points, let's say their position vectors are given by x1 I cap, y1 j cap, z1 k cap, or in 3D I could call it x1 comma y1 comma z1. I hope you're able to relate it now. Similarly, if there is another point x2 I cap plus y2 j cap plus z2 k cap, that is the position vector of the second point. Or in 3D it can be called x2 comma y2 comma z2. Then the distance between these 2 points. Then the distance between these 2 points is given by, I hope you are understanding this particular formula, which you must have learnt in 2D as well. But in 2D, this is the part which you didn't see. But in 3D, this is also introduced. So it is, okay, so there is a small correction here, which I have seen right now. So this should be x2 minus x1 whole square plus y2 minus y1 whole square plus z2 minus z1 whole square inside an under root. The part here I'm trying to make you understand is very simple. The part is very, very straightforward. Let's say there is this vector, I'm really sorry. There is this vector OP. There is another vector, let's say OQ, and now we are defining the distance between P and Q. So this is, let's say O, this is P, and this is Q. So P has points, coordinates x1, y1, z1. Q has the coordinates x2, y2, z2. So if I were to define the distance between PQ, let's say. So if I were to define the distance between PQ, so I hope by vector law of addition, which we are going to discuss right now, discuss after these slides only, the triangle law of addition, by using this particular part, I can find the vector PQ as well, because I have the position vector OP, I have the position vector OQ, then I can define the, vector PQ as well. We'll learn this particular part, don't worry about that. And once you have defined the vector PQ, you can find its magnitude, and its magnitude will be nothing but the distance between these 2 points P and Q in 3D. I'll give you a clarity here only. Let's say if I were to define the vector OP, what is vector OP? So position vector P, it is given by, let's say, x1 I cap plus y1 j cap plus z1 k cap, let's say y. How do you define vector OQ? So if I were to define the vector OQ, I will say it as, let's say, x2 I cap plus y2 j cap plus z2 k cap. Let's say that's your vector OQ. I hope there is no confusion on it. Now, vector law of addition, triangle law of addition on vectors, which you must have studied in physics as well. If I could use that property, we know that if I add vector OP to the vector PQ, then by triangle law of addition, I'll get the vector OQ. Did you all understand that part? Now, if I take OP on the other side, the vector PQ now will become, OQ minus OP. Right, students? I hope you're getting this part. Now, what is OQ? This. What is OP? This. So, from OQ, if I am subtracting OP, elements, the corresponding coefficients of I cap, j cap and k cap can be subtracted. So, PQ vector, as per our understanding, can now be written as OQ minus OP. So, this vector minus this vector. So, x2 minus x1 I cap, x2 minus x1 I cap plus y2 minus y1 j cap plus z2 minus z1 k cap. Now, if I were to ask you the magnitude of the vector PQ, why am I saying the magnitude of the vector PQ? Because the magnitude of the vector PQ will be the length of the PQ, which is the distance between the point PQ. So, if I am asking you to find the magnitude of the vector PQ, I hope you know how to find it. The magnitude of the vector PQ is going to be nothing but what we are given here. How? I'll take the square of the I component, I'll take the square of the y component, the z component basically, z cape component, and I'll take the square of the k cape component. And then I'll add them up, and then I'll take the square root of that sum. I hope you know how to take the modulus of a vector. So these are the basics which you all must be aware of. If you are not, this is what you already study in physics. Even if you have forgotten it from there, I am making you recall all of these basics from this particular chapter, vector algebra as well. So I hope you have started understanding what is the vector, how do you define a vector by its position vector, and then how do you find the distance between 2 points if their position vectors are given by using this distance formula. How did it come from? Where did it come from? How do you use vector law of addition, triangle law of addition? How do you find the modulus of a vector? What is the significance or meaning of the modulus of a vector? PQ, the magnitude of the PQ, the modulus of PQ will give me the length of the vector PQ. So I hope you are able to relate 3D with vectors now more clearly. With that, if I could proceed further with the next concept, I hope I need not tell you, if I wish to find the distance of a point from origin, then I need to find the magnitude of the OP vector, the position vector of P, which is what? If P is xi cap plus yj cap plus zk cap, then I'll call it under root over x square plus y square plus z square. That is how you define the distance of a point from the origin. I hope you know this. In 2D also, we write it as under root over x square plus y square. So here, the only thing which comes into picture is this z square. So you will be able to relate 3D and vectors a lot with what you have studied in 2D. You will realize it while we proceed ahead with this particular chapter. Along with 3D also, you will see or notice this particular part happening very clearly. So related with that similarity and keep learning, that will ease your learning. Now, let's move to the next part. I hope there is no confusion in this part, that if you are having a vector P and if its distance is needed to be found from origin. So let's say this is the vector P, which is clearly nothing but what? The vector P, the position vector P is given by xi cap plus yj cap plus zk cap. That's your position vector P, which is OP. So that's your vector OP. And if I were to discuss its distance from origin, the distance of point P from the origin, all I need to find is its magnitude. So its magnitude is going to be magnitude of the vector OP, which is given by under root x square plus y square plus z square. I hope this makes complete sense and you are able to understand all of this. Moving ahead, the next remark which you need to understand is that if somebody says that two vectors are same, let's say two vectors are same. So let's say this is a vector and this vector is same to this vector. So if these two vectors are same, we all know that these two vectors, let's say this is a vector PQ and this is a vector AB, right? So if somebody says that vector PQ is equal to the vector AB, if I'm told that vector PQ and vector AB are equal, then I hope you're realizing if two vectors are said to be equal, then it is possible only when two things are given, that their directions should be same and their magnitudes should be same. So first of all, their directions should be same. So both of them should be parallel or collinear. Second conclusion, that they should have their magnitude same, their length should be same. Then only we say that two vectors are same, equal. So if in the terms of component, if I were to discuss that these two vectors PQ and AB are equal, let's say the two vectors which they are taking as A vector and B vector here. So there is a vector A here they have taken here and there is a vector B vector here which they have taken here. And if they say that vector A and vector B are equal, which will be possible if their corresponding components of I cap, J cap and K cap are equal, which means A1 should be equal to B1, A2 should be equal to B2 and A3 should be equal to B3. I hope that part is also very well understood by you all and you are getting complete clarity on it. Moving ahead to the next part, what do we have here? Direction cosines. This is what we'll study while discussing the direction, while discussing the chapter 3D as well. But here also, we have gotten the opportunity to discuss it. So let us get clarity on it through visualization only. So do we have the figure here? Yes, we do have. It may look a little confusing, but through this figure only, I'll try to give you clarity on direction cosines. I'll give you understanding of one angle only, then only I'll ask you to imagine the other two angles, because in this particular figure, making you understand everything is a little tricky and difficult. So I'll give you clarity on one angle only, and on the understanding of that angle, I'll assume that you will get clarity on the other two angles as well. So let us understand one angle only. First of all, again, I'll begin with this point P. So we have a point P in space. I hope this figure is properly visible to all the participants. Yes, it is. So this point P has the coordinates x, y, z in 3D. So I'm keeping vectors in 3D on the same parallel track. So whenever, if I'm using the terms related to 3D, you don't get confused and you actually understand that this point P will be having the position vectors and as xi cap plus yj cap plus zk cap, which I'm not mentioning time and again. So I'll keep interchanging 3D and vectors, right? As per the need, as per the requirement. So whichever way helps us in understanding a concept in a more easier or efficient manner, I'll use that. So either 3D or vector will keep on moving parallel. I hope that doesn't confuse you. So in 3D, we have a point P, x, y, z, right? What I know is, how are we defining this point P's x coordinate? I hope you must have remembered it. You know it very clearly that if I have this point P, which is having its x coordinate, then how did I get this x coordinate? I hope you must have remembered that this particular length, or you may call it this particular length, or you may call it this particular length, or you may call it this particular length. What is it? It is the perpendicular distance of point P from the YZ plane. Although if it is on the positive side of x-axis, it will be plus x. If it is on the negative side of the x-axis, it will be minus x. So here, if I have this x, which is the x coordinate of P, then I hope you're realizing this must be this length only. So OA is going to be x. Do you all get that? OA is going to be x. Do you all understand that? Do you all get that? I hope there is no confusion on it, because this is what we had begun our discussion with right now. What I am doing is I am dropping a perpendicular from P to A. Now in 3D, it may not look like a perpendicular, but it is. Imagine in 3D, try to imagine that you have in 3D, which I'm trying to make you visualize in 2D. That's the challenge here. But let's say if you have this is your x-axis, let's say, right? And this is a point P. Right. So what I'm doing is from point P, I am dropping a perpendicular on the x-axis. So this is what is happening here. So that's your point A. But it may not look like a perpendicular because this is what we are drawing in 3D. And of course, this over here is your point O, which is nothing but what? The origin. So this is your origin, this is your point P, this is A, which is the feet of the perpendicular dropped from P on the x-axis. But this 3D part, I am making you visualize in 2D. I hope there is no confusion on it. We all know that P has coordinates x, y, z. So can you help me with OP? So I hope you know OP in a sense is going to be basically, if I am denoting P by vector R, so mod of vector R will be denoted by under root over x square plus y square plus z square. I hope you know this much discussion we already had so far. Now, so what I know is that OP will have a distance mod R. I hope there is no confusion on it. Now, can you help me with this OA? We all know what is OA. OA is going to be x, because we all know OA is going to be x. We all have studied it so far. So if I say that when I joined P with O, this PO made an angle alpha. This PO made an angle alpha. In 3D, it is hard to imagine or visualize. That's why I'm doing it all here. So what I'm trying to say here is that this PO, I hope you can see, is making an angle alpha, with the x-axis. So if I were to ask you, can you define cos alpha for me? You will say, sir, it is always base upon hypotenuse. It is x upon r. Did you get that? Did you all understand this particular part? I repeat, in 3D, it is difficult to understand. So I brought that 3D picture into 2D and tried demonstrating to you all. If you didn't get that part, take 3 pen, keep them mutually perpendicular, treat them as x-axis, y-axis and z-axis, and take another third pen. And from that pen, treat one of the pens as x-axis, and that fourth pen which you're positioning in the 3D space, that vector you can treat as a r vector, OP vector, and then you can also start visualizing the alpha angle, beta angle, and the gamma angle, which the vector OP is making with the x-axis, y-axis, and z-axis. And with that, when that 3D visualization is done by you on your study table, you can come to this conclusion that what I'm trying to say here is absolutely correct. I hope you're getting my idea, which I'm suggesting you all to do on your study table. Now, let me get back to the part here. If I could generalize cos alpha as x upon mod r, do I need to explain it for cos beta and cos gamma? Because now generalizations can be done because there will be similarity. So here, that's exactly what I'm trying to make you understand, that if you have cos alpha, then you can evaluate cos beta, and also you can evaluate cos gamma. So here, that's exactly what we are trying to make you understand, that here, I hope you all can notice this part here, that cos alpha, cos beta, and cos gamma. What were alpha, beta, and gamma? The OP vector, the angle the OP vector makes with x-axis, y-axis, and z-axis respectively. I hope you're getting this part very clearly. So if I take the cosines of those angles alpha, beta, and gamma, if I'm taking the cosines of those angles alpha, beta, and gamma, which are nothing but cos alpha, cos beta, and cos gamma. So these cosines of these angles alpha, beta, and gamma are called the direction cosines of the vector OP. Tell me honestly, are we clear on this particular part when I'm mentioning direction cosines? What is direction cosine? Did you get clarity on it? I hope you are understanding what is cos alpha, cos beta, cos gamma. If I were to define it as, it will be x upon r, y upon r, z upon r. I hope you are getting it very clearly. R means the modulus of the vector r. So this is the most crucial part which you should have in your mind. Along with this, one more conclusion, if you are able to draw, you can draw very easily that if I am having cos alpha as x upon r, cos beta as y upon r, and cos gamma as z upon r, and if I were to ask you what will be the value of cos square alpha, plus cos square beta plus cos square gamma. I hope you can relate it very clearly. It should be x square upon r square, y square upon z square, and y square upon r square, and z square upon r square. So it should be x square plus y square plus z square whole upon r square. Do you know what is x square plus y square plus z square? I hope you know. It is r square. So it is r square upon r square, which is going to be 1. So always remember, the sum of the squares of direction cosines is always 1. I repeat, if I am denoting direction cosines as L, M, and N. So let's say I am denoting cos alpha as L, cos beta as M, and cos gamma as N. So always remember L square plus M square plus N square is equal to 1. This is something which should be there at your fingertips whenever something related to direction cosines is discussed. Will you keep this in your mind? So whenever direction cosines gets discussed, you should have this conclusion in your mind that if the direction cosines are L, M, and N respectively, in that case, L square plus M square plus N square will always be 1. Why? You have the conclusion here, but you should remember this as a result. Moving ahead, I hope there is no confusion on this particular part. Let me just check. I hope I haven't missed or skipped anything. We are going great. That's exactly what we are trying to conclude here. That's exactly what is written over here. I will now move ahead with the part where we discuss addition, subtraction, and all related to vectors. Then we'll move to the product of vectors, then vector triple product, scalar triple product. All of that will also come into picture with a lot of things. Let's begin with this particular part where we'll be discussing the triangle law of addition. So triangle law of addition says a very simple thing that if you have two vectors, since we have already these things written over here, I'll use this particular part only. So this is the vector AB. This is the vector BC. So if I'm adding AB vector to BC vector, then I'll be getting the vector AC. I repeat, the conclusion I'm trying to give you is very simple. If AB vector is denoted by A, if BC vector is denoted by B, then vector A plus vector B can be said vector C, which is nothing but this side of this triangle. So whenever two vectors are given to you and their addition is needed to be done, form a triangle. Just ensure that you follow the order. Now, what do I mean by the order? The order is very simple. Let's say if I am told AB vector. So let's say if this is AB vector. Let's say this is AB vector. So if this is said to be an AB vector, then I need to understand this thing very clearly here, that this will be A and this will be B. Now to this AB vector, let's say I'm adding BC vector. So let's say this is BC vector. So this is BC vector. So this is B, then this should be C. So if I'm adding AB vector to the BC vector, then the sum will be AC vector. I repeat, then the sum will be this AC vector. So this AC vector over here will be equal to the sum of AB and BC. The direction, the order, I hope every single part which is being mentioned or discussed is understood by you all. I hope you are getting a very good clarity on vector law of addition. Any confusion so far? Did you get this part? So if I'm adding two vectors, let's say AB and BC, it will result into AC. And how did you get that part? Now, if vector law of addition is understood by you all, then we'll discuss parallelogram law of addition. What is parallelogram law of addition? If we have an image, I'll use that. Yes, we have an image. Or rather, if you don't want to see that image, I'll just simply tell you, make you an understanding this particular part. Let's say we have a parallelogram, right? Let's say we have a parallelogram like this. Okay. Now, what you need to understand here is that let's say we have vectors. Like let's say if this is point A and if this is point B, right? So let me call this vector AB. Can I call this vector AB? And similarly, we have this point, let's say C. So I can call it vector BC accordingly. So if I were to ask you, can you find AB plus BC? So you will say, sir, if I'm asked AB plus BC, or rather, let's say I'm asked AB plus AD, depending on the requirement, whatever kind of vector is asked, you can draw them properly on your space and then you can design your results based on vector law of addition, triangle law of addition. What I'm saying is, if I'm asked AB plus BC, can you help me with that? We know vector law of addition, triangle law of addition. So AB plus BC, I hope I need not tell you, AB plus BC, you all can predict very easily that, sir, AB plus BC is going to be AC. Can you not see that happening over here? So had I asked you AB plus BC by triangle law of addition, you could have said, sir, it is going to be AC. But what if I'm asked something else? Now, what is that something else? Let me take you to this particular figure here and try and make you understand. Let's say we have a vector OA. So we have this vector OA here. I hope you can see it right there in front of you. We have another vector OB like this. So we have another vector OB. And then we are asked to add vector OA to OB. Now, previously what was happening was AB vector was there. So the head of the vector AB became the tail of the vector BC. I hope you can see here. My point here is that if both of these vectors OA and OB have the same tail O, their heads are A and B respectively. And if I'm asked to add them up, can I do so? Yes. We know that if to this vector, I draw another vector which is parallel to this vector and its magnitude remains the same. If its magnitude remains same, so to vector B, let's say I have created another vector which is parallel to B, which is maintaining the same magnitude, then can I not say that this AC will be equal to that this AC, I hope no changes made, yes. So I can very easily say that this vector AC and vector OB are equal. And if vector OB and AC are equal, and if I'm adding vector OA with OB, if I'm asked to add vector OA with OB, I can say that I can add it as treating OA as OA, but OB as AC. I hope without any hesitation I can do that. Why? Because these two vectors are parallel and their magnitudes are same. So OB and AC are equal. Now by using the triangle law of addition, OA plus AC, I hope you won't hesitate in saying OA plus AC will be OC by using the triangle law of addition. So will I not say that this now becomes OC here? Any confusions on that? So are you understanding what is the parallelogram law of addition? Any confusions on that? If in simple language, if I were to conclude this particular conclusion, then always remember, let's say this is the, I need to flip it, right? So I'm flipping it so that you can understand it more clearly. Let me flip this here. Just give me a second, everyone. Flip here, right? Great. So this is what will be more understandable for you. So here, let's say this is a vector A, point A, then you have a point B. So this is vector AB, let's say, and this is point C. So that's your vector AC. So what is the challenge here? That we know AB plus BC, let's say, for a while, right? But I don't know AB plus AC, or let's call it D for a while here, because I'll call C so that the cyclicity remains. Nothing changes here. So let's say I'm asked to find AB plus AD. So the tail is same here. Previously, AB plus BC is what we used to do. So what I'm trying to tell you is that for a parallelogram, the opposite pair of sides are equal. So if the opposite pair of sides are equal, which means their magnitudes are equal. Not just that, since it is a parallelogram, so AD will be parallel to BC. So that is why I'm saying that parallelogram helps you in understanding that this vector AD can be taken as the vector BC because they are same in direction and magnitude. That means they are the same vector. They are the equal vectors. Which means if somebody asks you to find AB plus AD, I can say that it is equal to AB plus BC, which is equal to AC. So I hope you are able to understand parallelogram law of addition. There is no confusion on it. If you have gotten clarity on this particular portion, parallelogram law of addition, there is another thing which is called as polygon law of addition. Now, instead of giving you the entire proof, I'll directly conclude this, that what is the polygon law of addition. Let's say here, if I am given certain, sides of a polygon, any kind of polygon, regular, irregular, whatever it is. But let's say this is A, B, C, D, E, F, that's a polygon. Now, what I'm doing here is, let's begin with this part. Let's say I'm adding AB to BC to CD to DE to EF. So I'm beginning with AB, let's say, right? So the direction they have taken oppositely in the opposite manner. So let me just check the figure. Okay, great. So what they are doing here is, let me tell you by making it more clear here. See, the basically figure in the challenge is this. The challenge is a little different because they have drawn a little different figure and taken different data. So I'll simply correct the data. Okay. So I'll simply correct the data that is in my hands. That will be more efficient. Just give me a second, students. I'll correct the data here. Okay. So don't worry about it. I'll just remove this A from here. I'll just remove this A from here, B from here, C from here, D from here, so that you understand it more clearly. E from here and F from here. Now let us look at this. Just pay attention to this part, students. Now let's begin with this part. Okay. We need to begin with AB, BC, CD, D, and EF. And that is set to be, let's say, AF. Why? Let's work on that. So I now am beginning with, let's say, AB, right? So let's say this here is your AB. This is basically taken, that's wrong. The entire figure is wrong because these two directions are same. Okay, so skip that figure. Let's draw our own figure so that we don't get confused. Remove this particular part, forget this whole part. I'll draw a different polygon. So let's say I have a hexagon here. Okay, why to create a confusion here? Because the arrows are also not in sync in that figure. So let me begin with this part. So let's say this is a hexagon. Regular, irregular, that doesn't matter. And this hexagon has its own 6 vertices. Let's say A, B, C, D, E, and F. I was trying to work on that, but that was not correct. So let me use this particular figure now. Now, let's say we have this vector AB. So I'll begin with this vector AB. So we have this vector AB. So this is your vector AB. To the vector AB, I'm adding vector BC. So that's your vector BC. To the vector BC, I'm adding the vector CD. Okay. To the vector CD, I'm adding the vector DE. To the vector DE, I'm adding the vector EF. So here, if I'm adding all these vectors, by using the basic concept of triangle law of addition, you can conclude that this AB plus BC plus CD plus DE plus EF is going to be equal to AF. Is going to be equal to AF. That's what I'm trying to make you understand here. How triangle law of addition comes into picture. So AB plus BC, if I were to do it, can you help me with AB plus BC? You would say, sir, AB plus BC. I'll use this particular part here so that you don't get confused. Can you help me with AB plus BC, students? Sir, that would have been AC, right? Then AC plus CD would have been AD. Are you getting it? Then AD plus DE would have been AE. Then I hope I need not explain you. AE plus EF would have been AF. Triangle law of addition extended, that's it. Are you understanding this polygon law of addition? What you need to understand is it behaves as displacement because displacement is a vector quantity. So imagine it, how I remember it. If I started with A, point A, I went to B, then C, then D, then E, then F. So effectively, in a sense of displacement, how much did I move? So effectively, starting point was A, and the final point is F. So effectively, the displacement is AF. So no matter what you did was AB with BC, then CD, then D or EF, conclusion is you are on F. That means the effective distance you have covered, which is displacement, is going to be AF. So that's how also you can remember the polygon law of addition. I hope you are getting complete clarity on it. Now, moving ahead, addition in component form, the way we have already discussed. Let's say we have two vectors. First vector is A, which is A1 I cap plus A2 j cap plus A3 k cap. There is another vector B vector, which is B1 I cap plus B2 j cap plus B3 k cap. And then I'm asked to add these two vectors. So we know triangle law of addition, we know parallelogram law of addition, we know polygon law of addition. But let's say none of these are given. We are simply given these two vectors, which is what you'll be given in the questions most of the times. In that case, what we can do is we can add their components respectively. So I cap component A1 and B1 will get added, J cap component A2 and B2 will get added, and the components of K cap A3 and B3 will get added. And that's how, with complete ease, with a lot of clarity, you can write the sum of these two vectors, vector A plus vector B, in the component form. So I hope vector addition from all the different aspects is understood by you all, whether it is, vector law, triangle law of addition, polygon law of addition, parallelogram law of addition, and the most important, in the component form, how do you add two vectors? Did you get clarity on this? If this part is understood, let us understand subtraction of vectors as well. How does it happen? Let me try and give you some clarity through triangle law of addition. Let's say we have a vector A. Okay, so I'll take it accordingly the way they are taking. So let's say we have this vector A, which is, let's say, OA. So I'll draw it here so that you get more clarity. So let's say we have this vector A here. Okay, so this is your vector OA. I hope you can see it here. So that's your vector OA. Similarly, you have a vector AB. So let's say this is your vector AB. I hope you are getting it. So if I were to add OA to AB, what will be your response? You will say, sir, by triangle law of addition, this will be vector OA plus AB. There is no confusion on that. I hope you are getting it very clearly. So I hope you are getting this part very clearly, students, that if there you have a vector A, if you have a vector B, so OA plus AB, which is A plus B, will be OB, which is vector A plus vector B. Any confusions on that? I hope triangle law of addition is what you're aware of. But let's say vector B was there in this direction. So if I rotate it by 180 degrees and I take the same magnitude, then will I not get minus B, the vector minus B? I hope you are understanding this phenomena very clearly, that if you have this as, let's say, vector B, this is your vector B. So what I do here is I now take a replica of it, and simply rotate it by 180 degrees. I'm really sorry. I need to undo it. I am simply rotating it by 180 degrees. So if I am, let's say, I have done everything, but none of see. I'm really sorry. So these tools are not for us. I'm simply rotating it. So let's say this is our vector B. So if I'm rotating it by 180 degrees, I hope you can see the rotation over here. Things are sometimes really simple. We complicate them. So this is your vector B, right? But this is not vector B. This is your vector minus B. I hope you're realizing why. Because both of these vectors are equal in magnitude, but this vector and these vector are opposite in direction. If this is going there, it is exactly 180 degree opposite of it. I hope you can see it. So here also, if I had this as vector B, can I not have vector minus B? So I'll simply rotate it by 180 degrees, and that, let's say, after rotating it by 180 degrees, this is your vector minus B. So that's your vector minus B. I hope there is no confusion on it. So vector minus B has same magnitude as vector B, but it is 180 degree rotation of vector B, so that its direction became exactly opposite of vector B. So you have vector A plus vector minus B. I repeat, I am using the triangle law of addition only. So what does triangle law of addition say? The triangle law of addition says that vector A, if I add with vector A, the vector minus B. So this is your vector A, this is your vector minus B. If I'm adding both of them, will I not get vector A minus B? I hope you are understanding it. So this will be vector A minus vector B. So that's your vector law of addition only, but now it is called subtraction of vectors. How? I hope you are realizing it. Now, when somebody asks you to write it in components form, you will say, sir, it is very simple, because in the sign, in place of the addition sign, all I need to do is use the subtraction sign, the minus sign. Because if again we have these two vectors, A vector and B vector, and I'm supposed to subtract B vector from A vector, I'll subtract the corresponding components A1 minus B1, A2 minus B2, and A3 minus B3, and I'll use I cap, J cap, and K cap, and that's how we can write vector A minus vector B. Any confusions on that, students? I hope there is no doubt, there is no confusion. With that, I hope subtraction of vectors is also understood by you all, with this clarity that if I keep the magnitude same and rotate the vector by 180 degrees, I'll have the same vector but with the negative sign. Now, moving ahead, let us talk about subtraction of vector, some properties related to subtraction of vector. This is what is called a triangle inequality. This is what we study when we discuss modulus, that is absolute value function. This is what we study when we talk about complex numbers. I hope you know triangle inequality based questions are there to find maxima of minima z1 plus z2, z1 minus z2, if you are able to recall them. Similarly, this triangle inequality is there in vectors as well. Because what is vector addition or vector subtraction? Triangle law of addition. So if through addition or subtraction of vector, triangles are getting formed, then why can we not use triangle inequality? So there comes triangle inequality. Now what is triangle inequality? Let us start understanding it. Before I could explain triangle inequality to you, can you help me in understanding one fact, that if I am given a triangle, then do we know that sum of any two sides of a triangle will always be greater than the third side? Some of you might have subtly understood what I'm trying to make you understand here. Additionally, what I'm trying to make you understand is, can we also say, or do we also know for a triangle, that difference of any two sides, length of course, is always less than the third side for a triangle? If you know these two facts, then understanding triangle inequality is a very simple, a very easy task for you. I'll try and help you in understanding through this simple illustration. If you get that part, you need not remember this entire result. You just need to remember these two facts. So I'll simply, let's say, I am drawing a triangle here. So let's say we have a triangle over here, somewhat like this. So that's, let's say, a triangle for us, right? Now, if it is a triangle, we know certain things. Let's say if it is a triangle, let's say this side has length A, this side has length B, and this side has length C. We know that. Also, we know that if I'm treating them as vectors, so let's say this is vector A, this is vector B, then this is vector C, which will be equal to vector A plus vector B through triangle law of addition. I hope you know that. Now, what I am trying to make you understand is, let's say I am taking their magnitudes. So yes, we know if this is vector A, what is vector A? This is your vector A. If this is vector B, what is vector B? This is your vector B. And if this is vector C, this is vector C. Then we know that in a sense of vector law of addition, I won't hesitate in saying that vector A plus vector B will be equal to vector C. But this equality is true in a sense of vector law of addition, triangle law of addition. So when A, B, C are treated as vectors, then this is perfectly fine. But let's say if I'm talking about their magnitudes, so this entire scenario gets converted into a scenario of a triangle, let's say, for a while. So in that case, let's say the same triangle is there. Let's say the same triangle is there. In that scenario, I hope you will realize that this distance in a sense of distance, I'm not saying this is a vector now, I'm saying this length of this side can be treated as mod of vector A, because if this was a vector A, this side will have length as mod of vector A. Similarly, this side will have the length as mod of vector B, and this side will have the length as mod of vector C. So these are the lengths we are given as. Now, one thing or two things we know for sure. First thing, in triangle, sum of any two sides, that means length of course, sum of length of any two sides is always greater than the third side. And similarly, the difference of length of any two sides is less than the third side. That is what we know for a triangle as a property. If I use that property, then I can deduce or draw these results. Why? Because if there is a vector if there are two vectors A and B, and if I could create vector A plus B, then this will be the third side of that triangle. I hope you have seen this particular part here, very clearly given here, that vector C is nothing but what? This vector C is nothing but your vector A plus B. Yes. So that's what I'm saying. Then this magnitude of C can also be written as magnitude of vector A plus B. Similarly, through vector law of addition, we have seen subtraction of vectors as well through the same triangle law of addition. So through A plus B, if I could create a triangle with vector A, vector B, and vector A plus B, then I could create a triangle with vector A, vector B, and vector A minus vector B as well. So can I not apply triangle inequality in that? So that's what I'm saying, that if a triangle has two sides, one of the sides is mod of vector A, the second side's length is mod of vector B, then sum of the length of these two sides will be greater than equal to the third side. the triangle inequality. Are you getting sense out of here? Similarly, the difference of the length of two sides, because one of the sides is having length mod A, the other side is having the length mod B. So difference is going to be less than the third side, which is mod of vector A plus vector B. Similarly, not just that, with vector A minus vector B, I can create a triangle. We already have seen this with subtraction of vectors. So there also I can use this triangle inequality. How? See, if a vector has three sides, vector A, vector B and vector A minus B, or vector A, vector minus B and vector A minus B. So mod of vector A plus mod of vector B or mod of vector minus B will be same because in magnitude they are same. So mod of vector A plus mod of vector B, sum of length of two sides in a triangle is greater than the third side because the third side now is vector A minus vector B. So mod of it will be the length of the third side. Similarly, if I say that the difference of the length of two sides, mod of A minus mod of B, will be less than or equal to mod of A minus B because this is the third side. So difference of two sides is less than the third side. Sir, you are saying that this is an inequality. When does it become equality? Well, it happens when all the 3 points are collinear. What I'm trying to make you understand is that instead of triangle, if it becomes a straight line. So if all the 3 points are lying on a straight line, let's say this is what is happening over here. So if I'm given 3 points, let's say this is point A, this is point B, and let's say this is point C. I am denoting this AB as vector A, let's say for a while. I'm denoting this BC as vector B for a while. So if I were to ask you the vector AC, will it not be A plus B? If I were to ask you the vector AC, will it not be A plus B? Triangle law of addition only, but since no triangle is formed, then also triangle law of addition is getting created. So in this case, will I not say if A, B, C are collinear, if A, B, C are collinear, then mod of A plus mod of B will be equal to mod of A plus B because they are collinear. So that inequality becomes an equality if instead of triangle, we are dealing with 3 collinear points. So this is also a test through which you can verify or validate whether 3 points are collinear or not. I hope you are understanding why. So if something like that happens, you will be in a position to conclude that the given points are collinear. Now let us talk about section formula, right students? What is it? We'll discover it now. This formula right here is simply an extension of what you have studied in 2D geometry. I hope you remember if we are given 2 points and there is a third point lying on the line joining those 2 points, and if that third point divides that line joining those 2 points into the ratio m is to n, you had a formula. Either it was an external division or internal division, you had 2 formulae for that. The same formula will get extended here in 3D. So first of all, what you need to understand is that vectors in 3D are simply an extension of 2D geometry. So you will see a lot of things getting related, a lot of formulae getting repeated. So have this thing in mind that you should be able to generate these formulae, which we are going to discuss in vectors in 3D from 2D through your intuition and intelligence. And you can establish a relationship so that remembering the formulae in 3D and vector could become an easy task for you. How? Let's have a look at that part. Let's imagine that we have 2 points A and B and their position vectors are given by vector A and vector B. And there is another point P which is lying on the line AB, the line joining the points AB, and it divides it into the ratio m is to n. Now this ratio could be either external or internal. So I hope you remember this is what I'm saying here very clearly, that let's say we have here origin. So position vector of point A, let's say, is given by vector A, and position vector of point B is, let's say, given by vector B. Now, if I were to ask you that there is a point P lies on the line joining the points AB, and this point P divides the line segment AB into the ratio m is to n. So let's say AP is to PB is given as m is to n. So we have a formula through which we can very easily discover or describe or write the coordinates of P or the position vectors of P. How? The idea is very simple. M goes to this B, N goes to this A divided by M plus N. What I'm trying to make you understand is M times B plus n times a divided by m plus n. This is exactly what you must be able to recall. We have studied in 2D geometry as well. So whenever you study coordinate geometry, the same formula, the same sort of formula is used for internal division, if you remember or recall it. Similarly, there is a formula for external division as well. What is that? Let's say there we have a point A and B. There are 2 points A and B. The position vector of point A are, let's say, given by vector A. The position vector of point B are given by vector B. I hope there is no confusion on it. Now, what we know clearly is that there is a point P lying on the line joining the points A, comma B. But this time, what is special about this point P? That this point P lies externally. So there are two possibilities. Either it could lie on the right of B or it could have lied on the left of A. So let's imagine that in this case, it is lying on the right of B. Now you need to pay a lot of attention in this particular part. Please understand, two things I need to work upon. First, I need to find the distance between A and P, and I need to find the distance between B and P. If not, let's say I'm not able to find the distances between A and P and B and P, then I need to find the ratio of these distances A and P and B and P. So what I need to have here from here is that the ratio of these two distances. Which two distances, students? AP is to BP. So let's say by some calculation, by some data given in the question, if I'm able to work out this ratio, which ratio, students? AP is to BP, and that ratio, the distances, the ratio of those distances is found to be m is to n. If that ratio is found to be m is to n, then also the formula remains very simple. I repeat, how do I remember it? I'll share that method with you. See, what was m? M was the distance of A with P. So m will go with the coordinates of B. M will go with the coordinates of B. I hope this part is very well understood by you all. Similarly, what was n, students? If you had paid attention to n, what was n? N was the distance of point B from P. So n was the distance of this point B from P. So here n will go to the position vector of A. So here the formula now becomes MB, NA and MN. But what about the sign? Previously, when it was internal division, the sign we used was positive. But if it is an external division, the only thing you need to take care of is that the sign which we'll be using will be negative. So I repeat, the formula remains same. If you ever tend to forget what is needed to be, pushed where, you can remember it like this, that see, PA had a distance m. So this m distance, this factor m will go to the vector B, will get multiplied with the vector B. Similarly, n was the distance of point B with P. So this n, the number n will get multiplied to the position vector of A, which is A. Now, just another difference which you need to remember is that whenever it is an internal division, you'll use addition sign here. And if it is an external division, you're supposed to use negative sign here. Nothing else needs to be done or discussed in this particular case. If you follow these instructions, you can always have internal and external division followed very clearly, correctly. I hope you are getting it. Now, if you have understood internal and external division, I hope this part is also very well understood by you all, that let's say there is a line segment. Let's say there is a line segment. And this line segment has points A and B. So point A has, let's say, the position vector small a, and point B has the position vector as a small b. Now, I hope with this concept of internal division, can you not help me with the midpoint here? If I were to ask you the midpoint of this point A and point B, where position vector of point A is given by vector A, position vector of point B is given by vector B, can you help me with this point, which is the midpoint of this line segment joining A and B? I hope you must be very clear that, sir, this distance and this distance must be equal, which means this ratio must be 1:1. And if this ratio is 1:1, everybody knows it very clearly that 1 into B plus 1 into A divided by 1 plus 1, which is nothing but the coordinates of this point, which are given by vector A plus vector B divided by 2. So I hope there is no confusion in it. You have complete clarity on it and you are able to digest and understand this very clearly. Now, let's discuss one more case where I'm assuming that there is a triangle ABC, right? So there is a triangle ABC. It has vertices A, B and C. So the position vector of these vertices A, B and C are given by vector A, vector B and vector C. I hope there is no confusion on it. Now there are certain conclusions which you can draw. I'm writing all these conclusions right there in this one slide only, through which we can learn this relation and understand everything very clearly. Just pay attention. These all formulae have something very similar, very common here. What is that? Please pay attention to this part. Whenever you are asked to find the centroid, whenever you're given a triangle and you are asked to find the centroid, what is the centroid here, students? I hope you know, if I were to talk about the centroid of a triangle, you know it very clearly that when you deal with the triangle and you wish to write its centroid, then its centroid is given by the point of intersection of all the medians. So let's say one of the medians I have drawn from here. Median is basically the line dividing the edge or the side into two equal parts, bisecting it from the vertex you have drawn it. Similarly, there will be another median which I'll be drawing like this, and there will be third median which will be concurrent with these two medians, and it will be passing like this. So the point of intersection of all these three medians is called the centroid. I hope you know this very clearly. So this is going to be the centroid. One more thing you know for sure, that here if this was point A, this was vector B, and this was vector B. So vertex A is denoted by vector A, vertex B is denoted by position vector vector B, and vertex C is given by position vector C. Now I hope you are realizing that since it is a median, it will be bisecting it, and that's why you will get introduce the ratio 1:1. So by applying the internal ratio formula here, you can get this points ratio, let's call it D. Now we know one more thing, that if this point is D, the median gets divided by the centroid into the ratio 2:1. So if I were to ask you AG is to GD, if I were to ask you AG is to GD, you would have said, sir, this ratio is going to be 2:1. Now, if I know D, if I know A, can I not work out G? So by using this calculation, when you find the coordinates of G, it will turn out to be A plus B plus C by 3. I am in a very quick manner discussing the derivation, the formula, along with which I am trying to give you the conclusion as well. Similarly, in the same fashion, you can find the incenter as well. I'll just try and help you with the incenter. What is incenter first of all? So when you talk about the incenter, basically it's nothing but, first of all, you need to understand that, let's say there is a circle, right? There is a circle. Now I'll forget this circle for a while. Let's say there is a triangle. There is a triangle, let's say for a while, let's take it like this. So there is a triangle, and what I do is I have this circle here. Let me just take this circle. This is the triangle, right? Just give me a second, students. I'm not able to select the circle basically. So let me just come back to this part. Okay, coming back to the discussion, let's take a triangle first. Okay, because I was not able to select the object. So there we have a triangle. Again, this triangle has vertices A, B, C. They'll have their own position vectors, small a, small b, and small c. My concern here is, can I take the angle bisectors here? I hope you understand. If I have these three angles, angle A, angle B, and angle C, I'll be having the angle bisectors here. So the angle bisectors are also concurrent. What does it mean? That all the angle bisectors will pass through one single point, and that one single point will be called the incenter of the triangle. I repeat my statement very clearly here, students, that here I'll have the three angle bisectors. First angle bisector, let's say, goes like this. Let's say this is your first angle bisector. There you have the second angle bisector, let's say, and there you have another third angle bisector which goes like this, let's say. So these three angle bisectors, these are what? They are angle bisectors, internal angle bisectors. So with these three internal angle bisectors, we are able to get a point which is the point of intersection of all these three angle bisectors, which is called the incenter. Now, what is the significance of incenter? The beauty here is that this point, this point incenter, this point which is said to be the incenter, is equidistant from all the three sides. What does it mean? It means if I drop a perpendicular from this point to this side, and this side, that distance will be same. What does it mean? It means, students, that if I am able to draw a circle which is centered at this point, and if that circle touches all these three sides, then I'll be able to draw that circle, and these three sides will behave as tangents, and those distances, which distances, students? The perpendicular distance of these three sides from this point will be the inner radius, because that distance was same. So by using geometry, we can do that. So let's say by using geometry, I am able to draw a circle. I am able to draw a circle, let's say for a while, and this circle, let's say, touches this particular triangle like this. I hope we are able to digest this part very clearly. Now, I hope you're realizing that what is special here. The part which is special here is, let me just try and select it. Yes, we are able to. So I will try to show it with this particular here, this part. Now the interesting part here. What you need to understand here is that let's say we have this particular portion here, right? So from this point, if I were to draw a perpendicular, let's say I have drawn a perpendicular here like this. I were to draw a perpendicular like this, let's say here, and I were to draw a perpendicular like this, let's say here. So these are the three perpendicular lines. They have something very special common here. This is the, just give me a second, students. This is the perpendicular distance here. This is the perpendicular distance here, and this is the perpendicular distance here. Now these three perpendicular distances, which I have tried showing you through these pink lines, they are the in radius. They are the in radius. I hope you're getting it. And this point here, which is the center of this circle, is called the in center. So before we could straight away jump upon the conclusion that what is in center and how to find the coordinates of in center, are you able to understand how is in center formed? And what is the significance of an incenter? So incenter basically is the center of a circle which is inscribed in a triangle. So this circle has its own speciality, that this circle will be touching all the three sides of this triangle. Second conclusion here, the very, very important conclusion, that from this center, which is the in center, the perpendicular distances of all the three sides will be equal, and that's the only reason because of which we are able to draw this circle in this particular case. I hope this part is very well understood by you all. Now let's say what I'm given is, I am given the three vertices of this triangle, and I am asked to figure out the coordinates of the in center. Can I do so? The idea is very simple, students. All I need to do is, let's say this is vertex A, which has position vector A. This is vertex B, which has position vector B. This is vertex C, which is defined or given by position vector C. Now, I hope you know, if I were to ask you the distance here, so by using the distance formula, you can find the distance BC. In the same fashion, can you not find the distance AC? Can you not find the distance AB? So once you have figured out the distances AB, BC and CA, by using this formula over here, I hope you can see it very clearly that vertex A had the side BC opposite to it. So with the position vector of vertex A, I'll multiply the length of the side which was opposite to vertex A, which was BC, plus the vertex B had the side AC opposite to it. So with that position vector B, I'll multiply with AC, the length of the side which is opposite to B. Similarly, to vertex C, the side AB was opposite of it, which means I'll multiply AB with this position vector C. And that product sum I'll divide it by AB plus BC plus CA, which means the sum of the length of these sides, or you can call it the perimeter of the triangle as well. So always remember that the coordinates of the in center are given by BC times position vector A plus AC times position vector B plus AB times position vector C divided by AB plus BC plus CA or AC, whatever you wish to call it. Two things I am sure you must be now very clearly aware of. First one is centroid, second one is in center. Now, let us discuss the third formula, which is orthocenter. Orthocenter is again a very straightforward, a very simple phenomena. What now you need to understand is that, let's say if we are dealing with a triangle. So let's say we again have a triangle somewhat like this. And what we do is we drop the altitudes, we drop the perpendiculars. So let's say from each vertex, I have dropped altitude. So first altitude goes like this. I hope you can see it very clearly. That's your first altitude for a while, let's say. The second altitude, let's say, goes like this. And of course, by using this particular concept, I very clearly can conclude that the third altitude must pass from here, from this point. Let me just draw this part again. So it will be passing from this vertex and it will be passing through this particular point. I hope there is no confusion on this particular part. Did you get that part, students, here very clearly? Okay, so yes, this is it. So the point of intersection of all these three altitudes, which is this, is called the orthocenter. I hope there is no confusion on it. You have gotten a great clarity on it. that these three are the altitudes here. So I have drawn the altitudes and the point of intersection of all these altitudes. The altitudes are also concurrent for a triangle. So the way centroid was getting formed from medians, in center was getting formed with the help of angle bisectors. Orthocenter is formed with the help of altitudes. So the point at which all the altitudes are intersecting is called the orthocenter. That can also be worked out. Now the formula is very simple here. See, let's say again we have this thing in mind that this is vertex A. Again, I'm not writing it time and again. Position vector of vertex A is given by A, B is given by small b, and position vector of vertex C is given by, let's say, small c. Of course, what we know is that this angle over here will be angle capital B, this angle here will be capital A, and this angle here will be capital C. So these vertices have angles capital A, capital B, and capital C. So let's say I'm aware of three things: the angles ABC and the position vectors ABC. With the help of these two things, I can very easily work out the orthocenter. The way we worked on in-center, in the same fashion, orthocenter is given, but with a slight difference. The slight difference is to the position vector A, to the position vector A over here, I'll multiply it by 10A. The position vector B gets multiplied with 10B, and the position vector C gets multiplied by 10C. And this sum is divided by 10A plus 10B plus 10C. If you were to apply this formula, you can very easily crack the coordinates of orthocenter, or in vectors language, position vector of orthocenter. The same logic, the same modus operandi will be applied while dealing with 3D geometry as well. So why to complicate it? Why can't we keep it simple in vectors language only? I hope you're realizing it. Now, similarly, there is the fourth concept, which is called the circumcenter. Now, what is circumcenter, students? Again, let's say we have a triangle. We could have drawn it all in one triangle only, but that would have made it amazingly confusing. So let's say we now take a triangle and I draw its perpendicular bisectors. Now I'm taking a combination of median and altitude. So it is neither median nor altitude, but it is something new, which is perpendicular bisector. So what I'm doing here is that on each side, I'm drawing a perpendicular which is bisecting the side. So let's say here I'm drawing a perpendicular like this, which is bisecting the side in this manner. Similarly, let's say I am drawing one more perpendicular bisector, let's say somewhat like this. It goes like this for a while, let's say. And similarly, the third perpendicular bisector, which is bound to pass through this point, let's say, is lying here. So what are they? They are perpendicular bisectors. Now, what does it mean? Perpendicular bisector means they will be perpendicular like this, first of all, and they will be bisecting these edges. So this side will be bisected, this side will be bisected, and this side will also be bisected here. So these three lines are called the perpendicular bisectors. Now, what is special in this case? Well, the special case here is very simple, that the perpendicular bisectors are also concurrent for any triangle, which means they'll also pass through one single point. Now, if they are passing through one single point, then the special thing about this particular point of intersection of all these perpendicular bisectors is this, that here, this point will be equidistant from all the three vertices. What does it mean? It means that distance of this point from this vertex, that distance of this point from this vertex, that distance of this point from this vertex will be same. I repeat, these three distances will be absolutely same. And if these three distances are absolutely same, can I not draw a circle which is centered at this point and which is passing through all the three vertices? So here in this case, we will be able to draw a circle. We will be able to draw a circle which will have this speciality. I'll try and draw it first so that you don't get confused, students. So I'll first of all, yes, I think we are able to draw. Yes, perfect. So coincidentally, I took a circle and it is luckily passing through all the three vertices. Brilliant. We didn't have to put much effort in this case. So my point is very simple here, students, that this point here, which was the point of intersection of all the perpendicular bisectors, was the point which happens to be the center of this circle. Which circle? The circle which is circumscribing this triangle. The circle which is passing through all the three vertices of this triangle. Are you getting this phenomena? So I hope first of all you must be able to understand that which kind of center is attained by which kind of lines. centroid, median, angle bisectors, in center, orthocenter, altitudes, circumcenter, perpendicular bisectors. I hope you are getting a complete clarity on it. Sir, again, if we are given the vertices A, B and C, the position vectors, so small a, small b and small c, can I now relate or work upon the formula for circumcenter? Yes, there is a formula for circumcenter as well. The formula is pretty simple and straightforward. What is it? What you need to understand is, first of all, I hope you must have realized what is circumcenter. Now, the formula for circumcenter is given by sine 2a times vector a, sine 2b times vector b, sine 2c times vector c. I hope you are realizing 2a, 2b, 2c are the double of the angles created or made at the vertex a, b and c. And of course, their sine ratio is taken, should be multiplied with their position vectors a, b and c. And this sum is again divided by sine 2a, sine 2b and sine 2c. If you pay attention to all these formulae, they have a similarity. What was the similarity? In the numerator, you had vector A, vector B, vector C. In the numerator of each formula, you had vector A, vector B and vector C. All you need to understand is that whatever coefficient was there with these vector A, vector B and vector C, that same coefficient sum was there in the denominator. What do I mean by this? Let's say for centroid, the coefficient was 1, 1 and 1. So the denominator had 1 plus 1 plus 1. Now, for in center, if it was BC, AC and AB, so the denominator was AB plus BC plus CA. I hope you're getting it. If in orthocenter, it was 10A, 10B, 10C, so the denominator had 10A plus 10B plus 10C. And if for circumcenter, it was sine 2a, sine 2b and sine 2c, so the denominator had sine 2a plus sine 2b plus sine 2c. So my idea, my suggestion here would be very simple, that can you not remember the coefficients in each case? And through that, you can actually derive the formula each time. How? I'll tell you that for centroid, the coefficient is 1. So you'll say that the formula will be a plus b plus c by 3. For in center, the coefficient is the length of the sides. So here for A it will be BC, for B it will be AC, and for C it will be AB divided by AB plus BC plus CA. For orthocenter, so ortho means right angle means 90 degree, 90 degree means perpendicular and base or something like right angle triangle, which usually happens with 10. So this is how you can relate it, although not a very good logic, but I remember it for the sake of learning it. So this is the technique which I follow. Right. So by having this thing in mind, you can say, sir, this will be 10A, A, vector B times 10B, vector C times 10C upon 10A plus 10B plus 10C. For circumcenter, I hope you're realizing what is circumcenter. For circumcenter, it is sine 2A times vector A, sine 2B times vector B plus sine 2C times vector C divided by sine 2A plus sine 2B plus sine 2C. So what I am trying to give you is that if you just pay attention to this particular part where I'm saying that look at the coefficients, you can develop a technique for remembering this particular formula. Now, let us proceed ahead, and I hope you have gotten a complete clarity on all sorts of these, types of these centers. Now let's look at the question and understand this particular concept more clearly. What does it say? This question was asked by JEE Mains in 2025. Okay, so let's look at the question now. Let the three sides of a triangle ABC are given by a vector this, and this. Brilliant. That is great. So the problem here is that what we have learned in terms of formula is that if we are given the position vectors A, B and C, the problem here is that they are not the position vectors of the vertices A, B and C. Rather, they are the three sides here. I hope you are understanding the difference. Side means the side, the complete vector. Position vector means the position, the point related to origin, then that position vector. So there is a difference, right? Still, there is some scope. Okay. Let us first of all look or pay attention to what we are given. So let's say we are given a triangle. That's great. So we are given a triangle. Okay, cool. So let's say I am given a triangle somewhat like this. Okay, so this is the triangle. Now, let me begin with the first side. What are given? So the first side is 2i minus j plus k. Okay, so let me say that this side here should be 2i minus j plus k, right? So this is your first side. Now, let me take the second side as I minus 3j minus 5k. Now, what I'm trying to tell you is, by using the triangle of addition, can we talk about the third side? I hope you remember. 2 plus 1, 3. Minus 1 minus 3, minus 4. And 1 minus 5, minus 4. So it should be 3i cap minus 4j cap minus 4k cap. Okay. Luckily, is it given as 3i cap minus 4j cap minus 4k cap? Yes, and that was bound to happen, because if it is a triangle and if these two vectors are representing the two sides of this triangle, then the third side should be the to be the vector sum of these two vectors. So this third side is directly there given to us. Now by using the vector law of addition, I hope we can write the third side. In a sense, I hope you're able to understand that if I were to write the third side, I hope you're realizing that 2i minus j plus k plus I minus 3j minus 5k, when these two sides are added, I'll get the third side. I hope the sense of the direction is also very well understood by you all. So this third side will be nothing but 2i plus I, which is 3i, beautifully given. Then minus j minus 3j, which is minus 4j. I hope you can see this also getting related. Similarly, minus 5j plus k is minus 4k. That is also what we are given over here. Sir, what is the advantage of doing all this? Even if you have noticed all this, what are you able to deduct from here? What conclusion can we derive from here? Okay, now let's work on that conclusion, which we are able to derive from here. Since vectors can be treated freely anywhere in the 3D space, I can use this feature of vectors for my convenience. How? Let's say I assume this point A's position vector as the position vector of A as 0 I cap plus 0 k cap plus 0 j cap plus 0 k cap, which means the vertex A I am choosing as origin. I am taking it as origin. Now, what is the advantage of it? Most of you must have noticed that if I am taking vertex A as 0 I cap plus 0 k cap, 0 j cap plus 0 k cap, I can very easily write vertex B. What will be the position vector of vertex B? Vertex B will be position vector of A plus this factor, because to OA, if I add AB, to OA, if I add AB, I'll get OB. I hope you remember this result. So if this is added to A, I'll get the position vectors of B. So let me write the position vectors of B. This will be 0i plus 2i, which will be 2i cap, 0j minus j, which will be minus j, and then of course 0k plus k, which will be plus k. Not this. If you are not able to get all of this, please understand a very simple phenomena. This is your origin, this is B. So from origin, if I move into this direction with this magnitude, I'll get this vector, which will be nothing but what? This minus this, which is what I have gotten. Did you get this part? Through this method also you could have said this. Similarly, let's say this is vertex C. This is vertex C. Can I not define the position vector of vertex C? From origin, I am moving in this direction with this magnitude. Can I not write the position vector C? It will be, I hope you're realizing, this minus this. So it should be 3i cap minus 4j cap minus 4k cap. So, if I was given the three sides of a triangle, by assuming one of the sides, one of the vertices as origin, I could now deduce the other two vertices position vectors. Any confusion so far? I hope you have gotten a great clarity on this part. Now, what is the advantage of doing all this? Now, let's read the question. The question is asking you that G is the centroid of the triangle. Now, if I were to tell you that if G is the centroid of the triangle, what do you know? Sir, it's a very simple result for us, that if there is this point G, which is the centroid of the triangle. Centroid of the triangle is always given by centroid of the triangle. The position vector of the centroid of the triangle is always given by vector A plus vector B plus vector C divided by 3. I hope you must have remembered this result. So can I work on the position vector G here? So centroid of the triangle will be given by 0 plus 2 plus 3, which is 5i cap. So the numerator will have 5i cap. Then 0 minus 1 minus 4. It should be minus 5 j cap. Similarly, 0 plus 1 minus 4. So it should be minus 3k cap. I hope there is no confusion on it. And this sum, this vector A plus vector B plus vector C should be divided by 3. I hope there is no confusion on it. So this is what I have gotten as vector G, which is the centroid. I hope you're getting it very clearly. Now, I need to find out three more things. AG, BG and CG. Basically nothing but the distances AG, BG and CG. So can I now work on finding the distances AG, BG and CG? So what will be AG? I hope you know. Position vector of G minus position vector of A will give me the distance AG. Then magnitude also that is needed to be taken. Similarly, GC can also be worked out. Similarly, BC can also be worked out. So let me begin with GA first. Okay. The best part here is that in order to find GA, I need not put much effort, because whatever the coordinates of G are, if I take the magnitude of it, it will be giving me the distance GA, because A happens to be the origin. So if I simply find the magnitude of this, it will give me GA. Did you get that part? So first of all, let us write the vector GA. Why am I finding the vector GA? Because I need to find the magnitude of AG, right students? So I'm beginning with this vector AG's magnitude, or rather let's say it's a square. So it's a square will be given by vector G minus vector A, which is origin. So I did not subtract it, because 0 when subtracted from anything, this gives me this original vector only. So this 5i minus 5j minus 3k should be divided by 3, and I need to take the square of the magnitude of this, right? I hope I have written the vector correctly. Yes. So I hope this part can be very easily deducted by you, because you know how to take the magnitude of a vector. So first of all, denominator will have this 3. So what you need to understand here is that 5 square by 3 square, 5 square by 3 square, 3 square by 3 square. So everywhere with each term I'll have 3 square in the denominator. So that can be taken out. So 3 square when taken out comes out. I hope you are understanding. What I'll be doing here is that I'll be putting an square root, and there is already a square over it. So that square root and square will get nullified. And that's my point, that I need to put this square root and square here. So that is why they have deliberately given you this square, so that you can simply get rid of that square root sign. So I'll not be writing the square root. I hope you're understanding why. Now, if I were to begin with, it will be 25 by 9. Then it will be again plus 25 by 9. And this will be 9 by 9. So 25 plus 25 plus 9 by 9. So this will be 59 by 9. So that's your AG square. I hope there is no confusion on it. Now let us work on BG square. I hope you're getting it. So what is G? This is G. What is B? We already have it. So if I were to find first of all vector BG, so I need to define the vector BG first, then I'll define its square, right? So here, let me write vector G minus vector B. What was vector G? This was vector G, which was 5i cap minus 5j cap minus 3k cap divided by 3, right? Then minus vector B. Vector B is 2i minus j plus k. So it is 2i minus j plus k, right? And this vector's square, magnitude square is needed to be taken. 2i minus j plus k. Yes. I hope this part can be done by you very easily. How? You will do it the same fashion the way we have done this part, which means what you will do is 3 will be multiplied here, LCM will be taken. So here it will be minus 5i cap. So I think we had 5i cap minus 5i cap. That will leave us with 0i cap. Okay. Then what about the j? There you had minus 5j cap. This is minus 3j cap plus 3j cap, because minus minus plus. So it should be minus 5 plus 3, which is minus 2j. Just correct me if I'm wrong. So I hope we are going great. 3, I'm really sorry. I added it. I'm really sorry. With I cap, I don't know how did I commit this mistake. I'm really sorry for this. So 2 into 3 is minus 6. So 5 I cap minus 6 I cap, I'm really sorry, should be minus I cap, right? Let us move to the next part. Here, this is 5j cap and this is plus 3j cap. I hope you're getting it very clearly. So minus 5 plus 3 should be minus 2j cap. Similarly, the next part will be minus 3 minus 3k. So minus 3, which will be minus 6k cap divided by 3. Now again, here also I'll be using the same formula. What is the same formula? I can find the magnitudes square like this, the same way we have done it. Now, if I found, once I figure out BG square, can I not find the CG square? I hope for CG square also you'll use the same result, which I'm writing here, because now I'm hoping and expecting that you can solve it by yourself further, because all you need to do is, we have AG square. From here, we can evaluate BG square. From this part, we can evaluate CG square. And once you have evaluated AG square plus BG square plus CG square, that sum needs to be multiplied by 6. And through that, you will get the answer. So I'll write CG as well, the vector CG. So vector CG will be vector G minus vector C. So what was vector G? Vector G is 5i cap minus 5j cap minus 3k cap whole divided by 3 minus, what about vector C? Vector C we have already worked as 3, 4, 4. So 3 minus 4 minus 4. So it should be 3i cap minus 4j cap minus 4k cap. So that's your vector C. So vector G minus vector C, its magnitude is needed to be taken and then its square is needed to be done. So two things I'm leaving up to you. One of them is BG square, which you need to evaluate by yourself. Then CG square, which also you can evaluate by yourself. Once you have found BG square and CG square, you will get a value somewhat like this. You add all these three values and then you multiply them by 6 and that will be the answer. So the remaining portion of this question, I'm asking or leaving up to you that you should do it by yourself, because it is left with a little amount of calculation only. My concern was to make you understand that whenever such question arises, how do you write the position vectors of the vertices A, B and C, and then how do you find the centroid, and once you have found the centroid, how do you write vector AG, vector GB and vector CG, or vice versa, and then the square of their magnitudes. How do you find that? Through one demonstration I have depicted it. For the other two, you can follow the same step and get the results. So I hope you are getting the complete clarity. It is simply a matter of calculation now. But my concern here is that, did you get this part? Did you understand the whole approach? Did you understand how to deal with questions based on centroid and all? I hope it has made a lot of sense. And let's move to the next part. From here, basically, when I go ahead with the next part, I hope this part is very well understood by you all. Now let us discuss that. Let's say if I'm discussing or keeping two vectors in picture, and we are supposed to find their resultant vector, specifically its magnitude and its direction. How do we work on it? Technically, this particular result you discuss in a very clearer manner in physics. You deal with this concept a lot in physics. But of course, since we are discussing vectors in mathematics, we'll have clarity on this topic in mathematics as well. But I hope you know it very clearly that this is something you discuss in physics as well. That same part I'll be explaining from my perspective. Okay, now have a look at this particular result. What do we have here? First of all, you need to understand this particular thing, that we have two vectors. Let's say vector P here and another vector, let's say vector Q. So these are the two vectors. Okay, now they have their tail at the same point. Let's call it O or whatever you wish to call it. And vector P and vector Q, if they are acting as forces, let's say for a while, on an object, let's say the resultant vector takes it here. So let's say there is this resultant vector which passes like this and it goes like this. So I hope you know parallelogram law of addition is very much applicable here, and through that I can define this vector R very easily. Now I hope you know that parallel to vector P, if I could draw a vector here which is parallel and similar and equal to vector P, because this vector and this vector has the same direction. Not just that, they are equal in magnitude. Similarly, here by using vector law of addition, what do I mean by vector law of addition here, students? By vector law of addition, I'm trying to say that this vector plus this vector will be equal to this vector. Triangle law of addition. So parallelogram law of addition with triangle law of addition can give me this result. So the conclusion remains very simple. We had this vector P, we had this vector Q, and the resultant vector R is this vector R, which can be completed as a diagonal here by creating this parallelogram. I hope there is no confusion on this particular part. We are very much clear on this. Now, what you need to understand is that there is one more thing. Can I say this thing very clearly, that the resultant vector R is the addition of vector P and vector Q. So this is something we all can draw or deduce. Now, by using the dot product or by using the simple concept that, let's say if I take modulus on both sides, So I hope if in terms of magnitudes, can I not say if vector R is the sum of vector P and vector Q, then magnitude of vector R will be equal to magnitude of vector P and vector Q. Vector P plus vector Q. Did you get this particular part? Now, if I square both these sides, so what we have attained here is, what we have gotten as a result here is that, I'm writing this particular part here, vector R we know is given as vector P plus vector Q. Now, if I take magnitudes on both the sides, of course, if two vectors are same, their magnitudes and direction will also be same. So, I have taken their magnitudes on both sides. So what do I have here is, if I square both the sides, so what will I get from here? I'll be getting square of magnitude of vector R, and here on the left hand side, I'll be getting square of sum of magnitude of sum of vector P and Q. Now, I hope you know, from here, if I expand this result, I'll get P dot P. What will be P dot P? It will be vector P square or mod P square. So here I'll get Q dot Q, vector Q dot vector Q. That will be mod of vector Q square. This is what we'll discuss when we are discussing the dot product. So don't worry about that. Then I'll get, as per A plus B whole square identity, I'll get 2 times P dot Q. Now 2 times P dot Q, 2 times P dot Q, I hope you're realizing, will give me 2 times mod P into mod Q into cos theta. And what is theta here, students? I hope there is no doubt or hesitation here that theta is the angle between vector P and vector Q. So basically I'm bringing dot product into picture. So square of magnitude of vector R can be written as P square plus Q square plus 2PQ cos theta. What are P and Q? P and Q are the magnitudes of vector P and vector Q. So with that, if I were to define the resultant vector R, its magnitude, it will be under root over P square plus Q square plus 2PQ cos theta. So that's the result number 1, which you are supposed to memorize. This is something which you should have in your mind, which you should have at your fingertips. Another result which you should carry with you is the second thing, that let's say this is the resultant vector R, right? This was your vector Q and this was your vector P. Now, if I am asked that what is the angle of this resultant vector R with this vector P, let's say that angle is alpha. So alpha is the angle which this resultant vector R is making with vector P for a while. Now, if I take it to a next level, what I know here is, please pay attention to this particular part. We know that if this vector was Q, this vector will also be Q. Do you all agree with this? Now, let's call this point O, this point let's say A, and this point here B. Right. Now, can you help me with OP, students? I hope there is no confusion on it. Rather, OP, you all must be able to understand in terms of distance. OP will be basically magnitude of vector P. Do you all agree with this on me? Now, with me on this. Now, second part is PB. What about vector PB? We all know, since OPBQ is a parallelogram, which means OQ and PB are same, they are equal vectors. So if OQ has the length mod Q, will you not say that PB will also have the same length mod Q? So PB will also have the same length mod Q. Now, if PB has the same length mod Q, what will you say about PA? What will you say about the length PA? Will you not say that this length PA is mod Q cos theta? So I'll say that this length PA is nothing but mod Q cos theta. Everyone with me so far? Similarly, can you help me with the length AB? I hope you're realizing in this triangle PAB, the length AB will be given by mod Q sin theta. So this is the going to be mod Q sin theta. Now, I am asking you to look into this particular triangle. Which triangle, students? I am asking you to look into the triangle OBA. So in the triangle OBA, we all know that this is a 90-degree angle. And if this is a 90-degree angle, can you help me with this angle alpha? Can you not say that this angle alpha, which I'm writing as tan alpha, will be given by perpendicular upon base? What is perpendicular? AB. What is base? OA. So tan alpha I'm writing as AB upon what? OA. I hope there is no confusion on it, that AB will remain AB, but can I not write OA is OP plus PA. So OA I'm writing as OP plus PA. Now, what is AB, students? AB, as we have already discussed, AB, as we have already discussed, is Q sine theta. I hope you are getting it very clearly. And what about OA? OA, as we have discussed, is OP plus PA. What is OP? OP is magnitude of vector P, and PA is Q cos theta. So if you are asked the angle between the resultant vector and this vector P, which let's say is given here as alpha, then tan alpha is given by this formula. Why did I discuss this derivation? Because I wanted you to have this clarity that how did we derive it. That logical approach should be there in your mind, because in mathematics you don't deal with a lot of formulae, rather you deal with approaches, you deal with more intelligence, you deal with more logical mindset. So you should know how did we get something, because that conceptual clarity will be tested in this examination. They may not very much be interested in the part where you are asked to remember or memorize these formulae. Rather, they will more be interested in how well versed are you with these concepts intellectually or logically. How actually you get or understand these concepts. That understanding, that comprehension, they're trying to assess through these different concepts. So your conceptual applicability plays more crucial role in deciding your JEE score as far as mathematics section is considered. Remember that. Remember that. Now, let us move ahead. Let us go ahead with the next conclusion. Here, if this part is understood, next part will be getting more clarity about. So going ahead, we now look at some more understandings. This is what we have understood, that the internal bisector of the angle between any two vectors is along the vector sum of the corresponding unit vectors. Now this line is not just a line which I'm asking you to read. This line has its own meaning, its own sense. What is that? Please understand. Let's say I'm given two vectors. Let's say I'm given two vectors. There are two vectors. Let's say one of the vectors is this. This is just a vector we are dealing with, and the other vector is this. So these are the two vectors I'm dealing with, right? Now let's say I am asked to write the angle bisector. For a while, to be more specific, internal angle bisector. Can I find the internal angle bisector? The internal angle bisector is a very interesting phenomena here. Let's say this particular vector here is denoted by, let's say, vector A, and this particular vector is denoted by vector B. Now, let me take a unit vector from vector A and a unit vector from vector B. Why am I doing so? Please have a look at that. So let's say if I have taken a unit vector from this vector A, let's say that unit vector is here given by this. Let's say this is that unit vector which I am taking from vector A. This is that unit vector. Similarly, another unit vector I'm taking from vector B. Okay. Any confusions on that part? I hope there is no confusion on it. Now, from this vector B, I take another equal vector and draw it somewhere here. Similarly, from this unit vector A, let's say I'm not able to draw it, so I'll draw it like this. I take another vector A, which is basically equal to this unit vector A. I repeat this part if you are not able to get more clearly. This vector is unit vector A. This vector is unit vector B. So parallel to unit vector A, I have drawn a vector A here. Parallel to unit vector B, I have drawn a vector B here. So I hope you are getting it more clearly. This is a rhombus. To be more specific, this is a rhombus. Instead of calling it a parallelogram, I'll be more specifically calling it a rhombus. Now, what is the advantage of it? The advantage is very simple. The advantage is very straightforward. If you are noticing that if this vector and this vector are same, then if I were to draw a diagonal of this particular rhombus, let's say if I were to draw a diagonal of this particular rhombus, let's say I'm drawing the diagonal of this particular rhombus, let's say this. Now, of course, diagonal will be limited to here, this position only, but I'm extending it here. So what I am trying to make you understand is pay attention to this diagonal of this rhombus. Which rhombus? The rhombus which had the unit vectors vector A and vector B. So there was vector A, there was vector B. I took unit vectors A and B and I created a rhombus, I completed a rhombus, and then I took a vector along in the direction of the diagonal of this unit vector A and vector B is created rhombus. So from this rhombus, I am taking this particular diagonal. Now, why did I do all this? Let me read this line for you all, then I'll come back to this part that why did I do all this. But I'm sure most of you must have realized what have I done here. If you know the basics of geometry. See, the internal angle bisector between any two vectors is along the vector sum of the corresponding unit vectors. What I'm trying to make you understand is, will you not agree that if this is vector A, this is vector B, this is vector A cap and this is vector B cap, this distance here so far up till here from this point to this point, this is A cap plus B cap, and I have taken a vector which is in the direction of A cap plus B cap, which will have its own magnitude. So magnitude, let's say I'm not aware of, but can I not write it as, I'm really sorry, can I not write it as lambda times A cap plus B cap? So up to this length, this was A cap plus B cap, but it can have its own magnitude depending on the requirement of the question, which we don't know so far. So I'm putting a lambda here, which will help us in deciding its magnitude, but it becomes lambda times A cap plus B cap. Now, if you all are paying attention to this derivation here, what I'm trying to make you understand very clearly here is that for a rhombus, this angle and this angle are equal. If this angle and this angle are equal, are you not realizing I am able to draw the angle bisector of vector A and vector B? So whenever you are asked to write the internal angle bisector of vector A and vector B, what I'll do is I'll simply take A cap and B cap and I'll take their vector sum. So along with the vector sum of A cap and B cap, the internal angle bisector will lie. It can have its own magnitude, and that magnitude will get decided with the help of lambda, which will be able to work out with the help of more data given in the question. My concern here was to simply make you understand that are you able to digest this particular concept when we are trying to learn the concept of internal angle bisector. In the same fashion, you can understand the concept of external angle bisector. I'll directly straight away explain it in this manner. For example, here, let's say we have a vector A like this, we have a vector B like this. So the internal angle bisector, as we have already discussed, is given by mu times vector A cap plus vector B cap, mu lambda, whatever it can be, scalar quantity basically to decide its magnitude. Similarly, if I were to find the external angle bisector, so external angle bisector, for external angle bisector, opposite to vector A, exact 180-degree opposite to vector A, I'll have vector minus A. So, or rather opposite to vector B, I can have a vector minus B. So if I take the difference of the unit vectors A and B, which is A minus B, will I not have this vector? Which is nothing but what? Which is the external angle bisector of vector A and vector B. I hope you realize and understand this particular concept, that whenever you deal with two straight lines for a while, let's say, so there are two straight lines, this straight line and there is another straight line. So these two straight lines will have two angle bisectors. So one of the angle bisectors could be the acute angle bisector and the other angle bisector could be the obtuse angle bisector. So in the same fashion, this same phenomena I'm trying to make you understand here in this context, that one of the angle bisectors will be internal angle bisector and the other one will be external angle bisector. My point is that internal angle bisector will lie along with the vector sum of the unit vectors A and B, and the external angle bisector will lie along with the unit vector difference of vector A and vector B. Did you get that part? Is there any confusion on this? I hope you are getting this, how to find the internal and external bisectors of two vectors by using this particular concept. Now, moving ahead, let's see, or let's get more clarity on few more concepts. Here, there comes the most interesting, the most important, the most crucial concept: linear combination of vectors. Linearly dependent, linearly independent, collinearity, coplanarity, all of this will be understood here in this part. And if you are able to digest this particular portion of this video, which we are going to discuss now, then you'll have an excellent amount of clarity on what is linear combination of vectors, how to write it, what is the application of it, how to use it, what can you interpret if such kind of information is given in the question. All of that I'll be discussing in this particular part of the video. So here, the request is pretty simple. Pay very much attention to this part because we'll be talking about linear combinations, linearly dependent vectors, linearly independent vectors. What is the significance and meaning of it? What do you understand by collinearity? What do you understand by coplanarity? All of that will be discussed here. So this is again a very crucial portion from which questions are formed, questions are framed. Questions very subtly use this particular concept. So pay a lot of attention here in this part. Look at this part very clearly. I'll begin with this part that let's say if there is this vector r and I can call it a linear combination of vectors a, b and c if there exist some scalars x, y and z such that r can be written as x times a plus y times b plus z times c and all. So first of all, I'm trying to make you understand what do I mean by linear combination. Linear combination means that vector r is a linear combination of, let's say, vector a, b and c. How and when? If there are certain scalars, let's say x, y and z, so I could write vector r as a sum of xa plus yb plus zc and like that. So if I'm able to write vector r as a sum of a, b, c with some scalars, of course, then I'll say that vector r is a linear combination of vectors a, b and c. For example, let's say in 3D, we have a vector r1 which is given by 2a plus b plus 3c. So vector r1 is a linear combination of a, b and c. I hope you're getting it. Similarly, if let's say I'm able to write vector r2 as a plus 3b plus 2c. So here vector r2 is a linear combination of a, b and c. First of all, did you all understand the term linear combination? And if you have understood the term linear combination, I'll move ahead with further next part. What is that? Now, let's say I wish to establish a relationship between two collinear or parallel vectors. So let's say I wish to claim that there are two vectors which are either collinear or parallel. So I hope you realize and understand it very clearly that if two vectors are either collinear or parallel, they will be denoting the same direction. Their directions will be same. I hope you are getting this part. So if their directions are same, I can relate this part here. As you all can see very clearly, the point is very simple that if two vectors are parallel or collinears, then I can write the first vector as a linear combination of the other vector. Why? Because they are collinear, they are parallel, because their directions are same. So what I'm trying to make you understand is that let's say there are two vectors a and b which are collinear, right? And x cap be the unit vector in the direction of vector A or vector B or vice versa. Basically, it will be both. Why? Because if I were to write a vector A, I'll be writing vector A as magnitude of vector A into its direction, of its direction. Similarly, vector B will be magnitude of vector B times its direction. Now, its direction can be either plus x cap or minus x cap if they are collinear, if they are in the opposite direction. So I hope you're realizing they have their x cap same, their x cap common, their x cap same for both of vector A and vector B. What does it mean? It means whether vector A or vector B, they both have this x cap, which means either vector B can be written as a linear combination of vector A or vector A can be written as a linear combination of vector B. The point remains very simple that if they are like or unlike or collinear or parallel vectors, then always remember that if two vectors are linear or parallel, then I will be able to write them as the linear combination of each other. In a very simple language, if I were to conclude it, what I'm trying to make you understand it, that A could be either lambda times vector B because A and B have the same direction, or even if opposite, that will be decided by lambda by being negative. So here what you need to understand is if they are collinear or they are like or unlike, which means basically parallel, in that case A will be lambda B. So A can be written as a linear combination of B or B can be written as a linear combination of A. In a better language, in a more clearer language, I can also write it as that if vector A and vector B are collinear or parallel or like or unlike, then vector A and vector B can be written like this. A linear combination of vector A and vector B will be 0 because vector A will be something scalar into vector B or vector A will be equal to something scalar into vector B, which means I can finally conclude that linear combination of vector A and vector B, the xa plus yb should be 0 where x and y are non-zero. I hope you're realizing it. Why? How did we conclude it? That is of course important. How did we derive it? That is definitely crucial. But what you must realize and understand in this particular case is that if you have two vectors which are either collinear or parallel or like or unlike, in that case, you should be able to conclude that I should be able to write them in this format of linear combinations such as xa plus yb is equal to 0, where these scalars x and y should be non-zero. Why? Because of this conclusion, which we know that if two vectors are parallel or like or unlike or coplanar, then this holds true. So from this phenomena, we can write this. First learning, first conclusion, are you able to digest this? From linear combination, I am able to draw a combination, a result, a deduction. Then proceeding ahead, we'll keep drawing some more conclusions like that. Another conclusion. Let's say first conclusion here is that there are two vectors A and B. They are of course two non-zero vectors. Non-zero vectors, mind you, every single detail I'm mentioning is very crucial. And they are non-collinear vectors. What does it mean? They are non-collinear vectors. It means if vector A is like this, vector B could be like this. So they are simply two non-collinear vectors. It means that if there are two scalar quantities x and y, and if somebody claims that he or she is able to write it as xa plus yb is equal to 0, then this will be possible only if x and y both are 0. I repeat my statement. First conclusion, A and B are non-zero. Second conclusion, vector A and vector B are non-collinear. And still despite all this, vector A and vector B non-zero, vector A and vector B are non-collinear, and still if somebody claims that if xa plus yb is 0, then it is not possible. It is possible only when x and y are 0. So you need to understand three cases getting right from here, that if xa plus yb is equal to 0, if xa plus yb is equal to 0, then there are three possibilities. First possibility, vector A and vector B will be 0. The job is done. If vector A and vector B are 0 vectors, they are point vectors, then of course vector, this linear combination xa plus yb will be 0. No matter what value of x and y you put, for any scalar, xa plus yb will be 0. So if this is so, this will be there. The second conclusion, that x or y will be 0. As we have already discussed, if A and B are non-zero and vector A and vector B are non-collinear, then if this is said, then this will be true only when x and y are 0. The third conclusion, which you should understand, which we have discussed in the beginning here, that if vector A and vector B are parallel vectors, which means they could be either collinear or like vector or unlike vector, in that case, they can be written as a linear combination of other, which means I can write xa plus yb as 0, where x and y are non-zero. Do you remember that? I hope you are able to deduce all these three conclusions from this, and you are getting a very good clarity in your brain about vectors, their linear combinations, and how will you be able to relate them. Any confusion so far? Now, proceeding ahead, let's take more clarity on this particular result. If I am saying that A and B are two non-collinear vectors, and I am told that linear combination of A and B is written in terms of x1 and y1. So there are two scalars x1 and y1, and there is another linear combination x2a plus y2b, and that is same. So this x1a plus y1b is equal to x2a plus y2b if it is told, if it is given, and I am told that here these two vectors A and B are two non-collinear vectors. Still I'm able to write their linear combination. First of all, we already know if A and B are two non-zero vectors, and if I am able to write it like this, so can I simply shift it on the left hand side and write it like this, that from here, if I were to conclude, if I take x2 there, so I'll have x1 minus x2 times whole of vector A plus y1 minus y2 times whole of vector B, and it is equal to 0. And as we already know that we are told that vector A and vector B are two non-zero vectors. Vector A and vector B are two non-collinear vectors. In that case, if you are still able to write them as their linear combination, then it will be possible only the coefficients, the scalar terms are 0. So if the scalar terms are 0, that means you are concluding that first scalar term is x1 minus x2, it should be 0. And the second scalar term is y2 minus y1, that is 0. And x1 minus x2 or y2 minus y1 is 0. That helps us in concluding that x1 and x2 should be equal and y1 and y2 should be equal. So I hope you are realizing that all what conclusions which we are drawing are being understood by you all by having this clarity in mind that how are we writing the linear combinations of vectors. Depending on them being collinear or being non-collinear, the scalars, all what is being decided on these parameters, how are we concluding all that? Any confusion so far? Now, if I go ahead with the next conclusion, have a look at that. Some important conclusions you should have in your mind. First, let's say I'm given 3 points A, B and C, and if I'm told that they are collinear, my first conclusion will be this, that AB should be equal to lambda BC. I repeat my statement. If there are 3 points, right? So if we have 3 points in the space, so let's say if we have 3 points in the space, let's say this is point A, this is point B, and this is point C. And let's say I'm told that these points are collinear. What does it mean? So I'll be able to write vector A, then I'll be able to write vector BC. And of course, BC and AB or AC, any pair of two you take, then this, any pair AB, BC or AC, then these two pair, any two you take out of these three, they will be collinear. And if they are collinear, which means they'll be their linear combination can be written like xa plus yb is equal to 0, where x and y are non-zero. Or in a different language, I can say that AB should be equal to lambda BC. So whenever two vectors are parallel or like or unlike or basically collinear, then this is what you should have in your mind. I hope no confusion on that. Now, proceeding ahead, another conclusion. Another conclusion says that if 3 points with position vectors A, B and C are collinear, so there are 3 points which are having their position vectors, so small a, small b and small c, and they are collinear, then this will be possible only when xa plus yb plus zc is equal to 0, where x, y, z, the scalar quantities, not all are 0, and x plus y plus z should be 0. The proof is pretty simple. The proof is straightforward. Let's say if x plus y plus z is equal to 0, can I say, I'm really sorry, I'll take this pen here. Can I say x plus y will be equal to minus z? So from here, if I keep xa plus yb here on the left hand side, and if I take zc on the other side, then I can write zc like this with the negative sign, of course. And here, if I bring this minus z here in the denominator, I'll have xa plus yb upon minus z is equal to vector c, and minus z can be replaced by x plus y. That's exactly what I'm trying to make you understand, that vector c is such a vector which is dividing the line joining vector A and vector B in the ratio y is to x. I hope you can see it very clearly. So if vector C is dividing the line joining vector A and vector B in the ratio y is to x, what does it mean? It means vector A, vector B and vector C are collinear. So that is the conclusion you should be able to understand. The derivation and the fact both are equally important. I hope you will remember this also as a fact. The fact is pretty simple. If there are 3 points A, B, C, their position vectors are small a, small b and small c, then there should be 3 scalars, not all of them should be 0, x, y and z, such that xa plus yb plus zc should be 0. And along with this, you should have this thing in mind that x plus y plus z should be 0. Did you all get that part? I hope you are able to understand what we are trying to understand here through collinearity of certain number of vectors or points. Similarly, let's say in a better language, instead of this, if I wish to use this, now what does this result say? This result says that if there are 3 vectors, vector A, vector B and vector C, they are the position vectors of 3 points. And I am asked to verify or validate whether they are forming a vector, basically a collinear vector as well, collinear or not. So whether these 3 points are collinear or not, this is what I need to assess. Point is very simple. You take A1, B1, C1, B2, Here it should have been A2. So let me just write that correct part here. It should have been A2, B2, C2 and 1, 1, 1. And if this determinant is found to be 0, then we say that these three vectors in 2D space are collinear. If some of you could see it a little differently, I would have said that, sir, these are nothing but 3 points. See, in 2D we know 2, 3, 4, 5 and 7, 9. Let's say these are 3 points in 2D. And if I were to ask you to find the area of the triangle, you could use either stair method or this formula. Do you remember that half of mod of this will be giving us the area of the triangle formed by these 3 points in 2D? Do you remember it? We have discussed it in determinants. So if I could prove that x1, y1, x2, y2, x3, y3 along with this 1, 1, 1, if this determinant is found to be 0, these 3 points will be collinear. That's exactly what we discuss in 2D is written in vectors. But of course, I cap and j cap, two components are taken only. So I hope you're understanding this is still in 2D and that's how you can prove it. So you have two methods. Either you use this vector method, which is nothing but actually an extension of what you discuss in either coordinate geometry or determinants. Are you getting some clarity on it? Now, moving ahead, let us discuss some more properties here. Let's talk about coplanarity now. How do you deal with them? See, let's say there are two vectors, vector A and vector B. They are again non-zero, they are again non-collinear. But let's say now I'm entering into 3D space. So far I was still restricting myself to 2D. Now we'll be discussing something related to 3D where I'll be bringing vectors into a plane. So far we were discussing things related to in the frame of 2D. So collinearity was there. But now when you get into 3D, coplanarity comes into picture. What is it? Let's say there is this vector R, which is coplanar with vector A and vector B. So you should always remember that vector R, which is coplanar with vector A and vector B, can always be expressed as a linear combination of vector A and vector B. The idea is very simple here, students. Let's say there is this plane, right? This is the plane. And in this plane, you have two vectors which are non-collinear. Let's say this is vector A and this is vector B, let's say for a while. I hope there is no confusion on it. This is your vector A and this is your vector B. Now, let's say there is another vector R which is lying in the same plane as this vector. There is another vector R. It is lying in the same plane in which the vector A and vector B are lying. So what they are trying to make you understand is that vector R can always be written as a linear combination of these two vectors which are coplanar to the vector R. That's what I'm trying to make you understand. Did you get clarity here? And I hope you're understanding x and y are scalars, simply scalars. That's it. I hope first thing on coplanarity is understood by you all. There is no confusion on it. Now, moving ahead, let's get more clarity on this particular portion. Have a look at this part. Three vectors, let's say A, B, and C, are coplanar if any one of them is a linear combination of the remaining two. That's exactly what we have discussed. So let's say if vector A, vector B, and vector C lie in the same plane. So as per the theorem on coplanarity, we know that vector A can be written as a linear combination of vector B and C. So that's what I'm trying to make you understand here. If I am given three vectors and I need to check whether they are coplanar or not. So if any vector of among these three can be written as a linear combination of other two, then I'll unhesitatingly say that these three vectors are coplanar. I hope the concept which we started with was linear combination. And after collinearity, we have come to coplanarity. Now, I hope you're able to understand the conclusions we are drawing based on the theorems which we are understanding. So the concept remains very simple. What is it, students? That if I'm able to write vector A as a linear combinations of vector B and vector C, then I'll say that vector A will lie in the same plane as vector B and C are lying, which means vector A, vector B, and vector C must be coplanar. Any confusions on that? Moving ahead, the next theorem, extension of what we have discussed previously. Let's say this is something very important. Remember it. This is what we will use at a lot of places. IIT JEE loves it. They ask questions on it. They ask a lot of questions on it. So straight questions without any modifications are asked. The statement which I'm writing here, that same statement will be given in the question. A variable will be given and you will be asked the value of the variable. And this only you need to do and you will get the answer. Students remember this fact, this approach, and then they don't get the answers very quickly. The modus operandi, the standard operating procedure for such questions is what I'm going to tell you now. So pay attention to this part. The part is very simple. Let's say I am given three vectors. Let's say 3 points I'm given with position vectors, vector A, vector B, and vector C. And if I wish to check whether these 3 points with their position vectors as vector A, vector B, and vector C, which are written in the form of I cap, J cap, K cap, are coplanar or not, whether they are lying in the same plane or not, then the check is pretty simple, students, here, that you take this determinant of their coefficients of I cap, J cap, K cap. So A1, A2, A3, B1, B2, B3, C1, C2, C3. If this determinant turns out to be 0, you can say that these three vectors are coplanar. Did you get that part? This is a simple check, a simple litmus test you need to apply here, through which you can always apply this validation whether three vectors are coplanar or not. Will you remember this as a result? I think I need not repeat it, but you should have this result in your mind. This is exactly what we'll be using in scalar triple product, box of three vectors. Then also I'll bring this coplanarity under discussion. That's when also I'll tell you to recall this particular formula. So at this stage only I'm saying this, that have this thing in your mind. Keep this with you. Questions are asked straightforward, straight questions are asked. Data is given and you need to apply the determinant and find the value. Nothing else is needed to be done. But what happens with the students is that they forget this particular simple, straightforward concept, and that's the problem. So I hope you'll remember it and you can apply it and you will get the answers very quickly. Now, once you have understood this particular part, let's keep discussing. A lot of results are based on the linear combinations of vectors. What are they? Keep learning, stay focused, stay alert, and keep noting everything down. How? Here. So if I were to prove that 4 points are there, which I am asked to prove that they are coplanar. So let's say there is a plane. Let's say there is this plane, and this plane there are 4 points. So let's say in this plane there are 4 points. Now which are those 4 points? Let's say this is point A, right? This is point B. This is point C, let's say, and this is point D. What do I mean by point A, point B, point C, point C? So small a, small b, small c, small d vector are the position vectors of these points A, B, and C. A, B, C, D. So this is point A, this is point B, this is point C, right? And this is point D. So let's say if I were to give you the position vectors, can you not write the vector AB, AC, and AD? I hope you can, right? So if I were to ask you to write vector AB, what will you say? You would say that, sir, vector AB will be this. This will be your vector AB. I hope there is no hesitation on that. And how to write vector AB? It will be vector B minus vector A. That is very easy task for us. How can you write vector AC? That again is a very easy task for you. Position vector of C minus position vector of A. Can you write vector AD? Yes, you can write vector AD will be position vector of D minus position vector of A. Again, are you not able to deduct that, sir, I have gotten 3 vectors, AB, AD, and AC. If I were to check whether these 3 vectors are coplanar or not, so I think I have a method for it. And if I have a method to check whether AB, AC, and AD are coplanar or not, then I think if I could verify it, then I will be able to claim that these 4 points, A, B, C, D, would be coplanar. So modus operandi was very simple. I was given 4 points. I created 3 vectors out of those 4 points. I hope you are understanding how. And now with 3 vectors, I think I have the method to check whether these 3 vectors are coplanar or not by using the linear combination. So if I could do that, I think I can conclude whether these 3 vectors are coplanar or not. And if these 3 vectors are coplanar, then the 4 points through which these 3 vectors are formed must also be coplanar. Did you understand the approach? If you are able to understand this approach, let me just make you understand this particular part, that with the 4 points A, B, C, D, I could create, let's say, 3 vectors A, B, AC, and AD, and we know how to check whether A, B, AC, and AD are coplanar or not, as we have already discussed previously, if you could recall or recollect it. Now, There is another conclusion which is the extension of what we have already discussed. Let's say we are asked to verify that there are 4 points A, B, C and D. This is point D basically, it is not there. So this is vector D here. There should have been some space here. So these are the 4 points here, A, B, C and D, and they are coplanar. So again, there comes a very simple concept. If there are 4 scalars, x, y, z, and let's say u, not all of them are 0, such that xa plus yb plus zc plus ud is equal to 0, where x plus y plus z plus u should be 0. I hope you could recall it, as we have already discussed this in collinearity, a sense of 2D. So in 2D, we had 3 vectors A, B, C. I needed to check whether A, B, C are collinear or not. What we did was, if I'm able to write A, B, C as XA plus YB plus ZC is equal to 0, where X plus Y plus Z was 0, where not all of them were 0, I could state that all 3 of them ABC, vectors ABC were collinear. In the same fashion, that same formula is extended in 3D in terms of, in a sense of coplanarity. What does it mean? So if I'm having 4 vectors A, B, C, D, and if I wish to check whether they are coplanar or not, so if their linear combination XA plus YB plus ZC plus UD turns out to be 0, where X plus Y plus Z plus U is 0, where none all of them X, Y, Z, U are 0, then I can always say that vector A, B, C, D are coplanar vectors. I hope all what is being told is understood by you all, because any of these properties can be used in any question. So pay a lot of attention in this particular part of this video, because we are having a very intensive discussion on collinearity and coplanarity. I hope you're getting it very clearly. Now, moving ahead, getting more clarity on this particular part, let us learn some more things here. Let's say again, if I have 3 vectors, vector A, vector B and vector C, and they are of course non-zero, non-coplanar vectors, and x, y, z are 3 scalars, then if I am able to write xa plus yb plus zc is equal to 0, this should be possible only when x, y, z all are 0. I hope you can relate this also with what we have discussed there. Let's say if I was given 2 vectors A and B and they were non-collinear, and still if somebody said that xa plus yb is 0, then I would say that x and y will be 0. In the same fashion, xa plus yb plus zc will be 0 only if abc are 0 or abc are coplanar. But here I'm clearly told that ABC are known coplanar vectors, so they are non-coplanar vectors. So here I'm very clearly told that they are non-coplanar, non-zero, which means none of them ABC is 0. So even not ABC are not 0, nor they are coplanar. Then how can I have XA plus YB plus ZC to be 0? We already know it. So if this is 0, this is still 0, then this will be possible only when X, Y and Z become 0, because only then 0 plus 0 plus 0 will be 0. Did you get that part? Are you getting complete clarity on this portion here? I hope there is no confusion on it. Moving ahead, the next result. If vector A, vector B and vector C are non-coplanar vectors, then any vector R can be uniquely expressed as a linear combination xa plus yb plus zc, where x, y, z being scalar. Now, this is the foundation of 3D. This is how I will now bring 3D into picture with this simple line. With all what we have studied so far, this can be concluded here, and that's exactly is laying the foundation for 3D or for expressing a vector in 3D. Let's reread it. Let me read this part. Any vector in space can be expressed as a linear combination of 3 non-coplanar vectors. That's exactly what I'm trying to make you understand. If still you're not able to understand it, I'll try to demonstrate it. Let's say there are 3 vectors. Let's say there are 3 vectors, any 3 non-coplanar vectors, right? So these are the, let's say, 3 vectors I'm dealing with. What you must understand is that these 3 are non-coplanar. Although this is what I'm writing or drawing on a board, which is a 2D plane space. So here it is tough for me to make you understand it that this is a 3D space. But what I'm trying to make you understand is that they are the 3 vectors which are non-coplanar. So pairwise, 2 of them could be coplanar, but all three of them are non-coplanar, which means not all 3 of these vectors are lying in the same plane. I hope you're getting this part. Now, if this is a vector here, this is a vector here, let's say A vector, this is a vector here, B vector, and this is a vector here, C vector. And I know that vector A, B, and vector C are non-coplanar. Did you get that part? So vector A, B, C are non-coplanar vectors. And if there is a third vector, let's say vector R. So if there is a third vector, let's say vector R. So any vector in 3D space can be written as a linear combination of three non-coplanar vectors. What I am trying to make you understand is that vector R can be written as XA plus YB plus ZC. That is what I am constantly trying to make you understand through this particular theorem, which lays the foundation of 3D or vectors in a more clearer format. How? Because if I could now introduce 3D space, let's say these are the three vectors which we are dealing with. Let's say this is one of the vectors. Let me just change the color here so that it stays visible to you all. So we keep it white here. Again, let's say this is the other vector, the second vector. Okay, and this is the third vector. Let's say, why did I select it? Okay, so the third vector I'm choosing like this. I hope these are the three vectors. And let's say I'm denoting them as, this I'm choosing as, let's say I cap, this is j cap, and this is k cap. So these are the three vectors, three unit vectors in 3D space, and I know none of two of them could be coplanar, but not all three of them are coplanar. This is what I have taken along the x-axis. This is what I have taken along the y-axis. This is what I have taken along the z-axis. So all three of them are non-coplanar. So let's say if there is a third vector, somewhat like this, this is what I'm writing in 3D space. So let's say if there is a third vector, vector r, then it can be written as a linear combination of these three non-coplanar vectors. That's exactly what I'm trying to make you understand. And that is exactly what I'm trying to conclude with this particular result here. I hope you are able to deduce or digest all what is said so far. Now, moving ahead with this conclusion in mind, let us learn what do I mean by vectors being linearly dependent and linearly independent. This is an extension of collinearity and coplanarity. Have a look at this particular part. Here, let's begin with this conclusion here. Let's say there are some vectors a1, a2, a3 up till an. And I am able to write these vectors a1, x1 times a1 plus x2 times a2 and so on. And all of this is 0. All of this is 0. When x1, x2, x3 up till xn are 0. I hope you are able to digest or deduct what I'm trying to say here. If this is not understood by you all, let me take an example, what we have already discussed or studied so far. Let's say there are three vectors. Let's say there are three vectors A, B, and C, right? There are three vectors A, B, and C. And I'm able to write A, B, and C's linear combination. Let's say XA plus YB plus ZC is equal to 0 plus ZC is equal to 0. And. Now there are two possibilities. Three possibilities actually. Either vector A, vector B, vector C will be 0. So this possibility I'm discarding. I'm not discussing this particular property or this possibility. So I'm left with two possibilities now. Which two possibilities? First possibility, either vector A, vector B, and vector C will be coplanar. In that case, I'll say that yes, it is possible. Or the second possibility, vector A, vector B, and vector C will be non-coplanar. So if vector A, vector B, and vector C are non-coplanar, that is possible only. That means this linear combination cannot be written. You cannot write it like this. But still, if you are able to write it like this, that's possible only when x, y, z all are 0. So from here, two possibilities arise. Which two possibilities? If xa plus yb plus zc is equal to 0, you will have either x plus y plus z0, where not all of them are 0, or you will have all three of them, x, y, and z are 0. I hope you remember both of the conclusions we have drawn. If x plus y plus z is equal to 0, then we say that vector A, vector B, and vector C are coplanar. But if x, y, z all are 0, then we say that these three vectors are non-coplanar. So here, basically, this particular case is your case of vectors being linearly independent. Did you get that part? I hope from here you're able to deduce that if this particular case was the case of vectors being linearly independent, can you not deduce what will be the case when vectors are going to be linearly dependent? So I hope you are understanding. If the vectors are non-coplanar, basically, then we say that they are linearly independent. I hope you are getting it. But if the vectors are coplanar, I hope you remember this is the case when the vectors are either collinear or coplanar depending on the number of vectors we are dealing with. So here in that case, vectors will be linearly dependent. I hope you are understanding linear combination of vectors through which linearly dependent and linearly independent. So linearly independent because they are non-coplanar, linearly dependent because they are coplanar. That's exactly what I'm trying to make you understand. So if you have understood linear combination, then you must have understood when do we have vectors to be coplanar, when do we have vectors to be non-coplanar, and from those branches only you can draw a very good conclusion on vectors being linearly independent and linearly dependent. The same thought can be, extended here, which we have already learned. So if the vectors are linearly dependent, which means I will have this particular portion over here becoming 0, where not all of them will be 0. I hope you are getting this particular part, which is basically getting extended from the concept of vectors being coplanar. Do you remember that? A linear combination, right? So here, from here, if I go ahead here, now look at this particular part. I hope there is no confusion on this particular part. Whatever I have said so far, there is no doubt or query or concerns here. This particular part which says that this is the case of linearly independent and this is the case of vectors being linearly dependent. I hope no confusions on that. Now, moving ahead, linearly dependent I hope is very well understood by you all. Going ahead with the next part where we'll be discussing scalar or dot product of two vectors. So far, if I was restricting my discussion limited to algebra of factors, which was the most important topic of this particular chapter, from which maximum number of questions are asked, then this is the second most important. Of course, after this, we'll discuss STP and VTP, scalar triple product and vector triple product. But before that, the dot product or cross product, basically product of two vectors, which is classified into two categories. This second concept is the second most important concept from this particular chapter, vectors. All the questions, if they are not using the concepts of algebra of factors, then they'll be using the concepts of product of factors. And this is extended as STP or VTP, which of course we'll discuss later. But this is the part from where the second most number of questions are asked by JEE Mains. How, what is it, what are the concepts, what are the illustrations, what are the previous year's questions, everything we'll discuss. But I hope you're understanding this is the part where again you need to have a good clarity, because a lot of questions are asked from this particular part, product of two vectors, which is classified into two categories, scalar, which is dot, or vector, which is cross. Of course, we'll discuss that, but let us first of all focus on scalar product. So let's say we have two vectors, vector A and vector B. These are the two vectors. And if I'm taking their dot product, it has its own meaning geometrically, mathematically. We'll discuss all those meanings, of course. Don't worry about that. But first of all, let us understand what is scalar product or dot product. So if I'm taking the dot product of vector A and vector B, if I'm taking the dot product of vector A and vector B, it is written as vector A dot vector B, and it is simply given by mod A mod B cos theta. Now what is cos theta here? Cos theta is cos ratio of the angle between vector A and vector B. I hope you are getting it very clearly. Along with this, what you also need to understand here is that mod A and mod B are nothing but what? Moduli of vector A and vector B. That is all we know, that it is the magnitude of vector A and vector B. But what about the cos theta? We have already discussed. Theta is the angle here between vector A and vector B, and accordingly we have cos theta. Now, this theta will always range between 0 and pi. I hope you are understanding it. Why? I hope you have complete clarity on it, because vector A and vector B will have an angle lying between 0 and pi. I hope you are getting this part also very clearly. Whenever angle is between 0 to pi by 2, cos theta will be positive. If the angle is between pi by 2 to pi, cos theta will be negative. What I'm trying to make you understand is A dot B, vector A dot vector B. Vector A dot vector B will be either positive or negative, depending on the angle. So if vector A and vector B have this angle which is acute, which is less than 90, then their dot product will be positive. Or if vector A and vector B have their angle acute, obtuse between them. So vector A and vector B are somewhat placed like this. Let me just try and draw it to you so that you have more clarity on it. Let's say this is vector A and this is vector B. So if this is A and this is B. So I hope you all can see it very clearly that the angle between vector A and vector B is more than 90, which is an obtuse angle. So cos theta will be negative, and in that case, I'll get the dot product to be negative. So if theta is acute, the dot product will be positive. If theta is obtuse, the dot product will be negative. What about theta being 90? Shall I tell you, if the theta is 90, cos 90 will be 0, which means that dot product will be 0. I hope you are understanding it. What I am not saying is, please don't interpret that. I have not said that if the dot product is 0, then the vectors will be perpendicular. No, I did not say this. Please don't interpret it like this. If the dot product of two vectors is given 0, then you cannot always conclude there that then they will be perpendicular definitely. No, they are not surely perpendicular. Why are you not considering if vector A is 0, then also A dot B could be 0. If vector B is 0, then also A dot B could be 0. So that's where you need to understand that if A dot B is 0, then it is not necessarily true that they'll be perpendicular. But opposite of it is true, which means if vector A and vector B are perpendicular, which means theta becomes 90 and cos 90 is 0. Did you get that part? So keep these things in mind, the minute details, and these are the nuances where students commit the error. They don't take care of such small details, and when you tend to forget such small details, that's where you commit errors, and that's the advantage they take. I hope you are understanding my point. Now, I hope the conclusions which we have drawn so far can be summarized with this particular slide. First of all, as we have already discussed, A dot B is a scalar product, which means you'll get a scalar quantity. So when you take the dot product of two vectors, it won't be a vector quantity, it will be a scalar quantity. Of course, it has to be a real numbers. A dot B will be negative. A dot B will be negative if the angle between them, I think, yes. First of all, let's understand this, that A dot B will always be, I'll talk about the second point first, then I'll come to the third and fourth. Third and fourth we have already discussed. A dot B will always be less than equal to mod A times mod B. Why? Because cos theta lies between -1 and 1. If cos theta lies between -1 and 1, that means A dot B. What is A dot B? Let me just try and give you more clarity through this. What is A dot B, students? We know that A dot B is mod A, mod B, cos theta. So what I'm trying to make you understand is cos theta will lie between -1 to 1. So A dot B, which is mod A mod B cos theta, will lie between minus of mod A mod B to plus of mod A mod B, which is definitely less than mod A mod B. I hope you're getting it very clearly. So here, that's the second conclusion, that A dot B will always be less than or equal to mod A mod B. When will it be equal to mod A mod B? When the theta becomes 0. Because if theta is 0, cos theta will be 1. And if cos theta is 1, it will be mod A mod B. Otherwise, the cos theta is always less than 1 and it lies between -1 and 1. So if you are multiplying mod A mod B by any value between -1 and 1, then it will be less than mod A mod B. I hope you are getting it very clearly. The second conclusion and the third and fourth conclusion we have already discussed. Don't worry about that. And yes, the dot product of a zero and non-zero vector is a scalar 0. So that's where you need to understand, if the dot product is 0, it is not necessarily true that the two vectors will be perpendicular. But the opposite, when I say if the two vectors are perpendicular, then we can conclude that their dot product will be 0. Will you remember that conclusion, your students? Now, I'll try and make you understand the geometrical interpretation of the scalar product of two vectors. So here, it's again a very simple phenomena. When I say, first of all, let us read this line, then I'll explain it geometrically, logically as well. So if I'm taking scalar product of two vectors, so this is said to be the product of modulus of either vector and the projection of other in its direction. Now, what does it mean? Let's start working on that. we'll come to this conclusion. But let us begin with this part. Let's say I'm working on A dot B, right? So vector A dot vector B. What does it mean? It is going to be a scalar quantity. But to us, what is it? Sir, it is mod A, mod B, cos theta, right? This is mod A, mod B, cos theta. Now, if I were to draw these two vectors somewhat like this, let's say this is vector A, this is vector B for a while, and this is the angle between these two vectors, let's say theta, right? So this is, let's say, vector A, and this is here vector B. If, let's say, I drop a perpendicular from vector A to vector B. So from vector A, I have dropped a perpendicular here. So can you help me with this particular distance over here? What do you understand by it? Sir, since this angle is a 90-degree angle, and if this is theta, so this distance, which is the hypotenuse of this right angle triangle, is mod A. So this distance, which is the base, which should be nothing but what? Mod A cos theta. Did you get this part particularly, students? So what I'm trying to make you understand is a very important conclusion, that here, if I club mod A in cos theta, can I not write A dot B as modulus of B times mod A cos theta? And what is mod A cos theta here, students? Can you help me with that? All of you must be saying, sir, mod A cos theta is nothing but projection of vector A on vector B. So here, if I write it in a more simpler language, will I not say that A dot B is equal to mod B times projection of vector A on vector B? By this conclusion, will I not be able to draw what is projection of A on B? So what is projection of A on B, students? Can you help me with that? I hope you all would say that, sir, if somebody is asking you projection of A on B, then I can very easily write it should be A dot B upon mod B. I hope you are understanding it very clearly. It should always be written as A dot B upon mod B. Will you remember this as the result? Will you always have this thing in your mind that it is always A dot B upon B? That's a conclusion which I will always emphasize, that you should have this thing in mind, that projection of A on B means A dot B upon mod B. So that's the geometrical meaning of dot product. So with the help of dot product, we can actually work upon projection of a vector on another vector. Any confusions on that? Now, with that, let us proceed further. This is exactly what I was trying to conclude here. Now, let us get more clarity on the angle between two vectors. Now, if I am asked to take the dot product of two vectors in component forms, I hope you know how to do it. So let's say I have two vectors here. Let us say I have two vectors here. Let's say the vectors are, let's say one of the vectors is A, which is, let's say, A1 I cap plus A2 J cap plus A3 K cap. I hope there is no confusion on it. Similarly, there is another vector, let's say B, and that vector is given by, let's say, given by B1 I cap plus B2 J cap plus B3 K cap. So these are the three vectors, right, students? So we have, these are the two vectors. Now, can I find their dot product? So the dot product of two vectors in component forms is very simple. If I'm asked to find A dot B, you basically multiply their corresponding I cap, J cap and K cap components, because I dot J, I dot K will be 0. So other components will become 0 because they are perpendicular mutually, which means I will be multiplied with I, J will be multiplied with J, the component of K cap will be multiplied with the component of K cap. And because the angle between I cap and I cap, the angle between J cap and J cap, and the angle between K cap and K cap is 0, which means this will be cos 0, which will be 1. So the final product is going to be, A dot B is going to be, I hope you can conclude it, A1 B1 plus A2 B2 plus A3 B3. I hope there is no confusion on it. So let's say if I'm given two vectors and I'm asked to find out the angle between these two vectors. So from here, what we already know is, that A dot B is mod A mod B cos theta. So what will be the value of cos theta? There is just typing error. Let me just make this correction here. Give me a second, students. So I'll remove this cos theta from here. and I'll put an equal sign here. So cos theta will be what? Cos theta will be A dot B upon mod A mod B. So that's exactly what I'm saying, that theta will be cos inverse of A dot B, which is A1 B1, A2 B2, A3 B3, sum of these three, divided by mod A. Mod A is what? Under root over A1 square, A2 square, A3 square, plus mod B, which is under root over B1 square, plus B2 square, plus B3 square. That's exactly what I'm trying to make you understand here, is that you have found A dot B. You can find mod A mod B. So if A dot B is divided by mod A mod B, will you not get the angle or cosine of the angle between vector A and vector B? So I hope this concept is also making complete sense, that how are we working on getting the angle between two vectors. Now, there is another conclusion or some more important properties which you should have in mind from the concept of, from the perspective of ITJ mains and advanced, that let's say if we have two vectors A and B, we have two vectors A and B. So here, mod of A plus B square will be nothing but mod of A plus B into mod of A plus B, which is A dot A plus B dot B plus 2 times A dot B. So here A dot A is going to be mod A square, B dot B is going to be mod B square, and 2 times A dot B can be written as 2 times mod A mod B cos theta, or 2 times A dot B. Similarly, if I'm working on square of mod of A minus B, it should be mod A square plus mod B square minus 2 times A dot B. I hope there is no confusion on it. Similarly, when you are taking the dot product of sum and difference of two vectors, which is A plus B times A minus B, it is always written as mod A square minus mod B square, because A dot B and minus A dot B will get cancelled. So that's why I'll be left with mod A square minus mod B square. Any confusions on these three conclusions? I hope you will remember these things in your mind. Now, moving ahead, some more conclusions. Remember it. Please understand, whenever you have this triangle inequality getting converted into triangle equality, I hope you have remembered this discussion. We had a discussion on vector law of addition, after which we had a discussion on triangle inequality, and that's where I have told you that it becomes an equality when the points are collinear. So that's exactly what I'm saying, that A and B, if they are parallel, if A and B are parallel, then whether you add their individual mods or you add them up and then you take the mod, it is going to be same. Similarly, if A is perpendicular on B, let me get back to this conclusion here. If A is perpendicular on B, then we know that A dot B will be 0. And if A dot B is 0, will I not say that square of mod of A plus B will be equal to mod A square plus mod B square, because A dot B will become 0, if A and B are perpendicular. Same, in the same manner, I can say that if A dot B has become 0, here also this will become 0. So if this and this are becoming 0, I have mod A square plus mod B square, on the right hand side of both the rules A and B, formula A and B, which means their left hand side should also become equal. So if vector A and vector B are equal, then square of mod of A plus B and square of mod of A minus B are equal, which means mod of A plus B and mod of A minus B must be equal. So there are some important conclusions we are able to draw. First conclusion, if A and B are parallel, or rather opposite, if mod of A plus B is equal to mod of A plus mod of B, then I can conclude that vector A and vector B are parallel. Then I can conclude vector A and vector B are parallel. If square of mod of A plus B is equal to square of mod of A plus square of mod of B, then I will say that vector A and vector B are perpendicular, because A dot B has become 0. Similarly, if mod of A plus B and mod of A minus B are equal, then also I will conclude that A and B are perpendicular. Did you understand these conclusions? The same conclusions can be brought here based on the simple idea that A dot B becomes 0 if A and B are perpendicular. And all of this can be brought from that only. Trust me, questions are asked based on these properties. So these are not just some simple properties I'm asking you to look at, but rather in questions, they may give you this kind of a result. And then you're supposed to bring some deductions through your intelligence. Let's say in a question, this is what I'm given. So I should have this thing in mind, that if this is what I'm given, then this could be the possible meaning of that inference which I'm told or given in that question. Let's say in a question I'm given this data, that there exist two vectors, vector A and vector B, such that mod of A plus B is equal to mod A minus B, which are of course non-zero vectors. So I should have this thing in mind, that this will be possible only when vector A and vector B are perpendicular. So instead of following the whole approach, following the entire set of rules or steps, instead of doing all those steps again, if I could remember this as a result, I can directly apply it and get the answer. What you have is two choices. If this is given, you start solving it and then you deduce that A is perpendicular to B. But if it is already told you in this lecture, and if you could take it down and if you could remember it, then in the real examination hall, you need not waste time on bringing this result again or concluding this result or deducing it if you have this result with you. So these are certain crucial results which are time and again repeatedly used by JEE Mains in its questions, and that's why I'm writing them right there in front of you and very strongly urging you all to remember them, to mug them up, to memorize them, because if these results are learned here at this stage, they'll end up saving a lot of time in the examination hall, and that's exactly our motive is. We want to save as much time as we can so that we can solve more and more questions. That's our motive, right? Now, and that's the strategy. When somebody says, I want to enhance my speed, so you cannot just all of a sudden start solving questions. Speed comes from conceptual understanding. So the better clarity of concepts you have, the better speed you have. I hope you're getting this. So to have a better speed, better clarity on of the nuances you should have. So more concepts in what greater detail you know, that is the criteria through which you can be increasing your speed. You will be increasing your speed. I hope there's no confusion on it. Now, moving ahead towards the next set of concepts, rather concept, let us finally now deal with a question. What is it? What does it say? Let us have clarity on everything. So it says that A and B are two vectors of the same magnitude. Okay, that's the interesting part. So A and B are two vectors which are of the same magnitude. So by reading this line, can I conclude that mod A will be equal to mod B? I hope that can be said, such that this is equal to root 2 plus 1. Now you have two choices. Either you multiply it on the right hand side and then you conclude something, or rather you use componendo and dividendo. And I will request that componendo and dividendo will save a lot of time. What does componendo and dividendo mean? First of all, you should understand. Let's say to keep things very clear, to keep things very simple, let's say I am assuming mod A plus B as, let's say, for a while x. I hope I need not use x anywhere else. And let's say mod A minus B I'm treating as y. So what am I given in the question? The question is pretty simple for us now, because I am given x plus y in the numerator. This is what I'm given in the question, and x minus y in the denominator, and it is told to be root 2 plus 1. So can I write it as root 2 plus 1 divided by 1? Now what does componendo and dividendo say? Componendo and dividendo says that if you have this x plus y upon x minus y, you can do cross multiplication and get the result. That is perfectly acceptable method. But if you don't want to use it, you can use another result. What is it? In the numerator, you add the denominator first, and from the numerator, you subtract the denominator in the denominator. What does it mean? 2x plus y, I'll add x minus y. So when x plus y, if I add it with x minus y, this is what I can write in the numerator. Now, from the numerator, which was x plus y, I'm subtracting the denominator, which is x minus y, which will become minus x plus y. This is called componendo and dividendo. But if it is being done on the left hand side, the same should be reciprocated on the right hand side. So the numerator is root 2 plus 1, denominator is 1. So to root 2 plus 1, I'll add 1 in the numerator, and from root 2 plus 1, I'll subtract 1 in the denominator. So it will become root 2 plus 1 minus 1. I hope there is no confusion on it. Although you should not write all this, you should have your own intuition that it will become 2x, it will become 2y, and it will become basically root 2 plus 2, and it will become root 2. That you should be able to write right after this step. This is what I have written deliberately to make you understand the process of component dividendo. That was my intent or motive. But I hope you're understanding. This is how you can save time. This is what you need not write. Now, when I solve it further, what do I get? I hope I have the next step with me, right there in front of me. X plus x is going to be 2x, and y plus y is going to be 2y. So 2x upon 2y, 2x upon 2y will leave me with x upon y, will leave me with x upon y. And what will I have on the right hand side? I'll have root 2 plus 2 upon root 2. So root 2 plus 2 upon root 2. So root 2 plus 2 upon root 2. From here, if I divide this right hand side by root 2, it should be 1 plus root 2 or root 2 plus 1. And x and y are mod a plus b upon mod a minus b. So here, x I'm writing as mod a plus b. Y I'm replacing by mod a minus b. Of course, they are vectors, but let us not write them time and again. And there I have root 2 plus 1. So this is root 2 plus 1. I hope there is no confusion on whatever we have explored so far. Now, let us work on what we are asked. So this is what we are asked. I think I'll be able to work it out. It is not going to be a difficult task. But given, based on what is given to me, can I bring more conclusions into the picture? I think I can. So let us try and bring those conclusions. So if I start working on those conclusions, what would those be? See, I will take you back to this particular result which we have discussed so far here. These two results, do you remember these two results? I hope you must have remembered. Mod of a plus b when squared gives you this, and mod of a minus b when squared gives you this, which is very easy for us to learn and remember. So that's exactly what I'll try and use here in this particular question. How? If I square both these sides, so here I'll have mod of a plus b being squared divided by mod of a minus b being squared, and here it will be square of root 2 plus 1, which will be square of root 2, which is 2, square of 1 is 1, plus 2 root 2. I hope there is no confusion on this particular front. Now, when I proceed this particular part further, the left hand side, a plus b, mod of a plus b square is mod a square plus mod b square plus 2 times a dot b. Let us keep this with us. And here I'll be having the denominator will be mod a square plus mod b square minus 2 times a dot b. Not just that, but on the right hand side, it will be 3 plus 2 root 2. Right, students? I hope there is no confusion on it. Now, one more conclusion I can draw, because what I know is that the vector A and vector B were same in magnitude. So I can replace vector mod of B by mod of A. So it will be mod A square plus mod A square, which will give me 2 times mod A square. Are you getting it very clearly? Were you able to anticipate this? So here it will be 2 times mod A square minus 2 times A dot B, right? Similarly, in the denominator also, I'll have 2 times mod A square. Sometimes I may forget to write this vector sign. I hope you will understand and digest why. And here it will be, sorry, the numerator will have plus, it should be minus, right? And it should be 3 plus 2 root 2. Okay, so we have 3 plus 2 root 2 right there. Now, the next thing which I could very clearly do is that I could take this 2 and this 2 common. So when you take this 2 and this 2 common, I think we are left with one more conclusion, which is nothing but what? Which is nothing but what? Mod A square plus A dot B upon what is there in the denominator, mod A square minus A dot B. Any confusions on that so far, students? Is equal to 3 plus 2 root 2 divided by 1. Now again you have two choices. Either you do the cross multiplication and simplify, or rather I can see some similarity here, and then I'd again be tempted to use the method componendo and dividendo, which is more efficient. Trust me, in a longer run you'll realize that this is more efficient, using componendo and dividendo instead of cross multiplication, especially when you are seeing such kind of a pattern. So if I could use componendo and dividendo, I think we have the result here. If I could use componendo and dividendo, I will directly use it now. So to the numerator, I'm adding the denominator. So mod A square plus mod A square will be 2 times mod A square. This will get cancelled. So the numerator will be 2 times mod A square. The denominator will be numerator minus denominator. So this minus this. So mod A square is cancelled. A dot B plus A dot B, which is 2 times A dot B. What do we have on the right hand side? It is 3 plus 2 root 2 by 1. So plus 1 I'll do in the numerator. So it will become 4 plus 2 root 2. I hope there is no confusion on it. And in the denominator, from 3 plus 2 root 2, I'll subtract 1, which will be 2 plus 2 root 2. So this will give me 2 plus 2 root 2. Now, even if I simplify this further, I think I'll get a better result, which will be 2 is getting cancelled by this 2. So I am left with mod A square divided by A dot B there. And on the right hand side, I'm left with, if I take 2 common, I'll be left with 2 plus root 2 in the numerator, 2 plus root 2, right? I'll write it first. So if I have taken 2 common, what am I left with? 2 plus root 2. So I'm writing 2 plus root 2 in the numerator. And if I have taken 2, I should have, okay, I'll do it in the next step so that you don't get confused. If I'm taking 2 common from the denominator, it will be 1 plus root 2. What I'm suggesting you all to do is that take root 2 common from the numerator. If you are taking root 2 common from the numerator, can I do it here only? So if I take root 2 common from the numerator, it will be 1 and this will be root 2. So if I'm taking root 2 common from the numerator, this will make it 1 plus root 2. So 1 plus root 2, 1 plus root 2 is getting cancelled. So this result is nothing but root 2 here. Now, this is something which is very crucial or beneficial for us. Why? Look at this particular result. Look at this particular result, or keep this result in mind. Let us go back to the question. What was the question? The question was finding this. The question was finding this. So let us work on finding what we were asked. Then we'll use what we know so far. So let us work on this result. Mod a plus b square upon mod a square. Okay. So we now are dealing with mod of, I often forget this particular part where I need to change these, features. So mod a plus b whole square upon mod a square. Okay. So I think this is an easy task because you know how to expand it. We have discussed a lot of formulae now. So you can directly apply and get the result. What is that? Have a look at this. Mod a plus b whole square will be, I hope you know, mod a square plus mod b square plus 2 times a dot b. I hope there is no confusion on it. Divided by mod a square. You already have. Now, mod a square mod b square will be 2 times mod a square. So that I'll be writing as 2 times mod a square plus 2 times a dot b divided by mod a square. Now, if I take this 2 common and if I divide both these sides by mod a square, this will be 2a square by a square. That will be 2. So I'm taking that 2 common and here I'm left with 1 basically. I hope there is no confusion on it. And here I'm left with a dot b upon mod a square. So here I'm left with a dot b upon mod a square. Did you all get that part? I hope there is no confusion on this particular front where I'm writing it as 2 times of this. Now, let us get back to what we have already deduced. A dot b upon mod a square. If I were to find the value of a dot b upon mod a square, will I not say it will be reciprocal of this, which is 1 by root 2. So that's exactly what we needed. I hope you can see a dot b upon mod a square, a dot b upon mod a square is 1 by root 2. So that value, a dot b upon mod a square, if I could use here, that will be 1 by root 2. So I think I have gotten the answer. It should be 2 times 1 plus, this is 1 by root 2, and that's your final answer. If it is not given, you can simplify this. This will be root 2 plus 1. So in the numerator, it will be root 2 plus 1. In the denominator, it will be root 2. But here again, you have this 2. So when this 2 is cancelled by this root 2, it becomes root 2. So it is root 2 plus 1 into basically root 2, which again, when simplified further, leaves you with root 2 plus 2. And I think such option should be given somewhere. In the option C, it is given. And that's your correct answer. Any confusions on that? Any confusion on that? Tell me by writing in the comment box how many of you were able to deduce it. How many of you were able to get this? A very straightforward result it was. A very good, interesting question it was. Used a lot of concepts. We had discussed a lot of things here. Let us move towards scalar product in terms of components, as we have already discussed it. I think I need not explain this particular part. We already have had a discussion on this, right? And if you have learned that part, let us focus on another question on this dot product where this kind of data is given to us, right? So let us read it first. What are we all told? That there is a vector A which is I cap plus 2j cap plus k cap. All right, so there is this vector A. And there is this vector which is B. So there is a typing error here. It should have been B. So there is another vector. This is vector B over here. Mind you, students, this is not vector A. This is vector B. Right. Then what are we told next? The next thing we are told is that let C cap be a unit vector. So I hope you're realizing there is a third vector which is C cap. Now, in the plane of the vectors A and B. So vector A and vector B are lying in a plane, and in that plane vector C cap lies. Okay. And C cap is perpendicular to vector A. Okay, that's brilliant. So vector C is perpendicular to vector A. Then such a vector C is. Okay. So instead of finding C cap, let us find the vector C first. Once I find the vector C, once I'm able to find the vector C, I can very easily find this vector C cap. Right. Now let's work on finding out the vector C. How do we do that? What do we know? We know very clearly that vector C lies in the plane of vector A and vector B. Now, we have already discussed that if vector C happens to lie in the plane of vector A and vector B, can I not write C as a linear combination of vector A and vector B? I hope you must have remembered it. So let's say vector C is x times vector A plus y times vector b. I hope that can be said and very clearly be written here. There is no confusion on it. Now, what are we told next? That this vector c is perpendicular to vector a. Okay. So, can I not say, if I am told that vector c is perpendicular to vector a, that means its dot product with vector a will be 0. I hope you are able to understand it. So if vector c is perpendicular to vector a, if I take its dot product with vector a, it will be x times a dot a plus y times a dot b. I hope there is no confusion on it. Now, once you start working on this, what result do you get? Let's have a look at that. So a dot c, I don't know nothing about a dot c. All I know is that a and c are perpendicular. That means it can be concluded that their dot product will be 0. So here this will be 0. What do we have here? X times a dot a. A dot a will be mod a square. So this is x times mod a square plus y times a dot b. I think I am able to find a dot b. How? Because we know how to multiply vectors in the component form. So a dot b, right? So this will be I to I, which will be 2. Then I'll have 2 and then 1. That will again be 2. And then I have 1 and then minus 1. That will give me minus 1 from here. I hope there is no confusion on it. Now, when you proceed ahead, what do you get here is that this a square. So mod a square I need to find. I hope that's a very simple task. 2 square is 4, 1 square is 1, 1 square is 1. So 4 plus 1 plus 1, 6. That is under root 6. So mod a is under root 6. So when you square it, it should be 6. So 0 is equal to 6x and that should be 4 minus 1. That I think is 3. So that is 3y. From here, if I try and find or work upon x upon y, what result do I get? I think if I take 6x on the left hand side, I'll be having 6x is equal to minus 3y. And from here, if I try working on x upon y, it will be minus 1 by 2. So that's a result. Let us keep it with us. So x upon y, we have received as minus 1 upon 2. Now, what is the advantage here of having it? I have cracked the ratio of x and y. So we know that x is to y is minus 1 is to 2. Now with that, can I not say, let's say if x is, let's say if x is k. So can you not work out y? I hope you're realizing if x is k, from here only I could have said that y is nothing but what? Minus 2x. So if x is assumed to be k, y is going to be minus 2x, which is going to be minus 2k. I hope there is no confusion on it. Now, sir, what is the advantage of having this? Please understand, now I am able to crack vector c with this logic because vector c was xa plus yb. What is x? Sir, x is k. So, vector c now will be, vector c can be said to be xa. What is the xa, students? That should be ka. So, this should be ka plus yb. What is yb? Yb is minus 2k. So, that is minus 2k, right? So this is minus 2kb. I hope there is no confusion on it. All you need to do is take this k common. So when this k is taken common, what are you left with? I am left with a minus 2b. Let us write a minus 2b here. What is a? Vector a is I to 1. That is 1 to 1. So vector c, if I were to write, it should be k times. It should be k times 1 to 1, right? So this should be I cap plus 2j cap plus k cap minus, what is 2b? So double of vector b will be 4, 2 minus 2, right? So it should be 4, right? And then I'll have 2, and then minus 2. I hope you are realizing reversing the signs because there is this negative sign. So 4, 2 minus 2 will become minus 4, minus 2 and plus 2. I hope there is no confusion on it. Now, if I'm willing to write vector c should be given by k times I minus 4i, that is minus 3i, 2j minus 2j, I think that is cancelled, and k plus 2k, that is 3k. Now, even if you wish to take this 3 out, then finally you will be left with 3k times minus I cap plus k cap. I hope there is no confusion on it. The result which we have received is very much clear to you all. Now, this is not what we were asked. Why? Because we were asked c cap. and that's a problem. We have worked out vector C. Can I not find C cap? That's a very easy task, students. Why? Because if I am willing to find C cap, now if you are getting confused with this 3k, don't worry about it, because I'll tell you that this 3k won't play any role at all if you are thinking like that. I'll try and tell you, let's say even if this 3k was there with I cap and j cap, what would have happened? So if this 3 cap goes with this, it would have been minus 3k I cap plus 3k. Okay, so that could have, no. So this is 3k and that is k cap. So I hope you won't get confused between k and k cap. Can you help me in finding c cap? So what will be c cap, students, here? C cap will be vector c divided by mod c. I hope there is no confusion on it. You all are able to crack it. So what is vector c? This is your vector c. So that's your vector c, which is minus 3k, right? Times. There you will be left with, I think, minus plus I cap minus k cap. I hope there is no confusion on it. Yes. So when you are taking minus 3k common, you are left with I cap minus k cap, or even let's say I'm taking 3k common, right? So if I'm taking 3k common, you are left with minus I cap plus k cap, right? There is no confusion on it, I believe. But when I wish to take mod of it, I have deliberately done it. So when you take the mod of it, it will give me square root over minus 3k square, which is what, 9k square. Similarly, this is also plus 3k square, which is again 9k square. That's what I was trying to make you understand, that it won't create any problem at all. I hope you must have realized now here. 9k square is 2 times 9k square. So 2 stays inside the under root, 9k square comes out and it will be 3k. And 3k gets cancelled by this 3k. So finally, here you are left with minus I plus j divided by this 3k are cancelled, and then you are left with under root 2. What you all must understand is that here, if I look at minus I plus j, sorry, minus I, why am I writing plus j? It should be plus k, right? So it should be minus I plus k divided by root 2. That is exactly what we are given in the option D. I hope there is no confusion on it. The only thing which you should keep in your mind is that here I could have had mod k in the denominator, because under root over k square would have given me mod k. So when k cancels mod k, I could have had a plus minus sign over here. So this answer is perfectly acceptable. Even a negative sign would also, or could also, have been our answer. Did you get this part? Two things you must be able to learn from this particular question. What are those two things? First thing is pretty simple, where you are said that here in this particular vector, this vector C is basically lying in the plane of vector A and vector B, which means C can be written as a linear combination of vector A and vector B. Second learning, the vector A and C are perpendicular, which means their dot product will be 0. So these are the two learnings which I applied, and rest is very simple. Finding the mod, finding the unit vector of that particular vector, that all is a very simple task. Even if you don't do all this, let's say you are not willing to do all this, what else you could have done here is that this is what I have tried showing you, that this is the kind of calculation students end up doing. What I'm trying to make you understand is you need not do all this, because directly this is 3k right here. So 3k remains as a constant outside, and then you are left with this vector minus I cap plus k cap. Take the unit vector of this vector. So minus I cap plus k cap, if I divide this vector by its magnitude, I'll get its unit vector, because 3k will remain as it is. I hope you're getting it. So here, if I take the magnitude of minus I cap plus k cap, it will be minus 1 square plus 1 square, that will be 2. So it should be square root of 2. And here, this magnitude gets divided by 3k, because in the denominator we were getting 9k square. So 9k square, when under root is taken, that will again give me 3k. So this 3k gets eliminated, and here by doing this calculation, you can very easily calculate the unit vector C. Any confusions on that? Are you getting it very clearly that this 3k can directly be eliminated while finding the C cap, and you can directly write this vector's unit vector? I hope it makes complete sense and you are able to digest what I'm trying to make you understand in this particular case. Now, moving ahead, let us look at the vector product or the cross product. And there comes another part, which is again a very crucial part. As we have already been discussing, algebra of vectors, scalar product, vector product. These are the three topics which play a very crucial role, or which are the most important topics from where the maximum number of questions are asked from this particular chapter, vectors. So always remember, this is the part where you need to again pay a lot of attention. This is again one of those crucial concepts. So again, the concept is very simple here, students. We have a vector A, we have a vector B, and if I'm willing to take their cross product, although this is what you study in physics as well, scalar, vector product, dot product, scalar product and all. So here, instead of getting into the details of the direction, if I talk about the mathematical part, vector A cross B, this A cross B is a vector quantity. We all know A dot B was a scalar quantity, but A cross B is again a product of vectors, but cross means the vector product. So again, A cross B will give you mod A, mod B times sine theta. This is going to be the magnitude of A cross B. What is sine theta? Theta is the angle between vector A and vector B, and on the basis of that you can predict or work out the sine theta's value. But since we have told that A cross B is a vector quantity, hence I will be using a direction. So I'll be using a unit vector to add a direction to it. But what is this n cap? That is also something you can understand quite easily if you just pay attention to what is written over here. The product vector A cross B in that order is defined by a vector whose magnitude is mod A mod B sine theta, and theta is the angle between A and B, and its direction is perpendicular to the plane of A and B in such a way that A, B and this direction constitute a right-handed system. Now please understand, what I'm trying to make you understand here is a very simple phenomena. Let's say we have a plane in which A and B lie. So this vector A goes like this, let's say, and vector B goes like this. So perpendicular to this plane, there could be two vectors, right? Either it could be coming out of this or it could be going backward towards the board, if you can imagine this. So if I create a right-handed system, which means A cross B, if I try to hold with this right hand, then the thumb will be directing towards the end cap. So it will not be going inside, it will be coming outside, because if I try to hold A cross B, then A cross B is letting me understand that with the right hand system, I can clearly deduct or reduce the direction of A cross B, which will be n cap. And what is n cap here? The right-handed system formed by A, B and n cap. I hope you are very clearly understanding it. So n cap is going to be a vector. Which of course I'm not able to draw in 2D, but I'll try to show it to you that this is perpendicular to both of these vectors. And of course, this is your n cap. So that is the direction of A cross B. Did you get that part? More importantly, what is going to be something which you should understand is what is the magnitude of A cross B, because that is what we deal with mathematically. In physics, you deal with n cap a lot, but here we'll be more concerned about A cross B. But you should remember that A cross B will be a vector which will be perpendicular to the vector which, perpendicular to the plane rather, in which the vector A and vector B lies. I repeat, vector A and vector B will be lying in a plane because these are the two vectors. They are bound to lie in one single unique plane. And n cap will be a vector which is perpendicular to this plane. Which plane? The plane in which vector A and vector B are lying. Did you get that part? Now, proceeding ahead, what do we know next? There are some more things which we already have understood. This is exactly what I have been explaining to you all. Now, there are certain properties which you should be aware of. In scalar product, a lot of things we assume. For example, A dot B and B dot A are commutative, which means they are same. Whether you find A dot B or B dot A, because it is same. But here the problem is A cross B is not equal to B cross A, because that direction has come into picture. So if A, B and n cap are forming a right-handed system, then while finding B cross A, B, A and that n cap, which is different, should also form a right-hand system. And that's where you need to understand that A cross B and B cross A could be same in magnitude, but when it comes to understand the whole vector completely, they'll have opposite directions. I hope you can imagine this. Let's say my palm is a plane, and on my palm, vector A and vector B lie. So imagine these are the two vectors which are lying on this palm. I hope you can imagine this. So if A and B are given, and A cross B could be this. So this is n cap, which is coming out of my palm. But if I find B cross A, this will be this vector going perpendicular to my palm on the back side. So that's what you need to understand. If A cross B is this direction, then B cross A could be this direction, although the magnitude could be same. That's why we will be concluding this particular part like this, that A cross B is not equal to B cross A. Rather, A cross B is equal to negative of B cross A. Why? Because of the direction. I hope you got this particular part. Similarly, vector product is not associative. What you clearly should understand is that A cross B cross C is not equal to A cross B cross C. It is amazingly different. How? This is what we'll explore while discussing the vector triple product, the final topic which we'll study from this particular chapter. Then I'll try and explain this part to you there. As of now, just understand this fact that they are not same, right? Now, let us look at the third part. If A and B are two vectors, then either I multiply A cross B by M, or I multiply vector A by M and then I take the cross with B, or even if I multiply scalar M with vector B and then I take cross with A, all is going to be same. So scalar getting multiplied to either A or B or A cross B won't make any difference. That will remain same. Going ahead towards the next property, this is again the extension of the one. Now this is something really interesting. Here, the way we have learnt in matrices, pre-multiplication, post-multiplication, I hope you must have remembered it. In the same fashion, here also you should remember the distribution. For example, if I am willing to find A cross B plus C, so A is getting multiplied from the left hand side. So if I wish to distribute it to B and C, it will be A cross B plus A cross C. There is a typing error here. It should be A cross B plus A cross C. This should have been vector C here. I hope there is no confusion over here. Similarly, if I were to talk about the right hand distributivity, which means if B plus C is multiplied by A, which means B plus C whole times cross of A. So it will be B cross A plus C cross A. Did you get that part? So here order matters. I hope you remember it. You will remember it. The only reason will remain very simple, because A cross B and B cross A are not same. Rather, A cross B is equal to negative of B cross A. So if you could understand that part, I think all of this will make complete sense to you. Now, moving ahead, what do we know next? Next, few more properties. Here, look at this part. The same holds true. If I multiply A cross product basically with B minus C from the left hand side, it will be A cross B minus A cross C. I hope there is no confusion on it. Now, similarly, what you need to understand is the vector product of any vector, 0 or non-zero, with a 0 vector is always 0, because the magnitude of the 0 vector will be 0 and 0 into anything will be 0. So again, A cross 0 or 0 cross A will give me 0 null vector, right? Now, here, the next property is the vector product of two non-zero vector is 0 if, now again, as we have learnt that for dot product, you cannot always say that they'll be perpendicular. There were some possibilities. Similarly, let's say if I am able to find that A cross B is 0. If we are able to deduce that vector A and vector B's cross product is 0. Now, what does it imply? First possibility, that A and B could be parallel. A and B could be parallel. Or second possibility, that A or B could be 0. But let's say if it is told that A and B are non-zero vectors. If it is given and told that vector A and vector B are non-zero vector, despite that I could find that their cross product is 0. If even vector A and vector B are not 0, and despite that we are able to deduce that their cross product is turned out to be 0. Well, that can happen. That can happen only when, I hope you all must be realizing, what do we know is that here, if I write it here, what is A cross B? A cross B is mod A, mod B, sine theta, whole times n cap. That's the direction. So if this A cross B is found to be 0, where neither A nor B is a 0 vector, well, I hope you're realizing mod A and mod B will not be 0. N cap is a unit vector. So what would have been 0 then? Then sine theta would have been 0. When do we have sine theta to be 0? When theta is 0. So if theta is 0, which means the angle between vector A and vector B is 0, which means vector A and vector B are collinear or parallel or like or unlike. So that's the part where you need to pay attention here, that if vector A cross B is found to be 0, that should clearly imply that A should be parallel to B. Here you need to take care of this thing in mind, that vector A and vector B were non zero vectors, then only this is true. So I hope you're realizing if I take I cross I, j cross j or k cross k, it will also be zero because I is parallel to I, j is parallel to j, k is parallel to k. On the basis of this, you can find the vector product in component form as well and the formula for that as well. Apart from this, here let us talk about this particular part as well. I hope you're realizing I cross j will be k cap. I hope you're understanding. Right-handed system, j cross k will be I cap and k cross I will be j cap. But again, if I change the order, which means instead of I cross j, if I'm dealing with j cross I, it will be minus k cap. If I'm dealing with k cross j, it will be minus I cap. If I'm dealing with I cross k, it will be minus j cap. I hope you're understanding the right-handed system which we are following. That's exactly what we need to understand here. There is this Lagrange's identity which I'll discuss, but before discussing the Lagrange's identity, I'll try and discuss the cross product in component form as well. Let's say there is this vector A which is A I cap, A1 I cap, let's say, and then A2 J cap, then plus A3 K cap. Similarly, there is another vector B, which is given as, let's say, B1 I cap plus B2 J cap plus B3 K cap, right? So these are the two vectors. Now, here, if I am willing or if I am asked to find A cross B, then how do you find A cross B? The process is straightforward, very simple. Either you take A1 I cap multiplied by all these three, then A2 J cap multiplied with all these three, then A3 K cap multiplied with all these three, and then you get the result. 9 terms will appear, then you'll find the summation or subtraction, whatever is needed to be done. Or rather, what I'm suggesting you to do is, there is an even shorter method, which says in the first row, you write I cap, J cap, and K cap. Now, some of you, those who were asking in determinants that what are the applications of determinant, these are the applications. It shortens your approach. It actually helps you in being more effective. It actually helps us in generalizing a lot of formulae with this simple determinant formula. So, I cap, J cap, K cap comes in the first row. Then you begin with this A vector. The coefficients are A1, A2, A3. So here you write A1, A2, A3. And then coefficients of B vector, B1, B2, B3. So B1, B2, B3. That is going to be A cross B. If you expand this determinant, you will get A cross B. Any confusions on that? Did you understand that part, students, that how did we find A cross B? So this is what you do when you are asked to find out the vector product in component form. Now, what is it? Lagrange has given an amazing identity. This identity is a beauty in itself. Why is it a beauty? First of all, let me try and tell you this. Let's say in a particular question, which will be there in JEE Mains. So there will be a question in JEE Mains which can be done with Lagrange's identity in seconds. Let's say there is a question, and in that particular question, they give you two things. This is a concept which will help you in getting the answers very, very efficiently, very, very quickly. What is that concept? In a question, let's say I am given mod A and mod B. So I am not given vector A and vector B. Along with this, let's say I am given the value of A dot B as well. So what am I given? Let's say I'm given two things. Which two things, students? Those two things are pretty simple. First of them will be, let's say mod A. This is what I'm writing here. Let's say I'm given mod A, right? So vector A's magnitude is what I'm given. Along with this, vector B's magnitude is also what we are given. So mod A and mod B we all are aware of. But what is the catch here? Let's say along with this, I am told vector A dot B. I am given vector A dot B as well. So three things, let's say I'm given. I'm not given vector A, I'm not given vector B, but I'm given three things. Magnitude of A, magnitude of B, and A dot B. All of them are scalar quantities. Great. If I have these three things, even if not vector A and vector B directly, rather simply if I'm given even mod A dot mod B. So let's say separately or isolately, even mod A and mod B are also not given, but the product of their magnitudes is given. And second thing is, let's say the dot product is also given. Then Lagrange has told us a very, very important, a very crucial identity whose proof I'm not giving at this stage. This can be proved very easily. In this one shot, let us have this result directly, which will apply. So Lagrange had said that magnitude of A cross B square which means square of magnitude of A cross B can always be written as mod A square mod B square minus A dot B square. I repeat, please remember this as an identity. This is something which you will keep using in questions. This is not something very ordinary I'm saying here. This is something which is required in a lot of questions. If you remember it, you can solve a lot of questions very quickly. I repeat my statement. Mod A and mod B is given, A dot B is given. Then you will be able to work out A cross B. Of course, it's magnitude. Did you get this part, this particular part, this identity? I hope you are able to understand. In a very simple language, it can be proved quite easily. From A cross B, I'll get sine square theta. From A dot B, I'll get cos square theta. So sine square theta plus cos square theta will be 1. And the common part which you'll be left with will be mod A mod B. Do you get that part? So that's how you could have proved it. But my conclusion remains very simple, that remember this as a result. Students forget it. And and sometimes while I explain it as a teacher, most of the students believe that this is something very common. This is something very ordinary. Yes, we all can remember it. And they all take this particular concept very casually. They don't learn this particular result, which has its own beauty, its implications. It will help you in solving a lot of questions. So I repeat my statement. Remember this. It will help you a lot in solving a lot of questions within seconds. Square of mod of A cross B plus square of dot of AB will be mod A square mod B square. Will you remember that? If this Lagrange's identity is understood by you all, let us move ahead with this thing which we have already discussed. I think I need not explain this part. Now let us understand one more thing. The way we understood the scalar product, its geometrical meaning, projection. I hope you must have remembered it. Can there be a meaning of can there be a geometrical meaning of the vector product? Yes, there is. What is that? Let us work on it. So here, let's say we have a vector A and we have a vector B, right? I hope this part is very well understood by you all. Now, with vector A and vector B, let's say I can form a parallelogram. Yes, we all can. So I hope that's a very simple task. So we have a vector A and we have a vector B. So let's say this is your vector A. So parallel to this, I have drawn another vector which we have drawn here. So that's your vector A again. And similarly, we had this as vector B, and parallel to this, we have drawn another vector which is this vector B only. So I could draw a parallelogram like this. What I'm doing here is, from this vertex B on the side OA, if I'm treating it as a parallelogram, I'm dropping a perpendicular. So this over here, BL is a perpendicular over here. I hope there is no confusion on it. Now, the interesting part here is, please pay attention to this part. Let's say I'm in a triangle OBL. What will be sine theta, students? So in triangle OBL, if I work on sine theta, it will be BL upon OB. I hope perpendicular upon hypotenuse. That is very clearly understood by you all. So what is BL? I hope we all can see it very clearly. BL will be OB sine theta. Do you all get that part? So here, what is OB, students? I hope you are realizing that OB is the magnitude of vector B. So OB sine theta will be basically mod of B sine theta. Now, when you are finding A cross B, what is A cross B, students? So vector A cross B, when you're trying to find out, it will be mod A mod B sine theta. Let's forget n cap for a while. Let's talk in terms of magnitude only. So A cross B will have its magnitude as mod A mod B sine theta. But what is mod B sine theta, students? We have already worked on mod B sine theta, that was BL. So A will be OA in terms of magnitude, B sine theta will be BA. So what is OA into BA? What is OA into BA? Sorry, it is not BA. I think there is some typing error. It should be BL basically. So here it should have been BL. So it is OA into BL, right? So this is not A, this is BL here. So I repeat, if you have this base which is OA, and if you are multiplying it by its perpendicular, which is basically the distance between two parallel sides, then we know that this is the formula for the area of a parallelogram. Do you remember that? So by that, I can very easily conclude that cross product, when I take the magnitude of it, then I'll be getting the area of the parallelogram. So I repeat my words very clearly here, students, that if I had this vector A and vector B, and with the help of vector A and vector B, I'm able to draw a parallelogram. And if I'm asked to find the area of this parallelogram, I'll say that area of this parallelogram is going to be magnitude of A cross B. So what is the geometrical meaning of A cross B? What is the geometrical meaning of A cross B? Let's say I'm given two vectors A and B, and if I'm able to form a parallelogram with them. So if I take the magnitude of A cross B, so if I take the magnitude of A cross B, then this number will be the area of the parallelogram formed with the vectors A and B. I hope you can see it very clearly. There's no confusion on that. Here, when I proceed further, there is this thing which you all have understood very clearly. Few more things which you should pay attention to is that if, let's say, I am given a parallelogram whose diagonals are given by D1 and D2, then also its area can be found as half of D1 cross D2. That is also something you should remember. Similarly, let's say there is a plane on which the quadrilateral ABCD is there, then half of AC cross BD, which is again nothing but extension of this formula only, so nothing needs to be explained here. This is something which you should understand is here the area whose adjacent, the area of a triangle whose adjacent sides are vector A and vector B. Now I can explain this part to you very clearly. Let's say there you have this as vector A for a while. Let's say this is vector A. Similarly, there is another vector B. So this is your vector B. Now let's say I am finding A cross B. So what will be A cross B? I hope I need not tell you. If I complete a parallelogram, I hope how can we do it? If I were to complete a parallelogram, I'll draw a vector parallel to A, I'll draw a vector parallel to B. So this parallelogram, although it doesn't look like this parallelogram which you will be able to draw, this parallelogram's area will be given by A cross B. Do you remember that result, students? But let's say if I complete this triangle, if I join these 2 points, I'll get a triangle basically. If I join these 2 points, I'll get a triangle basically. Do you not think that that triangle will be half of the area of this parallelogram? So if I could find the area of this triangle, I hope we can very clearly relate that the area of this triangle will be half of the area of that parallelogram. Which parallelogram, students, I'm trying to mention here? That if I take the replica of this particular side here, let me take it here, right? Similarly, if I take the replica of this side here, which is this here. So I hope you can see this entire parallelogram. So we all know that the area of this parallelogram is given by mod of A cross B. I hope you remember it. So that is the area of the parallelogram. But if I take half of it, do you not think it will give me the area of either this region or this region? So I hope you're getting it very clearly. Half of A cross B, let's say I'm calling it O, I'm calling it A, I'm calling it B. What is happening here? So this is, let's say, B. So half of A cross B will be area of the triangle OAB. I hope there is no confusion on it. You are making a lot of sense out of what I have said so far, right? So here, area of triangle ABC can be half of ABAC, BCBA or CBCA, basically cross product, and its magnitude needs to be taken. Not just that, this is also something you can remember if you want to, if you are willing to. It's again a very crucial result. Let's say I am given a triangle, and this time instead of giving its side, it gives you the vertices, the position vectors of the vertices A, B and C. So let's say they are small a, small b and small c. Can I find the area then also? Yes, the formula is given by half of mod of A cross B plus B cross C plus C cross A. So this is something also which I will ask you to remember. Now, moving ahead towards the next conclusion, I'll say, yes, there we have this conclusion. If I wish to check whether 3 points are collinear or not. So yes, one of the ways is linear combination. The other could be this. If these 3 points are collinear, then the area of the triangle formed with the help of these 3 points will be 0. So I hope you're realizing, if I put a mod over it and I multiply that by half, this will give me the area of the triangle formed with the help of vector A, B and C. So of course, if there is no triangle formed by vector A, B and C, position vectors A, B and C, then of course this value will result into 0. The area will result into 0, which will help us in concluding that this expression should be 0. Did you understand that part, students? I hope there is no confusion on it. And with that, let us move ahead towards a question based on vector product here. Now, what does the question say? Have a look at this part. It says C be the projection vector of B. So there is a vector B, and this B has its projection, and that is C on vector A. So here, vector B, from vector B, I have dropped a projection on vector A, and that is not just a length or a scalar quantity, it is a vector which is given by vector C. Alright, that is fine, that is great. What are we told next? If vector A plus C is 7, okay, that I'll use later. Then the area of the parallelogram formed by the vectors B and C is asked by JEE Mains in 2025. Three details, three information, three pointers are given to us. Let us use all of them one after another. Let's begin with the first set of data. C is a vector which is the projection of B, on this vector A. Now, usually projection is a length. Usually projection is length, basically shadow. But here in this particular case, if I am told that here C is the projection vector of vector B on A. Okay, forget that. Can you help me with projection of B on A? You must have remembered it. If I am asking you, find the projection of B on A. So I repeat, if I am asked to write projection of vector B on vector A, what would it be? I hope you must have remembered. It is always given by B dot A divided by mod A. Are you able to recollect it? Are you able to recall it? But here, what is the challenge here? Here, projection of B on A is this, of course, which is there true in terms of magnitude. But this projection is not a magnitude quantity. This is not a scalar quantity. This is a vector quantity, which is given by vector C. So projection of B on A happens to be a vector quantity. So if it is a projection of B on A, so it will be in the direction of A. Let's say there you have this vector B, there you have this vector A. So what is projection of B on A? So projection of B, I hope you're realizing, that is your vector B, that is your vector A. So projection of B on A will be this length. In scalar terms, this length is given by projection of B on A. But they are telling you that this is vector C. So if this is vector C, will I not say that this projection of B on A, which is said to be a vector quantity, it will be projection of B on A, which is given by this, and this is a vector quantity, which means it should have a direction, and this is having the direction same as vector A. So should I not append an A cap here? So this is the magnitude of vector C and this is the direction of vector C. Did you get that part? I hope there is no confusion on it. Now, if you have gotten this clarity, I'll move ahead with this conclusion that now we are able to crack vector C through some means. So let us try and write vector C. I hope this part is understood by you all. The only problem I might be facing is that I am not given vector B properly. That's the catch. This is exactly what we are trying to find out here. So let us try and find vector C here first of all. So if I start working on vector C, what is vector C here, students? Vector C is given by B dot A. Can I find B dot A? Yes, it's a very simple task. Scalar product in terms of component. So lambda I. So that is lambda. So here in the numerator, I'm writing B dot A. So B dot A is given by lambda I, or I, that is lambda. Okay. Plus, when you compare the J cap, so there is no J cap. So 0 into 2 will be 0. Getting it, everyone? Then 4K cap, 2K cap. So that is 4 into 2, 8. So from here, I'll get 8. So this is B dot A. I hope there is no confusion on it. What about this mod A? Can I not write A cap? Can I not write this vector A cap as, I'll write it here. In the numerator, we had this B cap dot A cap, but in the denominator, we had mod A. A cap, I can write as vector A upon mod A. So this mod A into mod A will give me mod A square. So here, B dot A upon mod A square is needed to be done. Can you help me with mod A square? Let's find mod A first. So it will be 4, 4, 1. 2 square plus 2 square plus 1 square. So 4, 4 plus 1 is 9. Square root of 9 is basically 3 and square of that 3 will be 9. So mod A square will be 9. Did you get that part? So mod A square is going to be 9. That I'm writing here. Times, whole times vector A. So what is vector A? I need to write vector A. This is vector A, I, 2j, 2k. So here it is going to be I cap plus 2j cap plus 2k cap. So that's your vector C. Any confusions on that? I hope you're able to digest this part here very clearly. Now, what are we told next? That sum of vector A and C, the magnitude of sum of vector A and C is 7. Okay. What I know very clearly is this is vector C. So can I not say, if somebody says that sum of vector A and C, the magnitude of sum of vector A and C is 7. What is vector C? Vector C is also written in terms of vector A. If you are not getting it, I'll write it here. What I'm given, or what I am told here, is that sum of magnitude of vector A and C is 7. So let's say vector A is vector A, but what is vector C? Vector C is lambda plus 8 upon 9. Vector C is lambda plus 8 upon 9 times vector A. What was vector C, students? Vector C was lambda plus 8 upon 9 times vector A. So that was vector C. And its mod is given by 7. I hope there is no confusion on it. Moving ahead, can I say vector A stays common times, what are we left with? We are left with 1 plus lambda plus 8 divided by 9. Its mod is needed to be taken and it is given to be 7. I hope there is no confusion on it. Now here, 9 plus 8 will be 17. So it is lambda plus 17 by 9, and then this should be multiplied with the mod of vector A is equal to 7. Now please understand, we were told that lambda was a positive quantity. So positive plus positive upon positive will be positive. This being constant can be taken out of this magnitude. So this is going to be lambda plus 17 whole divided by 9, which is a positive quantity, times mod A is equal to 7. Do you all get that part? I hope there is no confusion on it. Now, moving ahead, what I know next is that I think I have cracked the value of lambda from here, because mod A, what is mod A? We have already evaluated this as under root 9. I hope you must have remembered it. So mod A will be 3. So here if I write 3 over here, it is lambda plus 17. 3 by 9 is going to be 3 is equal to 7. From here, lambda plus 17 will be 7 into 3, which is 21. So lambda should be 21 minus 17. 21 minus 17. I hope nothing needs to be told. This is going to be 4. So that we have received as a value of lambda. Any confusions? The question is not done yet. Why? Because from here, if I move ahead, I am asked the area of the parallelogram formed by vector B and vector C. Okay. So what was vector C? I think we had vector C. This was vector C, right? So we have cracked the value of lambda as 4. 4 plus 8 is how much? 4 plus 8 is 12. 12 upon 9. I think 12 upon 9 is basically 3 times 4. 3 times 3 is 9. So 4 by 3. I hope there is no confusion on it. So this is 4 by 3 times I cap plus 2j cap plus 2k cap, which is vector A. So vector C is basically 4 by 3 times of vector A. I hope you are understanding this. Now let us get back to this part. Here I am told the area of the parallelogram formed by B cross B and C. So if I am asked to find the area of the parallelogram formed by B and C, it will be magnitude of B cross C. Do you remember it? Magnitude of B cross C. I know vector C is 4/3 of vector A. So can I write it as B cross 4 by 3 of vector A? I hope there is no confusion on it. 4 by 3 being scalar can be taken out. So it can be written as 4/3 of B cross A. So my job is now restricted to finding B cross A. Now B cross A is a very easy task for us because we know B, because we know A. I think B cross A will not be a huge or amazing task for us because it will be 4 by 3 times of magnitude of determinant of. So this is mod. So by having the vector product, I'll be getting a vector quantity. But that vector B cross A I need not have, I need to take its magnitude. So B cross A I'll find first by using the determinants, and then I'll find its magnitude. So B cross A will be I cap, J cap, K cap. Then components of B are lambda 0, 4. I hope you are understanding there is no J cap, so it should be 0. So lambda 0, 4. And what was lambda? Lambda was 4. So it should be 4, 0, 4. Then you are supposed to write the components of A, which were 1, 2, 2. Which were 1, 2, 2. Now, the next part is pretty simple here, students. I need to find this particular result, which is going to be 4 by 3, magnitude of which vector? Let us write the I component. So I cap will have 0 minus 8. Do you all get that? 2 into 0, 0. 4 into 2 is 8. So which is minus 8. So it should be minus 8 I cap. Then let's talk about j cap. So j cap will be 4 into 2, 8 minus 4. So it should be 8 minus 4, which is 4, but j will be with negative sign, so it should be minus 4j cap. Then let's talk about k cap. So k cap will be 8 minus 0. So it should be 8k cap. So it should be 8k cap. I hope there is no confusion on. If you wish to avoid a little bit of calculation, you can take 4 common. So 4, 4, 4 when taken common, 4 into 4 is 16. So this will be 16 by 3 basically. And then you'll be left with 2, 1, 2. So it will be minus 2i cap minus j cap plus 2k cap, right, students? Now, I hope finding the magnitude of this is an easy task. 4, 4, 1, which is 9, square root of 9 is 3. 3 gets cancelled by this 3, and then you are left with 16. So, the area of the parallelogram formed by the vector B and C is going to be 16. Did you get that part? A lot of things we have done in this particular question. I'll begin with the first part. I found first of all the projection. Then I went to A plus C, its magnitude was 7, through which I could find lambda. And after finding the lambda, I worked on finding the area of the parallelogram given by vector B and vector C. I hope step by step you are able to understand this. Tell me in the comment box how many of you have cracked it before me. I would really appreciate it if you are now able to apply the learnings which are taught to you. And I hope this one shot is found to be a very fruitful session for you all. This question, if it is understood, let us move ahead towards the next part. What is the next part over here, students? Moving ahead, let's see a few more things very clearly here. After this question, let's say, what do we have here is scalar triple product. Two things which are reduced as per the syllabus, but of course they are equally important because a lot of questions which you were solving previously can be done with more ease if you know STP and VTP, scalar triple product and vector triple product. What are they? Let's have a look at this particular part. Again, I repeat my statement very clearly. Keep this thing in mind that questions may not be directly visible from STP and VTP, which can be solved with algebra of vectors and product of vectors. But if let's say you are able to use STP and VTP in your questions, then your efficiency gets enhanced. So if you are investing some time in learning what is STP and VTP and its applications, its interpretations, then your ability to deal with questions will become more effective. How? Let's have a look at that part. Here, first of all, let us work on understanding STP. It's a very simple thing. Don't worry much about it. It's a very simple observation. If you simply understand what is it and what are its implications, what do you understand by it? If you understand the STP and its applications, then you will be able to apply it in a lot of questions and get the results. So scalar triple product is defined for 3 vectors. Triple product, I hope you're understanding it. It is defined as dot product of one of the vectors with the cross product of the other two. So what does it mean? Let's say if I'm finding A cross B dot C. So what is it? Cross of A cross B will be a vector. Vector C is already a vector. So dot of A cross B with C is scalar triple product. Or what you can say is that this A cross B dot C is written as box of ABC. So this is given by box of ABC. Always remember, you need to understand this thing very clearly since it is a scalar triple product. As the word itself is giving us the idea that A cross B dot C. So first of all, you will find A cross B and then you'll take this vectors dot with vector C, and of course it is the final outcome is going to be a scalar quantity, and that's where we are calling it scalar triple product. Did you get that part? Now here the properties. How do you deal with STP? Let us look at that particular part. What you need to understand is that geometrical interpretation. What is the geometrical interpretation here? It's a very simple phenomenon, students. I'll directly give you the idea. Here, let's say first of all I was finding A cross B. So let's say there is a plane. There is this plane, right? So this plane has vector B and vector A. So what do you understand by A cross B? Do you remember? Mod of A cross B will always give us the area of the parallelogram made with the help of vector A and vector B. So vector A and vector B are, let's say, forming this parallelogram. So this parallelogram's area is going to be given by mod of A cross B. And imagine if the base area, the area of this base, which is A cross B's mod, if I could multiply it with the height here. What is the height here, students? The height here is given by vector C. So the area had the area mod A cross B, and if I multiply the area of the base with its height, do I need to tell you? It always gives you the area of this prism, or prism in a simpler language here is this the basically cuboid or a parallelogram or a parallelopiped. What do I mean by that? Please understand this conclusion very clearly. What I'm trying to make you understand is a very simple phenomena here. What is that? Have a look at this part. Let's say here I had a base. Let's say I had a base here, which is given by here, let's say vector A and vector B. So this, what's wrong with this? So this is vector A and vector B. With the help of it, I could derive a base, basically a parallelogram in 2D. But let's say I add a fixed height to it. So let's say I'm adding a fixed height to it. So when a fixed height is added to it, this is what it becomes. I hope there is no confusion on it. So if I'm adding a certain height to it, if I'm adding a certain height to it in 3D, it has now become a parallelopipe. Now, of course, it is not necessary that this C will be perpendicular on A and B. So what else could be possible is that vector C could be a little bit inclined on vector in B. So vector C could be like this as well. So in that case, I hope you're realizing this is how it could have become. So this is what a parallelopipe is. Imagine you are living in a room and I push some sliding efforts on the terrace of your room. So your room gets tilted. Imagine a carton, a box, and you just push some tangential efforts on its terrace, on its top. So it gets tilted like this. Although I have not drawn this figure very properly, but I hope it makes complete sense in your brain that this is a parallelopipe. So the volume of the parallelopipe is given by a very simple fact that if you are able to find its base, if you are able to find the area of its base, and if you multiply the area of that base with its height, if you multiply that area of the base with its height. So please understand the area of the base is always given by A cross B. I hope you are understanding it. And if you wish to multiply it with its height is going to be mod C times this angle here, let's say cos theta. If this angle over here with this vector C and vector B is theta, then this height h will be given by h cos theta. My motive here is not to make you understand the derivation. My motive here is to make you understand the geometrical interpretation of STP, which is nothing but what? If you are given a parallelopipe whose base is given by, let's say, vector in vector B, and its height is given by vector C, then scalar triple product A dot B cross C or A cross B dot C will give you the area of this parallelopipe, which is basically, in this particular case, if it all becomes a 90 degree, then it will become a cuboid. So area of the cuboid is also given by A dot B cross C or A cross B dot C. It is commutative here. What do I mean by that? Let me try and make you understand. STP is a very simple phenomena. Let's say if you have three vectors A, B and C. So even if you put efforts in finding A cross B first and then you find its dot with C, or whatever result you get, that same result will be attained by you if you are using this particular application. So determinant plays a very crucial role, or rather a very effective role in finding the STP with a lot of ease. What is that ease? Let's say if I am asked to find the area of a parallelopipe which is formed with vector ABC, or rather let's say in a question I need to find STP of ABC, which is either A dot B cross C or A cross B dot C, something like that. In that particular case, all I need to do is write the I cap, J cap, K cap components of A first, then B and then C, and this will help you in getting A cross B dot C. The order must remain same. The cyclicity must not change. If the cyclicity is not changing, then cross and dot can be interchanged. What I'm trying to make you understand here is that even if you are finding A cross B dot C, or if you find A dot B cross C, then also it will give you the same result. Trust me. So I'm trying to tell you that dot and cross, the order can be changed with dot and cross, but the order of ABC, the cyclicity must not change. So here, if it was like this, you could have had it like in a different manner as well, where you could have said, sir, can I take B dot C cross A? I think the order hasn't changed. A, B, C, C, A, B, B, C, A. If that cyclicity is maintained, then yes, whether you take this or this, they'll have the same value, which is this determinant. So first of all, what is STP? What is the geometrical meaning of STP? And third, how do you evaluate an STP? Now, fourth thing, if STP can be evaluated with the help of this determinant, so all the properties which are true for a determinant can be applied for this STP. So now I'll be sharing a lot of properties of scalar triple product with you, and I'll not be proving them. I'll simply be redirecting them with the notion that if you know the determinants, if you know the properties of the determinant, you can very easily predict the properties of STP. What are they? Let's have a look at this. First of all, as I have already mentioned, that it is commutative. It can, the dot and cross can be interchanged here, which means that even if I take A cross B dot C or A dot B cross C, which means position of dot and cross can be interchanged. Only thing you need to ensure is that ABC, this product should not alter. This order, this cyclicity should be maintained. Then it will always give you the same value, which is given by box of ABC. I hope you are remembering it. So box of ABC means determinant ABC, where in the first row you are writing the components of A, second row has components of B, and the third row has components of C. Did you get that? So here I am trying to tell you that whether you have ABC or BCA or CAB, I hope you remember interchanging rows, interchanging columns. That's exactly what we are doing, and on the basis of that, ABC, BC and CAB will be same. What does it mean? It means A dot B cross C, or even B dot C cross A, or even C dot A cross B. They'll be same. Not just that, there are three more results to it. A cross B dot C, B cross C dot A, C cross A dot B. All of them will give you the same result. So all 6 of these are going to give you the same result. That's what I'm saying. Next property. I hope you're realizing ABC can be written as negative of BCA. Why? Because if I'm interchanging two rows, then the sign of the determinant changes. Are you getting it? Are you able to relate it? The next property here, if a scalar quantity is there present in any row of a determinant, then that scalar can be taken out of the determinant. I hope you remember it. The properties of determinants are shown here as the properties of STB. So they are nothing but the properties of determinants which you have learnt. Similarly, if K1 is multiplied to the first row, K2 is multiplied to the second row, and K3 is multiplied to the third row, rather what I can do is K1 can be taken out from the first row, K2 from the second, and K3 from the third, and then you can take the determinant of these ABC only without that multiplying factor, because that multiplying factor is taken outside from each row, and that's how you have multiplied them all together, and then you take the STP or the box of ABC. Are you understanding this particular part very clearly here, students? Now, moving ahead, what do we have next? Yes, we already know that determinants addition was also there. We have studied it. So let's say if in a row you are adding two vectors. In a row, you are adding the components of two vectors and the other two rows are same. So I hope you know in determinants, we can split those two rows like this while keeping the other two rows same. So A plus B, C and D, if STP of or box of this is needed to be brought, you can write it as A, C, D. I hope you are understanding it, plus box of B, C, D. Any confusions on that? All I'm trying to make you understand is a very simple fact that this order must remain same. The cyclicity must not change. A, then B, then C, then again if A, then B, then C, then A, then B, then C. So this is how you should maintain that cyclicity. If that cyclicity is maintained, you will always have the correct value of your scalar triple product. Any confusion on that, students? Moving ahead. There is one more thing. Please understand this particular part. And these are the conclusions which I was mentioning or talking about. I was trying to say this very particular thing here very clearly, that if you know these properties, which I am going to discuss now, then some of the questions which you were using, which you were able to solve through some longer methods, through algebra of vectors or vector and dot product of two vectors, with STP and VTP, you can solve them more quickly, more efficiently and more effectively. Let us learn those properties first. Now, what are those properties? The necessary and sufficient condition for three non-zero, non-collinear vectors ABC to be coplanar is that their STP is 0. What do I mean by that? My point is very simple. Factually, why am I saying this? Because let's say if you have, let's say, three vectors which are coplanar. So let's say there are three vectors lying in this plane. So this is, let's say, vector A. This is, let's say, vector B. And this here is, let's say, vector C. They can roam anywhere in this plane. Basically, they could be placed anywhere. So these are basically three vectors I have drawn in this manner because of my own reasons. It could be anywhere, right? All you need to ensure is that they should lie in this plane. What do you mean by A cross B? So if I'm finding A cross B, it will have its own magnitude, which I'm not concerned about, but that A cross B will be a vector which will be perpendicular to the plane in which A and B are lying. Now, what I have found is A cross B. Now, with A cross B, which is a vector quantity which is perpendicular to this plane in which A, B, and C are lying, and if I take its dot with C, so n cap is the direction of A cross B, which is perpendicular to this plane, the plane in which A, B, and C are lying, which means this C will also be perpendicular to n cap, which means if A cross B, which is having the direction n cap, if I multiply it with vector C, do you not think its dot product will be 0? Why? Because A cross B will be perpendicular to vector C as well. And that's why I was saying that the necessary and sufficient condition to check three non-zero, non-collinear vectors to be coplanar is only this, that their STP, their box, should be 0. So if the box is 0, they'll be coplanar. If they are coplanar, the box will be 0. They should be non-zero and non-collinear. That's the condition. Here, this is something which, if you remember, can be used a lot, especially in the questions of JEE Advanced, majorly in JEE Advanced. But of course, in JEE Mains also you use it. If you remember the product of determinants. If you remember, in the determinant chapters one shot, we had a discussion on product of determinants. And if you remember that particular property, that's exactly what I'm using here. Let's see it opposite first. If I am asked to take the product of two determinants x1, y1, z1, x2, y2, z2, x3, y3, z3 and a1, a2, a3, b1, b2, b3, c1, c2, c3, then we all know that that product of these two determinants can be written as this, comma, this, comma, this. So STP of x1a, y1b, z1c, comma, x2a, y2b, z2c, x3a, y3b, z3c. If that STP is needed to be taken, what is common here? If you just pay attention to the part here, this x1, y1, z1, x2, y2, z2, x3, y3, z3, that is there. These are the 9 scalar quantities. But what is common here? The vectors a, b, c, a, b, c, a, b, c. If these three vectors are there and if its STP is needed to be taken, what you do is you can split it into two determinants and then product of these two determinants can be taken. Don't take the product of these two determinants. First of all, evaluate this determinant separately, which you all can do very easily. Evaluate this determinant separately. They'll give you two values and then multiply them. So this is again a property which will be used. If you remember it, you of course are going to get a lot of good results more effectively and more efficiently. I hope these properties are very clearly understood by you all. Moving ahead towards the next set of properties, what do we have next? Here also, let's say if there are 4 points. So with 4 points, I can create 3 vectors. And if I'm told these 3 vectors are coplanar, then again, their STP should be 0. Very well understood, I believe. Now, moving ahead here, if 4 points A, B, C, and D, there is a small correction over here. This should have been vector B here. So if there are 4 vectors A, B, C, D, they are coplanar if, you can remember this as a result, box of ABC plus box of ACD plus box of ADB should be equal to box of DBC. Remember this as a result, or rather the previous result, any. Or if you don't remember all this, I will say that with 4 vectors, you can, with 4 position vectors, with 4 points, can you not create 3 vectors? And those 3 vectors, if they are coplanar, their STP, their box will be 0. That you need to remember. This one, even if you don't, will do justice to you. Here also we know that if any determinant has 2 rows same, if any determinant has 2 columns same, then its value is 0. So if you are taking box of AAB or BBA or CCB, it will be 0 because AAB will be coplanar. That is also a reason to prove it that this box will be 0. So if in any box you see 2 vectors to be same, then its box will be 0. You need not evaluate it explicitly. Are you getting that result? Moving ahead towards the next property here. Now, let us talk about a tetrahedron. So what is the tetrahedron? I hope you're able to understand this particular shape. A pyramid kind of a structure. So we are talking about a tetrahedron specifically, which has the triangular base. So in 3D, try and imagine you have a triangular base here, and on that triangular base you have created a pyramid. So this is the tetrahedron, which basically has 4 sides. I hope you can see this here. If you look at this particular tetrahedron, it has a triangular base. I hope you can notice it here. And on this base we have created 3 faces. First, I hope you can see the second one, and this as the third one, if you could notice very clearly. So this tetrahedron shape, which is having a triangular base, is covered by 3 faces. Is there any confusion on that? Did you get complete clarity on it? Now, let's say this tetrahedron, which is given by OABC, I hope you are understanding, it will have 4 vertices. If this has 3, this tetrahedron is made with, let's say this O is basically origin for a while. So these 3 points, these 3 vertices on the base, which are said to be A, B, C, having position vectors A, B and C, or even if they are given by 3 vectors A, B and C, these 3 edges, then the volume of this tetrahedron is given by 1/6 of STP of ABC. So that's where STP plays another crucial role geometrically, that if you're given a tetrahedron, let's say any tetrahedron you're able to form, any tetrahedron, let's say there is this tetrahedron which you're able to form with these 3 vectors. This is vector A, this is vector B, and this is vector C. Sir, how are you calling it to be a tetrahedron? See, when I complete it here, this is going to be the base. So can you see that this is the base of the tetrahedron? So here, if these 3 edges are given by vector A, vector B and vector C, this tetrahedron's volume will be given by 1/6 of the STP of A, B and C, and I hope you know how to find the STP of these 3 vectors. Did you get that part? Any confusions on that? If you have understood that part, let us look at the question, and then I'll try and tell you how easy questions are. Of course, asked by JEE Mains only. This was a question by JEE Mains in 2024 or 25 possibly. So in this particular question, how are we going to solve a question based on volume of a tetrahedron? Let's look at that data first of all. So here we are told that ABCD is a tetrahedron such that AB, AC and AD are mutually perpendicular. That's the best part. So if I could try and make you imagine this, what they are trying to tell you is that this angle over here, this is what you need to imagine 3D. So the angle between sides A and B is 90. The angle between this B and C is also 90, if you are able to imagine this in 3D. Even the angle between A and C, this angle here between A and C, that angle is also 90. This is what you need to imagine in 3D. So these 3 sides, these 3 edges are mutually perpendicular, right? AB, AC and AD. Now, what are we told? The areas of the triangle ABC, ACD and ADB. So here, I hope you can see, if you forget this base, we have 3 triangles. Which 3 triangles here, students? If I could help you noticing that this is your first triangle, can you not notice it? Then you have a second triangle. Which is the second triangle? This one over here. Can you not notice it? This is the second triangle. I hope you can notice it. And then you have the third triangle. Which is the third triangle here, students? This triangle. This triangle over here is the third triangle here. I hope you can notice it very clearly. So these 3 triangles area is what we are given to be 5, 6 and 7. That's brilliant. Then they are asking you the area of the triangle BCD. So they are asking you the area of the triangle BCD. Okay. So before I start solving this question, can I now work on drawing it more properly? Because once you're able to draw it, the visualization becomes simple. And if you're able to visualize it, then the problem will be really simple. Most of the students give up. Most of the students give up on the part, sir, this is going to be a very complicated question. This is going to be a hugely, amazingly huge question in terms of calculation, and then we simply have dropped it. So sometimes what you need to understand is questions may look lengthy, questions may look tough, but they are not. This is the perfect example of such questions. A lot of times questions may appear difficult, question may look tough, but they really are not. So once you get into this question, if you arrange the data more wisely, if you are intelligent enough in organizing your data, putting your coordinate axis systematically, you will be able to get your answer very quickly. Why? Because you have the clue. If you didn't notice, then this is the part which will help you a lot. AB, AC and AD are mutually perpendicular. Try and imagine having three vectors which are mutually perpendicular. Are you not able to think x-axis, y-axis, and z-axis? Are you not able to think I cap, j cap, k cap? And your job is done. My point is very simple, that this question is really simple. Once you read this line and use it as per your benefit, as per your requirement, according to your need. So if AB, AC and AD are mutually perpendicular, let me use I cap, j cap, k cap or my coordinate axis system. So let's say I have these coordinate axes x, y and z, right? So let me just draw these. So this, let's say we are imagining to be the z axis. Okay, then we are taking the, let's say, y-axis like this. All right, students, and then let's say we take the x-axis like this. Okay, so these are the x-axis, y-axis, and z-axis. Now, on these axes, which can be treated as I cap, j cap, and k cap, unit vectors, here on this axis, if I know that these three are basically at 90 degrees. I hope you can see it very clearly. So can I not avail them as vectors A, B, AC and AD? I can have vectors A, B, AC and AD on these x-axis, y-axis and z-axis respectively. Why are we not using them as per our need? Why do you have to complicate it? So here, that's the advantage you could have taken. So how do I do it? I will say that, sir, I have to take three vectors A, B, AC and AD. So what is common? A. So use it accordingly. A can be taken at origin. Why are you not taking it? You have this vagueness. So take that benefit of doubt, put A at origin. So if I could place A at the origin, so origin I'm treating as A. So let's say this is B, this here is C, and this here is D. I hope there is no confusion on it. So here, I hope I need not tell you that if, let's say, D is your x-axis for a while, this B lies on the y-axis for a while, let's say, and this C lies on the z-axis for a while. Can you help me with the coordinates of D, B, and C? See, if vector D lies on the x-axis, it will have its x component only because y component and z component will be 0. So D can be written as x I cap plus 0 j cap plus 0 k cap. So this D can have x 0, 0 as its coordinates in 3D, or this AD, if I wish to write the vector AD, then I can write the vector AD. Let me write the coordinates of D here, which are x 0, 0 here. So if I wish to write the vector AD, can I not say that it will be x I cap? Do you all agree with this? Similarly, the coordinates of B, since it lies on the y-axis, it will be 0, y, 0. So vector AB will be yj cap. I hope there is complete clarity about this. So this is going to be yj cap. What about vector AC? C vector lies on the z-axis, so it can be treated as 0, 0, z, and its coordinate can be taken as, so its coordinate are taken as 0, 0, z. So vector AC will be given by z k cap. Any confusions on that? Do you get complete clarity on it? Now, let us complete this tetrahedron. Do you not think that if I am completing this tetrahedron, then this tetrahedron will look somewhat like this? See, this AD will be joined here, this BD will be joined here, and then this CB will be joined here. So I hope you are able to imagine a tetrahedron in 3D. AB, AD and AC are three triangles. I hope you can see them very clearly. Which three triangles I'm talking about? These three, students. Which three? Here. This is your triangle ACD. I hope you can see it very clearly. This is your triangle ABC. I hope you all can see it very clearly. This is your triangle ABD, which also you must be able to see very clearly. And why not take them on the positive side? So positive x, we have x 0, 0. On positive y, we have 0, y 0. And on positive z, we have 0, 0, z. Why do we need to complicate it? So let's take the benefit of doubt. Let's take things according to our convenience, because nothing very specifically given over there. So why don't we use them according to our need? So this is what we know, right? Now, I know the angle between this AB and AC is 90. The angle between AC and AD is 90. The angle between AB and AD is also 90 over here. I hope you're able to imagine this in 3D. So these are basically three right-angled triangles. I repeat, ABC, ACD and ADB are three right-angled triangles. I hope you're understanding why. So if they are the three right-angled triangles which are having the area as 5, 6 and 7, I know a lot about them. What I'm trying to make you understand is here a very simple phenomena. Can I say when you are told ABC, the area of the triangle ABC. So the area of the triangle ABC here is given to be 5. So area of the triangle ABC is given to be 5. Can you not see this? So if this area is given to be 5, how do I find the area? Sir, for a right angle triangle, the area is half base into height. Let's talk about 2D. So half base into height. So base is y, height is z. So can I not say half y into z will be 5? Which means yz will be double of 5. Yz will be double of 5, which will be 10. Did you get that part? Similarly, let's talk about the area of ACD. So ACD, again half base into height. Base is x, height is z. So half zx will be 6. So if half zx is 6, can I say zx will be double of 6, which will be 12. Similarly, the third part, ADB. ADB, I hope you can see base and height. So base is y, height is x, half xy is 7, and that's why we'll say xy is double of 7, which is 14. So this conclusion, I hope you're able to completely comprehend without any confusion that yz, zx and xy we have evaluated here with this much ease. Now, let's talk about the third part. We are asked to find out the area of the triangle BCD. We are asked to find the area of the triangle BCD. Now let us use the geometrical interpretation of the vector product of two vectors. What do I mean by that? See, BCD, we have a vector BC, we have a triangle BCD. So if we have a triangle BCD, let's say we have two vectors DC and DB. DC and DB. Can you not see that? And if I take half of magnitude of cross of DB into DC, that will be the area of the triangle. Do you not remember it? So I repeat my statement very clearly here, students, that here, if I were to find cross of DC and DB, if I took the cross of DC and DB, and of course its mod and its half, then it would have been the area of the triangle DCB, which is exactly what we are asked. So area of the triangle BCD, area of the triangle is BCD is given by half of mod of DC cross DB. This is exactly what we have discussed when we discussed the vector product of two vectors. So I hope DC and DB is a very easy task for us, because half will remain half, mod will remain mod. But let's talk about the DC cross DB. So it should be I cap, J cap, K cap. And then what will be DC? Let us try and write DC. So vector DC, right? So vector DC will be position vector of C minus position vector of D. So it will be Z minus 0, 0 minus 0, 0 minus X. So Z, 0 and minus X. So it is going to be Z I cap, 0 J cap and minus X K cap. Let us work on DB. Vector DB. What will be vector DB? This is going to be vector DB. It will be position vector of B minus position vector of D. It will be 0 minus X, Y minus 0 and 0 minus 0. So I think it will be minus X I cap plus Y J cap plus 0 K cap. So minus X, Y and 0. Okay, so this should be minus X, Y and 0. I hope there is no confusion on it. Minus, let me just check it once again, minus X, Y and 0. Because if you do any calculation error here, the entire question goes wrong. So let us be more cautious and alert while putting these values here. Getting it? Now, this half remains half. This mod still stays here. Now let's work on I cap. So I cap will be 0 minus xy, which is plus xy. So it should be plus xy. It should be plus xy I cap. Then let's work on j. What will be j? So j here will be, of course, it should be minus j, because second position, second row, second column. It should be 0. It should be, I hope with I cap, yes, we have written it correctly. For j, it should be 0 plus x square. I hope there is no confusion on it. So for j, it should be, I'm really sorry. For j, it should be 0 plus x square. So it should be x square j cap. I hope you have gotten this part also very clearly. Now, let's talk about k cap. For k cap, you would be writing it as, this k cap stays like this. So it should be yz minus 0. So it should be yz k cap, right? So I hope this part is also very well understood by you all. There is no confusion on it. Now, let us work on putting these values and then finally getting the answer which we are supposed to get. I hope there is no confusion on it. There is complete clarity here. Now, how do you find the mod of it? I think modulus of this, magnitude of this is a very simple task because it should be x square y square plus square of x square plus y square z square, and that's how I will get the final answer, right, students? I think that I'm making a mistake here because when I look at this part, this is making me a little confused. So let me go back to see these two vectors, vector DC, right? So vector DC would have been minus x, 0 and z, right? Yes, I have written it incorrectly. It should be minus x, 0 and z. I'm really sorry for this. So let me just correct this here. There was a correction here. So this should have been, I repeat, minus x, 0 and z. Okay. So this should be minus x, 0 and z. Let me check the other part as well. The vector dB. So the vector dB should have been minus x, y and 0. So I think that is correct. Minus x, y and 0. Yes. Now, let us work on this particular part now. So it should be half of, I hope you're realizing that was the correction over there. So here, if I look at, this is j cap, right? So if I look at this part I cap, it should be 0 minus yz. So it should be, it should be minus I cap. For I cap, it should be 0 minus 0 minus yz. So it should be minus yz I cap. Then for j, it should be 0 minus xz j cap, but it should be plus, so it should be plus xz j cap. Then for k cap, it will be minus xy plus 0, so it should be minus xy k cap, right? And that's why we have these values yz, zx and xy. So yz we have as 10, zx we have as 12, and then 14. So I will be writing it as 10 plus 12 and then minus 14. Even if you wish to write it as this, then it should be minus 10 I cap plus xz was 12, and then the other one was 14. So it is 14 j cap, 12 j cap minus 14 k cap. Its magnitude and its half is needed to be taken. So first of all, take the half because that will make our calculation a little simpler. So 10, 12, 14. So if I take this part here, 10, 12 and 14, it will give me 5, 6 and 7. So it should be minus 5 I cap plus 6 j cap and minus 7 k cap. I think the calculation is done. This is what you all can do. 5 square is 25, 6 square is 36, 7 square is 49. You add them up and then you take the square root and then you can mark the correct answer accordingly. My motive was to make you understand the question was not tough. It may appear to be tough. It was a question on tetrahedron. Students do get confused of tetrahedron so easily that the moment they see the word tetrahedron being used in a question, they skip the question. It's simply a matter of visualizing the question properly. So in vectors in 3D, if you are able to put the data on your scale, on your basically frame with as much ease as possible, you will be able to crack a lot of questions with a lot of efficiency. Now, let us talk about vector triple product. Now, what is vector triple product? First of all, without confusing you all, I'll straight away try and give you what is VTP. Straight away at this stage here, what you need to understand is that whenever you wish to write A cross B cross C. Now, I hope you know cross is a little confusing for students. Cross basically is something where you need to be more cautious because whenever dot is there, a lot gets simplified. But whenever cross comes into picture, you need to be more cautious, more vigilant with the order, with the sign and a lot more things. Here again, we are taking the cross product. So this is the triple product and this is the cross triple product. So it can be said the vector triple product. Now, what do I mean by vector triple product? You can now at this stage, instead of looking at the proof, you can remember the result directly. So here, all I'm trying to make you understand is a very simple result. Let's say this is incorrect. I believe something is wrong here. Let me just make this correction over here. So whenever I'm asked to find A cross B, whenever we are asked to find A cross B, how do we find it? Let's work on it. So A cross B, how do I remember it? This is the shortcut I'm giving you. How do I remember it? First of all, you need to understand that it will always lie in the plane of B cross C. I repeat, vector triple product is a triple product of three vectors A, B and C where A cross B cross C. And unlike STP, it is not commutative. So you cannot have A cross B cross C. I repeat, A cross B bracket cross C. That will not be equal to A cross bracket of B cross C. That is different. How is it different? Let me try and make you understand. This vector A cross B cross C, A cross whole of B cross C, which is vector triple product of A and B cross C. So you are taking the cross of A and B cross C. So first of all, what you need to understand is that this vector will lie in the plane of B and C. The proof cannot be discussed at this stage. We are directly giving you the result which should be used here. So here, if this is how I usually remember it, if A cross B cross C, this particular result, A cross whole of B cross C, if it is lying in the plane of B and C, I will be writing it as a linear combination of B and C first. So I will have something times B minus I will have something times C. So this is a vector which lies in the plane of B and C because I'm able to write it as a linear combination of vector B and C. Now what will appear here in these brackets? So how do I remember it? See, when I dealt with this B here, what am I left with? I'm left with A and C. So take the dot product of A and C. What am I dealing with here is C. So what am I left with? I'm left with A and B. So take the dot product of A and B. That's it. Your job is done. Your job is completely done. So you were saying that A cross B whole of A cross B cross C is different. Yes. How is it different? Let me try and explain that part. What I'm trying to say is, let's say if I'm finding A cross B cross C, then how is it different? Do you know how to expand it? No, we don't. But can I write it as, see, this cross is the primary cross we have. So if I swap the order, can I write it as C cross A cross B? But we cannot do it. I can, but if I'm doing it, I need to use a negative sign. So A cross B cross C can be written as negative of C cross A cross B. I hope you're getting it. Again, I'll use the same result. What I know from here is that this product will lie in the plane of A and B. So here, this negative sign will be there as it is. I'll be having vector A and vector B. So I'll be having vector A and then I'll be having vector B. I hope there is no confusion on it. So when vector A is there, I need to take the dot of C and B. Vector B is there, then I need to take the dot of C and A. And of course, when you put this negative sign into picture, this will appear first with a positive sign. So it will be C dot A times B minus C dot B minus C dot B times vector A or of vector A basically. Did you get that part? So all you need to do is remember this formula only. Remember this result only. If you have this result with yourself, you can always conclude all the other results. My motive is to make you remember it with the trick I have given. I hope you will try and remember it. If this VTP is understood by you all, there are certain properties which simply means that follow the steps which you are told previously in the previous slide. And with that, you can conclude all these results. Let us look at this. A cross B cross C cross D. Sir, this looks more confusing. Trust me, it is not. For a while, can you not imagine A cross B to be another vector? Let's say we are treating it as a vector D. So does it not look like vector D cross C cross D? And how do you find vector D cross C cross D? I hope you know how to find that result. And if you know how to, sorry, D is already there. Let me use a different result. Let's say here, to make you understand more clearly, A cross B, let's say I'm denoting by vector E. So how does it look like? It now looks like E cross C cross D. The problem looks like E cross C cross D. Now, do you not know how to expand E cross C cross D? Once you have expanded E cross C cross D, E again can be replaced by A cross B. And by doing that, or after doing that, this is the result which you'll get. So my point remains very simple, that even whenever you're asked to find even more complex versions of vector product, use this substitution, and all you need to remember is that one single formula. Let's get more clarity with this particular question. What does it say? Have a look at this particular result or a question here. It says A is a vector, B is a vector, and C is a vector. They are the three vectors where we are told that C is coplanar with vector A and B. Now, what are the two methods? If C is a coplanar with vector A and B, then C should be written as a linear combination of A and B. That's method number one. Second method. If C is coplanar with A and B, there is another thing which you can use, the vector triple product or scalar triple product. But to keep things simple, I'll use the simpler method, the linear combination here. Let's not complicate it so that we straight away apply the logics we have learned so far and get the answer. So first of all, what you need to understand is C is coplanar with A and B. So if C is coplanar with A and B, can I write C as lambda A plus mu B? Because if C is lying in the plane of vector A and vector B, which means C can be written as a linear combination of vector A and vector B. Now what are we told next? If the vector C is perpendicular to vector B, are you able to recall a question we have discussed previously when we were discussing the dot product? Do you not relate it with that same question only? So in this particular question, I'll be giving you the hints, the approach. I'll not be solving it completely. I'm giving it as a homework. So the next step, what I do is, we are told that if the vector C is perpendicular to vector B. So this is our first hint. This will help us in forming the equation number one. Second equation is C is perpendicular to B. So can I not say vector C and vector B, their dot product will be 0? That's your second equation. Third equation they have directly given, if I take the dot product of vector C with a vector A. If I take the dot product of vector C with vector A, it is 5. That's your clue number 3. Trust me, once you use all these three equations, once you simplify all of them, once you get the answer, you will very easily be able to crack the values of lambda and mu with the help of these three equations. And once you have cracked the lambda and mu, by putting lambda and mu here, you can crack the vector C. And once you have the vector C, finding its magnitude is not a tough task for you. So did you understand? JEE Mains has asked such silly and easy and simple questions on vectors if you know the concepts pretty well. And do you remember how crucial that concept is? Linear combinations of vectors, coplanarity, collinearity. That is something which you need to remember. Now, moving ahead, I hope you can do it by yourself further because you know such questions, you know the concepts, all the hint which is needed, all the clues which are given, which are required for this question are already provided to you. And we are believing and hoping that after all what you are told, or suggested in this particular chapter, after all what is taught to you so far in this particular chapter, you all must be able to solve this particular part very easily and very quickly. Lagrange's identity. So Lagrange has given two identities. One of the identities was square of magnitude of A cross B plus square of magnitude of A dot B or vector A vector B is always equal to, I hope you remember it, you have remembered this particular result, should be equal to, let me get back to the point. The identity suggested by Lagrange's, which I have given you previously, is basically a corollary of this identity, this rule basically. If I replace C cross D by A cross B, do you not think I'll get square of A cross B? That's exactly what I'm saying. So this is Lagrange's identity. If I'm willing to find A cross B dot C cross D, then Lagrange has suggested that you can do this. This is the entire proof, which I'm not explaining right now. I'm just giving you the direct result, which you're supposed to use directly. Let's say in a question, I am asked to find A cross B dot C cross D. Since it is a dot finally, see, it will be a vector, this will be a vector. But then finally, I'm taking the dot of two vectors, which means it is going to be a scalar quantity. So instead of finding the vector product of A and B first, then vector product of C and D, and then finding the dot product, in a simpler language, all you need to do is one simple task. Find A dot C, find A dot D, find B dot C, find B dot D, and then take its determinant. And then you will be able to find this particular result. So again, it's a very crucial result. Instead of using the longer approach, which you are always allowed to, you can use this short method as well, which can be called the short technique, which is simply a formula, a conclusion, which is derived with this particular formula. Along with this, the corollary of it, which we have already discussed previously, was very simple result that if I replace C cross D by A cross B, then I hope you're realizing I'll get the same result which we have discussed as Lagrange's identity previously. So these are basically two identities which look different, but they are simply one single identity. The original identity is this, and from this the corollary has derived, where you replace C cross D by A cross B, which we have already discussed previously in this particular one-shot video. Moving ahead, let us go further. Let us see further. What do we have next? Another question, another crucial one. JEE means 2025 has raised it. Let us read the question first of all. The question says, vector A is given by this, vector B is given by this, vector C is given by this. So D, B, basically these are four vectors A, B, C, D, such that B cross D is equal to C cross D. So they are not three, they are four vectors. And A dot D is 4, so we need to find this. We need to find this. We need to find this. I'm constantly making you see this particular part. Okay, forget that. If nothing has struck here, let me begin with scratch. Let me begin from scratch. First of all, this is what I'm given. What am I given? I am given that B cross D, I often forget this particular part, that B cross D is equal to C cross D, right? Now, I'll take C cross D on the left hand side. So when I take C cross D on the left hand side, you have B cross D minus C cross D. We know that like matrices, we need to take care of the order here when we do the vector product, right? So this D is getting post multiplied, right hand multiplication. So can I not write it as B minus C cross D is equal to 0. What does it mean? If I'm able to write B minus C cross D is equal to 0, then we know that B and C are non-zero. Their difference is also non-zero. D is also a non-zero vector. So if these are three non-zero vectors, and let's say these are two vectors, B minus C is a vector, D is a vector, and their cross is 0, it means they should be parallel. We have already discussed it. If the dot is 0, they should be perpendicular. If the cross is 0, they should be parallel. So from here, if their cross is 0, this implies that vector D is parallel to vector B minus C. Any confusions on it? Now, what I need to understand is, can I write D as a linear combination of B minus C? I hope you remember it. So here, can I say that now on the basis of this, I can write vector D as lambda times B minus vector C. What is B minus C? Let us try and work on B minus C. So vector D from here will be lambda times. What is B minus C? So B minus C will be 3i minus 2i. That should be I. Then minus 3j minus j. Sorry, minus 3j plus j. It should be minus 2j, right? You should be more cautious while calculating things because a single error will make you go wrong, completely wrong. And 3k minus 2k will be plus k. So that's your plus k. So this is how you can define vector D, but the unknown here is this lambda. Okay, how do we find this? We are given a clue, students. Can you not see A dot D? So A dot D is said to be 4. So now let us work on A dot D. So if I know that A dot D is 4, I'll use A dot D. So what is A? Vector A is I cap plus 2j cap plus k cap, right? So that's your vector A. What is D? This is D, which is lambda times I cap minus 2j cap plus k cap, and this is given as 4. This is given as 4. I think I now can write the value of lambda from here, because lambda times 1 minus 4 and 1. So I have 1 minus 4 and 1 is equal to 4, right? Is equal to 4. So from here, this is minus 2. 4 by minus 2 is, I think, minus 2. I hope we are going great. So lambda is basically minus 2. I hope we are going great. So from here, I can crack the value of lambda, which is minus 2. So now if I have the value of lambda, which is minus 2, can I not write the vector D? I hope we all can write the vector D. So once you have found the vector D, can you not find A cross D? So now I leave it up to you that you should do it by yourself. That now solving it further is an easy task, is a very simple task. Why am I saying this? Because you know lambda. If you know lambda, you know vector D. If you have vector D, if you have vector A, can you not find A cross D? And it's mod n square. I hope that's a very simple task. Even if you don't want to find A cross D, do you have Lagrange's identity? That also you can use. So I leave it up to you. Either you find A vector and D vector, A is already given, D vector can be found, their cross can be found, and then this can be found very easily. If not this, use Lagrange's identity. So both of the conclusions I leave up to you so that you can find the answer with yourself or by yourself. Moving ahead, what do we have next? So There we have reciprocal system of vector, the least important topic, but yes, you should know it. That's why we have kept it, to make you understand it. So the reciprocal system of vector is basically a concept. Mostly questions are not asked from this particular topic, but still we'll study it for the sake of studying it, because it is given in the syllabus. You should at least know what is it, because if they ask you or they mention this term reciprocal system of vector, you know, uh, then you should be able to apply this particular logic. What is the logic? First of all, let us understand what is reciprocal system of vectors. What is it? Let us know it. It's a very simple concept, students, that if there are two vectors, let's say there are two vectors, and if I take the dot of them, and if their dot is found to be 1, then they are called the reciprocal vectors. What do I mean by it? It's a very simple result. See, if I define a vector A as B cross C upon box of ABC, this is not mod of ABC, this is box of ABC. So let me make that correction. This is box of ABC here. This is box of ABC here. I repeat, let me begin with this part, B cross C upon box of ABC. So we have a vector B cross C upon box of ABC. Let's say this is a vector which I'm defining as A dash, Can you help me in finding the dot of A and A dash? So if I'm finding the dot of A and A dash, it will be vector A dot B cross C upon box of ABC. Now, what I need to tell you is, if A gets multiplied to B cross C, because this will be a scalar quantity, B cross C will be a vector, so that vector into this vector A. So A dot B cross C, we already know, is nothing but box of ABC. So this will become box of ABC divided by box of ABC, and both of them are scalar quantity, they nullify each other and the product is found to be 1. So they are reciprocal vectors, which A and A dash. So A and A dash are reciprocal of each other because their product is found to be 1. So let's say if I'm given a vector, a system of vectors A, B and C, 3 vectors are given, and let's say of any of these vectors A, B and C, let's say A vector's reciprocal is needed to be found. So the reciprocal of A in this system of vectors is given by B cross C upon box of ABC. Can you not help me with the reciprocal of B and C as well? I hope now you must have understood this part, that in this system of vectors, if I am asked to find the reciprocal of vector B, it will be given by C cross A upon box of ABC. If I am asked to find the reciprocal of vector C, it will be given by A cross B upon box of ABC. But to define the reciprocal of a vector, you need a system of vectors. So here I had 3 vectors A, B and C. With the help of these, I could find the reciprocals of A, B and C respectively by using these formulae, which were A dash, B dash and C dash. Did you get this part? Any confusion on that? So if so far it does not have much importance, but yes, it should be learned and remembered and understood by you. So whenever a question uses, by chance, let's say if a question uses the concept of reciprocal system of vectors, then you should have this process or this modus operandi or this SOP in mind. Did you all get that part? This is what I've been trying to prove. This is what we have already discussed. So I think finally we are at the part where we'll be culminating this chapter of vectors. We have discussed everything related to vectors. We begin with algebra, then we discussed dot, then cross, then scalar triple product, vector triple product, and then the reciprocal system. Most importantly, focus on the first part where we discussed algebra of vectors, which you all should know. Then we discussed dot and cross. Initially in the algebra of vectors, I skipped few basic terminologies, which you already know because you study them in physics. So that part I skipped in this one shot. What is unit vector? What are parallel vectors? This is what you already know. So these basics we didn't cover, assuming or believing that this is what you have been studying in physics, right? Now, the most important part here is that through this one shot, we have tried giving you clarity on what is asked, how is it asked, and how should you study for the chapter vectors. The second learning is that it is again one of those important units because vectors in 3D are clubbed together and questions are formed on them, and they become the second most important unit. So these 4 chapters are done with utmost focus and precision. They always help you in getting a 90 percentile. These 4 chapters are on any day sufficient. So far by looking at the patterns or the trends by JEE-Means. Vectors, 3D matrices and determinants. Always remember it. And I hope you know that all of this is provided to you at absolutely no cost, at absolutely free of cost. These one shots are already available on our YouTube channel. You can watch them. Along with this, in the description, we are giving you the link to the notes, the DPPs, which can be accessed through our PW app. The app is one of those amazing platforms through which millions of students are already preparing for different competitive exams and getting their desired results in success. So I think this is sufficient on this. Let's meet in the next lecture with another new topic, with more clarity, with more understanding, and with more, inclination or acceleration towards your JEE mains percentile. So I think let's call it a day here. Thank you so much. Take a good care of yourself. You have been a great audience.